Welcome back, students. So how are you all? I think I'm meeting you after a long time. So teaching on the board, few concepts like hydrocarbons should be dealt on the paper only, because every reaction there are certain positive charges, negative charges, some radicals formed. So I want you to concentrate on the paper. So I've been taking hydrocarbons on the paper only. So I'm very happy to meet you all again. So based on the request of you all, now countdown has started. JEE exam, NEET exam, your CBSE exams, all the countdowns have started. We are in the month of October, isn't it now? Right. So based on the request, I asked one day, in the community tab, which chapters to start, whether it is states of matter, redox reactions, or general organic chemistry. Then maximum oaths I've got it for general organic chemistry. So I already started at the 10 o'clock slot, where I'm sending questions every day. I'll be sending, not every day, every alternate day. One day would be physics or maths, and one day would be chemistry. Like that, from now, GOC question series, P-block question series, like that till your JEE or NEET exam, the series will be going on every day, right? So one day physics, once again I'm repeating, one day physics or maths, okay, and the other day chemistry. So based on your request, I'll be starting with general organic chemistry. My journey with general organic chemistry, this is my favorite chapter, if I have to say. There are a lot of things which you have to study in general organic chemistry, right? So those who have joined recently to my channel, welcome to my channel. It's your support always is required for me, for this channel to move ahead. All newcomers who have joined me, all the best. Keep updating every day. I'll be sending the videos on daily basis. You keep studying. Maintain a separate book. I keep saying the same thing always. Maintain a separate book for world of chemistry. So students, welcome to one more chapter, that is general organic chemistry, right? So let's see what are we going to learn in general organic chemistry, right? So general organic chemistry, basically it's a grade 11 topic then, but it has very important, means the use or the application of general organic chemistry in JEE NEET is too high, right? Lot of questions will come from this. I'll be doing all the questions also in the questionnaire series as well as in the topic, right? Fine. So my only one request, I'll be taking a lot of pain to upload the videos in spite of my busy schedule. It's very difficult because I hardly get 2 hours per day, okay? In that 2 hours I try to upload a video, so please watch it and try to prepare notes, right? In general organic chemistry, when I take the index of which we're going to learn is electronic displacements in covalent bond. So here first we already studied in grade 10 what is covalent bond, right? We have studied covalent bond is formed by sharing of electrons, right? Both will mutually share and form till they reach an octet configuration, right? Now in this covalent bond we are going to study how is the electron going to displace, means how is the electron, means how is the exchange, means is it going towards electronegative atom, is it electron withdrawing group or releasing group, like that. So electronic displacements, it is electronic displacements are studied in the inductive effect. Again we have minus I effect, plus I effect, like that. So inductive effect I'll be teaching with a lot of examples, reasoning questions, all will be there. So once you click inductive effect in my channel, you'll perfectly get all the information. Then after that, mesomeric effect and resonance effect, I'll be teaching you electromeric effect, and I'll be teaching you hyperconjugation also. Now I'm again telling, I'll be doing examples, worked out examples will be done, questions will be done, all will be there in inductive effect and as well as in everything, right? After electronic displacements, I'll be teaching you about reaction intermediates. So in grade 11 reaction intermediates, if you study, it is easy for you to do the name reactions in 12th. Done. So I'll be teaching about carbocations, I'll be teaching about carbanions, I'll be teaching about carbenes, I'll be teaching about arenium ions, and I'll be teaching about benzynes also. So these are the reaction intermediates. I'll be teaching what is the method, how are they forming carbenes, how are they forming carbocations, what is the situation, everything like that. And next comes isomerism, very important and famous topic. So we'll be studying about structural isomerism and stereoisomerism. Again I'll be teaching optical isomerism in that. In optical isomerism we'll be studying about cis and trans isomers. We'll be studying about cis and trans isomers comes under structural, that is geometrical. In optical isomers I'll be teaching about enantiomers, I'll be teaching about diastereomers, I'll be teaching about racemic mixtures and all those things. After isomerism I'll be taking you into IUPAC nomenclature once again. This will include all the chapters of grade 12th also. Then I'll be going to shapes of carbon compounds, right? I'll be teaching what are the s orbital, p orbital, d and f orbitals also. And finally, I'll end off with classification of organic compounds. In GOC in grade 11, there is a topic called purification techniques. That also will be dealing. Final, that will be the final topic. But this particular part, very important for your competitive exams, right? So please keep noting, students. Let us come back and meet with the first topic, that is inductive effect, in my next video. Thank you for watching. But one thing you remember, without your support, world of chemistry is nothing. Thank you. Right, so let's come back and start with the first topic, that is electronic displacement in covalent compounds in terms of inductive effect. Right, inductive, as we said, inducing means what? Let's see now. Suppose if I have an element like this, just see here. Now I have carbon, right? Now this is linked with an electronegative atom X. So X is an halogen. So X is an halogen, it can be fluorine, chlorine, bromine or iodine. Now what is the concept? In inductive effect, first important thing which you should concentrate is when you have two dissimilar atoms. Let's start writing in that, right? When two dissimilar atoms combine. Okay, now what's happening here? When I see carbon, the electronegativity of carbon is around 2.55 or 2.6 rather, correct? So let us say 2.6. Now the electronegativity of halogen, let me take first fluorine in this case. So fluorine electronegativity is how much? It is nothing but 4. Now what happens when two dissimilar atoms combine with an electronegativity difference? With an electronegativity difference. Now what happens? The element which has higher electronegativity starts dragging the electron density or electron clouds towards itself, isn't it? So this is electronegative, so it starts dragging the electron density towards itself, right? So when it starts dragging the electron density towards itself, what happens? There's a partial negative charge on this and there's a partial positive charge on this. So that, let us write that. When two dissimilar atoms combine with an electronegativity difference, the electron density is dragged towards highly electronegative element. Okay, this is done. So I have written this sentence. Let me write that. Now how does this look? When this drags the electron density, this attains a partial negative charge, whichever accepts partial negative charge, because the cloud has become excess here in this case, and this becomes partial positive charge in this, right? So partial negative and partial positive, done. Now what's happening? This particular concept is called inductive effect. Right? Let's come back and take one more example. Suppose if I have like this carbon, and there's one halogen or electronegative element present at the end. Now what did I say? It is highly electronegative in nature. So what does it do? This starts dragging the electron density towards itself, isn't it? It starts dragging the electron density. So 1. So when it starts dragging the electron density, this becomes partial negative charge, this becomes partial positive charge. Now this also is dragged from here, this becomes double positive. Just let us, I'm writing like this. This also further is dragged, so this gets double. This also is further dragged, this becomes, okay, right? So now what happens here in the last carbon? As soon as this starts pulling this particular thing, this becomes negligible. At C4 carbon, the inductive effect becomes, so inductive effect becomes weak or negligible. Okay, I'm writing the spelling wrong. Becomes weak. Let us write weak. Negligible or weak. So here what happens, because of this electron withdrawing nature or electronegative this particular effect is called inductive effect, right? So what else can I write in this? So inductive effect you can write like this and put a box in this way. And what is the characteristic of this? First important thing you have to remember, this is a permanent effect. This is a permanent effect. But what did I say? After when the distance increases from C1, C2, C3, C4, the effect becomes weak. So you can also write it is a weak effect. Done. Yeah. And next important thing, what should you remember? In the inductive effect, I said there should be in presence of electronegative atom, then only the difference occurs. Done. So you can write and here difference in electronegative. I have mentioned here, not required. These two you mention and finish off. With this concept, there are the inductive effect is again divided into two types. What are they? Minus I effect as well as plus I effect. So let us write. It's divided into two types: minus I effect and plus I effect. Right. So let's come back and start with the types of inductive effect. Right. So we've understood that there are two things. One is electronegative atom should be at one end and electropositive element on atom on one side. So electronegative atom starts dragging the electron density. The same concept when I take in inductive effect, as I said, there are of two types, that is minus I effect as well as plus I effect. Minus I, when I say minus I, very careful, remember minus I effect is always shown by electron, means minus effect is basically electron attracting or electron withdrawing groups. That is what you should remember. So minus I effect is shown by electron withdrawing groups, EWG, or electron attracting groups. Both are same. Same example I'm again taking. Suppose if I have 1 carbon, 2 carbons, 3 carbons, 4 carbons, and there is X here. Same example which I have taken earlier. I said this is highly electronegative. So this starts dragging the electron density from all these carbons. So this is C1 carbon, C2, C3 and C4. As it drags the electron density here, again from here, again from here, again further from here, right? Done. So because this drags the electron density, this gets partial negative charge, this becomes partial positive charge. This further becomes like this, we write like this. Okay, here, this is what you should remember. Now what happens when it comes to this particular carbon? As I said, the same again. At this carbon, the charge or the inductive effect will become negligible. Here the inductive effect is negligible at the C4 carbon. Now how will I write this particular thing? If I write the first thing in C1 carbon, which has partial positive charge, the inductive effect is greater. In the second one, in the C2, partial positive charge, inductive effect, this has greater than C3, and when it comes to C4, this is negligible. Correct? Right, negligible. Done. So this particular effect is called minus I effect. Just pulling, it's the same concept. Plus I effect will change, that is electron releasing. So minus I effect, first important thing, it's shown by electron withdrawing group. This is how you have to show, and then comes according to this order, this is one. Now because what is the use? Where are we applying a minus I effect? So minus I effect basically explains the acidic nature and basic nature. There are a lot of examples which are asked every time in question papers. So I'll be dealing all those examples now. So what is important to listen? Minus I effect application. So minus I effect basically, as I said, it explains the concept of acidity and it explains the concept of basicity also. Okay, basicity also it explains. Fine. So you have to be very careful what way they are going to ask you acidity examples and basicity examples. Now let's come back and start with the acidity examples and basicity examples based on this concept only. Now, right. Let's come back and see the effects of minus I effect. So minus I effect, what did we learn just now? We said it is an electron withdrawing nature or attracting nature, which will attract electronegative atom should be there. Done. So when I see the effect of minus I effect, so like the same thing, okay, effect of minus I, same thing every time. Done. So minus I, always remember acidic nature due to minus I effect, acidic nature is increased and basic nature is decreased. Okay, let us see what it is. Let's see. Suppose in the exam paper, they've given you two acids, they're asking you to compare the acidic nature. They're giving you two bases, they're asking you to compare the basic nature. How should you do that? Based on this concept only. Now, chloroacetic acid is given to me. Now, let us write the formula. So, chloroacetic acid is chlorine on one side, acetic acid. Basically, acetic acid is this one. No? Let us write acetic acid and come back. So, it is COOH is acetic. This one, CH3 is acetic acid. Now, what did I do? I have removed one hydrogen from here and I've added chlorine here. So, this is chloroacetic acid. Done. So, now let me write the COOH like this, O and OH. This is chloroacetic acid. Now acetic acid, let us write. I've written CH3, C double bond O and H. This is acetic acid. Next example which they gave me in the exam paper is ammonia. So NH3 and hydrogen here, hydrogen with lone pair of electrons. Now when it comes to aniline, what is the formula for aniline? It is benzene ring like this. And you have nitrogen H and H. Again, nitrogen has lone pair of electrons. Now, when it comes to water molecule, right? So, water is H2O, right? So, again, 1, 2, 3, 4, 5, 6, 7, 8. When it comes to phenol, phenol also formula benzene ring with O and H. Again, a lone pair of electron. Now observe carefully, they are asking me to write the order. Now when I come to the first case, I have to prove which is more acidic in nature. Just concept. Your concept should be based on this only. Minus A effect, electronegative atom. Here in this case, there is an electronegative atom. The electronegative atom is absent. So what does it do? It starts dragging the electron density towards itself. So when it starts dragging, the bond here becomes weakened and it releases H plus ion. That's why it is an acid, isn't it? So it starts dragging. So minus I effect is more. But in this case, what happens? There is here also, yes, I accept that. But here, this is electron releasing group. That is very important. Electron withdrawing group, electron releasing group. Done. So here in this case, because of the electron withdrawing group, minus I effect is observed. Hence, this is more acidic than this one. So let us write, this is more acidic than acetic acid. Done. In the next case, both this is a base, this is a base. Why is this a base? Because ammonia has a lone pair of electron, but something which donates lone pair is a base, isn't it? So ammonia is a base, that also is a base. Now I have to see which is more basic in nature. So in this case, when I see nitrogen, around nitrogen there are only hydrogens. But here in this case, when I see aniline, there is an electron withdrawing group. This benzene ring is an electron withdrawing group. It tries to drag the electron density. So I'm putting one arrow like this, electron withdrawing. So let us write phenyl group, what this group is, benzene group is electron withdrawing. What will happen here when it is withdrawing? Which effect is more? Minus I effect is more. Minus I effect is more. So among both, which is more basic? That means this is more basic. So in the other way, let me write ammonia is less basic than this. Done. Yeah, let us come back to water. Now here water neutral, but we're comparing the acidic nature because phenol is acidic in nature, isn't it? So let's see how can we justify. Here in this case, this is lone pair of electron. On either side you have water hydrogen present, but here in this case below oxygen there is an, again benzene is an electron withdrawing group, right? I did one video, electron releasing groups, electron withdrawing group. Please watch that video also. I have listed out all the things. So here this is again electron withdrawing. This electron it's dragged by the benzene ring. So what is happening here in this case? Again this is phenyl group is electron withdrawing. So again what do you see? Minus I effect. So among these two, which is more acidic? So let us write water is less acidic than phenol. So let us write the underline the examples. Chloroacetic acid, acetic acid, ammonia, aniline, water, phenol. So what we write? Chloroacetic acid is greater in acidic nature. Ammonia is less in basic nature. Water is less in acidic nature. Right, now let's come back and see one more example based on minus I effect. Now here what is the example given? Which among the following is most acidic? Following is most acidic. They've given me A, B, C and D option. First of all, as soon as you see some a particular question like acidic nature, basic nature, you immediately your concentration should go on the electronegative atom. So electronegative atom here is fluorine is here in the first carbon. In the second case, it is present in the second carbon. In the third case, present in the third carbon. In the fourth case, in the fourth carbon. Now I said inductive effect as it goes means it proceeds from C1, C2, C3 and C4, it becomes negligible, I said. And yes, so here in the first case, what happens, as I just now, what did I say just now? I said inductive effect, remember this keyword, reduces with distance, okay, it reduces with distance, fine. Now in the first case, electronegative atom is present in the alpha carbon, in the second case beta carbon, in the third case gamma carbon and delta further. Now when it is present in the first carbon, it tries to drag the electron density towards itself and finally towards here. Here then what happens? Here there is a charge separation and immediately this H plus is released out. When the H plus is released out, isn't it acidic in nature? Something which releases H plus is acidic in nature. So because it is very close by, it tries to drag the electron density and this becomes H plus and this becomes C carboxylate ion. Right. So now what happens? This, because of the release of H plus, immediately release of H plus, this is most acidic in nature. As I said, this is reducing as with distance it proceeds. So easy. So first case, so A is the correct answer. Now distance is increasing because it has to go here, here, and here. That's an option comes next. So first case, very fast, little bit less. In third case, more or less. In fourth case, it becomes negligible only. So first option is plus. Closer the electronegative atom, more is the acidic nature of the compound. Remember that. Further, what happens? This carboxylate ion, whatever is there, it is stabilized by the minus I effect of fluorine. Right? So it's simple. So let us write that also. Carboxylate ion is stabilized by minus I effect of fluorine. That's it. Let's come back and see one more example. Right. Now, let's come back and do one more question based on minus I effect. Let's see this question. Arrange the following acids in the order of decreasing acidic strength. Decreasing acidic strength you have to write. That means whichever is least acidic, that should be written at the last. And whichever is highly acidic should be written in the first, in the beginning. Now, they've given us 1, 2, 3, 4 options. What is the difference? First, let's see. All the electronegative atoms are different. What is similar? CH2COOH is similar in all the cases. Now your concept of minus A starts here. So we already know, according to this minus A effect, electronegativity order, fluorine is more electronegative than chlorine, fluorine, chlorine, bromine and iodine. This is the electronegativity order. This is highly electronegative 4. That's why wherever fluorine is there, the minus I effect will be maximum. Right? So done. So when I see all these, so fluorine is here, that means obviously it tries to drag the electron density towards itself. So it is highly acidic in nature. This compound, they asked me which is acidic based on acid strength. So let me write fluorine, it tries to drag the electron density. So let us write 1, 2, 3, 4 arrows. So this is highly acidic. This is greater than chlorine. Now let us reduce the number of this one to show 1, 2, 3. Here I have mentioned as 4 just for your comparison. 3. Now chlorine is more acidic than bromine. So here I have written 3 arrows. Now let me write 2 arrows. Then further, this is more acidic than, because I don't have place, I'm writing it here. It is more acidic than this. So this is your order. They have asked me to write order of decreasing acidic strength. See here, the acidic strength is decreasing. This is greater than this. This is greater than this. This is, did I write something? Okay, I wrote less now. So this is greater than this. This is greater than this. This is how you're going to write. Right, now let's come back and learn about plus I effect. So minus I effect, hope it is clear for you all. Remember carefully, whenever my acidic nature is given to you, you have to think about the electronegative atom, right? So when it comes to plus I effect, now the whole concept changes. It's the opposite to that. Plus I effect, you will be speaking about electron releasing groups only. So electron releasing groups, you will be maximum seeing alkyl groups. So different groups also are there. I'll be giving you the list. Again, I'm mentioning, I have done a video based on electron withdrawing group and electron releasing groups. Please watch the video, right? So electron releasing groups. So plus I effect, that means suppose if I have carbon atom, carbon chain in this. So here they're given list of the examples. Before I go to that, and let me take. So here instead of electronegative atom, let me take Y now. Done. Here among these two, this is electron releasing group. So what does it do? It tries to, like, it starts releasing electrons. Done. Fine. So when I have to show, this is, I'll put this arrow towards this electron releasing groups. Done. So to explain that concept. So now what happens? More number of electron releasing groups, more will be the plus I effect. Remember once again, more of electron releasing groups like alkyl groups, basic examples, more of plus I effect. Plus I effect. Done? Yes. How is that? Suppose if I take these examples, let's see. These are all alkyl groups, isn't it? Done? Yes. So in these alkyl groups, here how many alkyl groups are present? One alkyl group, that is methyl group. Here how many are present? 2 are present. 2 plus 1, 3. Here how many? Okay, 3 plus 1, 4. Here how many? Again 2. Now which is maximum among all these? When I see, this is a maximum number of alkyl groups, 3 plus 1, 4. So whichever has more alkyl group, that will have more plus I effect. So write the order now. CH3 taken thrice has more plus I effect compared to, next comes your, have I written both same? Okay, I think I have written both same only. Let us not take this example. 3 to 1, that only I will take. So compared to the second one, CH3 taken twice, CH. The next one, after this, the least will be CH3. Hope this is clear, right? So this concept is based only on the alkyl groups. So this has more of plus I effect and this has less of plus I effect. Done? Because there is only one alkyl group present. Suppose if I take this example now, what is this example teaching us? Let's see. Now I said the electron releasing group. So remember always minus I effect and plus I effect when I compare the acidic nature and basic nature. Remember this concept, that will be easy. When I draw a table like this, okay, let us make columns like this. Let us write this as a first column, acidity, and let us write the next column as basicity. Fine, let me divide this. First I'll write minus I effect, then I'll write plus I effect. Always remember minus I effect, acidic character, acidic nature increases. Plus I effect, acidic nature decreases. When acidic nature increases, basic nature decreases. When acidic nature decreases, basic nature increases. That means plus I effect, basic nature increases. Remember that. So let us take this example. Suppose if I take water, so I am going to take with respect to WRT, means with respect to water. I am comparing two, one is methanol, one is phenol. So methanol formula is CH3OH. Phenol, the formula is OH. Correct? Yes. Now what happens? What should I do? With respect to water, I am comparing which is acidic and which is basic. Now in case of methanol, this is an electron releasing group. Here, this is an electron withdrawing group. Correct? Done. So now what happens? Electron releasing group releases. So when it is releasing the electrons, what will happen? I said electron releasing groups. Simple. Once again, electron releasing groups means they will show plus I effect. Electron withdrawing group means they will show minus I effect. Let's come back. Plus I effect, what will it show? It will increase basicity. So this is basic in nature. Minus I effect, what will it do? It will increase acidity. So this is acidic in nature. Simple. Once again, electron releasing group means plus I effect. Plus I effect always increases basicity. Basic in nature. Electron withdrawing group Benzene is electron withdrawing group. With electron withdrawing group means minus I effect. What will happen? It will increase acidity. So acidic in nature. Right. Welcome back, students, to one more session of your general organic chemistry. So in the previous video, I've taught you what is meant by plus I effect and minus I effect. I also have taken certain examples. Done. So now let's see the applications of inductive effect. A lot of reasoning questions will come from this. Let's understand carefully everything. So whenever you study about minus I effect and plus I effect, remember one important concept, right? So basically, let me speak in terms of stability. So here, inductive effect explains, or it is, the concept of this is applied in studying the stability of carbocations. Very important. You'll be getting questions based on carbocation order. We'll be studying about stability based on carbanions. I'll also be teaching applications of inductive effect based on the acidic nature of carboxylic acids, basic nature of aliphatic amines. So let us write the applications and start applying that. So what are the applications? It is used to explain stability of carbocations, where I have taken one example already. I need to reason this. It will explain the stability of carbanions, then okay, carbanions. It also explains the acidic nature of carboxylic acids. It explains the basic nature of aliphatic amines. Done. So let us take all the examples and learn. Now suppose if they win such questions, now what did they say? I am learning in terms of stability of carbocations, because all are carbocations in this case, isn't it? Done. So order of stability. Remember stability, remember this concept, put it in a box. Stability is directly related to plus I effect. Stability is inversely related to 1 by minus I effect. Remember this. Means stability, plus I effect increases means stability also increases. This is inversely related. Minus I effect increases means stability decreases. Done. So when I speak about plus I effect, tertiary is always greater, means it has more stability than your secondary, more stable than primary carbocations. Now let me start. Let me number this. Suppose let me number this as 1, this is 2, this is 3, and this is 4. Because I don't have space, I'm writing the numbers. Now based on this concept, I'm applying here, which is more stable carbocation. Done. So here when I take tertiary, I said more stable. So among all these, what is tertiary? 4. This is tertiary carbocation, more stable. Then comes what? Secondary, which is secondary in this. This is secondary, 2, greater than. Next comes primary. So this is primary carbocation, 3. This is methyl carbocation, so 1. This is the order for the first case. Now when I come back to the second case, right, there are different things now, you have to be careful. Now in the exam, they've asked me the order. Now first concept, stability is directly proportional to plus I effect, isn't it? So here in this case, methyl carbocation, there are 2 alkyl groups. That means it shows which effect? Plus I effect, because it is electron releasing group. So let us number it. This is 1, this is 2, this is 3, this is 4 again. Okay. Now in the first case, 2 is greater. Correct. Now let us come back and compare. Now among all these, next carbocation, which one should I take? See here, this is electron withdrawing group, C6H5, and you have a methyl carbocation also here. Rather, if I have to say ethyl carbocation, next comes that order. So that is 3. After that, next, okay, I have to compare between nitro and chlorine. Chlorine electronegativity here. That's why that comes next. Next comes 4. After that, last is the nitro group 1. So this is the order of stability of carbocation. And then third one, if I take the same concept, but here again you have CO group, here ether, and there your carbocation, direct carbocation without any functional group. So again when I number this is 1, this is 2, this is 3. So among all these carbocations, which is more stable? Right. So now when I have to write this, now careful, this is the function group here, this is the function group. So when I compare, because I'll be doing certain reasoning part of this, why is that, which is a more electronegative, why is the CO group compared to this is less, all these I'll be discussing in just a few minutes. So just see, as of now I'm writing the order among all these. This carbocation 2 is more stable than 3, more stable than 1. Okay, just remember as of now. So this is how you're going to write the order. So hope this concept is clear, students. We'll apply this to these questions. Right, now let's come back and see one more application of inductive effect. Done. So here in what we learn, we have studied about relative stabilities of carbocation. Tertiary, more stable than secondary, more stable than primary. That is what we have studied. So here when I have example like this with alcohols, what should you remember the concept is? Stability of alcohols. Okay. OH is alcoholic functional group, isn't it? Is directly related to, let me put it in a box. Yeah, is directly related to the, what do you say, stability of the carbocation, right? The same concept, stability of alcohols directly related to the stability of carbocation. That means I'm trying to explain stability of carbocation. What carbocation is stable? Tertiary is carbocation is more stable than secondary, more stable than primary. So based on this order only, we will speak about the stability also. That means tertiary carbocation is more stable alcohol than secondary. Secondary is more stable than primary. Now they've given us this. Now I have to write the order of stability. So among all these, which is tertiary? This is tertiary, isn't it? Let me write the order. Fourth comes first, greater than. Then next is, according to this order, third. Then after this is second. So this is primary, isn't it? So this comes first. So this is what is the concept. So in grade 12 you'll be studying about dehydration of alcohols also. There is a reaction mechanism. In that you will be doing the dehydration based on this concept only. Tertiary dehydration, exactly means tertiary carbocation is formed first. That is how you show the dehydration, separation of water molecule. Done. So this is how it is related. So we have studied the application, the first application of inductive effect, that is stability of carbocation. Now let us come back and study the concept of stability of carbon ion. So remember this concept for carbocation. Right. Now let's come back and see the next application of inductive effect. What was the first application we've seen? It explains the stability of carbocation. That is what we said. Done. So next we'll study about the stability of carbon ion. Okay, carbon ion denoted by minus, isn't it? Now, one important clue which you should remember, let us write that in the box and then come back to this. So whenever you are given an order of carbon ion in the exam, okay, so already I've given for carbocation earlier, I've written some important clue in the box. Now, if a carbon ion concept or carbon ion order is given to you, what clue should you remember? Stability. See, stability of carbon ion. I'm not writing completely. Stability is directly related to minus I effect, and stability is indirectly related or inversely proportional to plus I effect. So what does this mean? Let's see. Stability is directly related to minus I effect. That means if I have minus I effect means what? Electron withdrawing groups. Done. If more of electron withdrawing groups are there, stability of the carbon ion is more. Once again, if more of the electronegative groups or electron withdrawing groups are there, stability is more. Other way, if more of the electron releasing groups are there, stability will be less. Okay, understand the concept. Let us apply. Now, so here they are given two examples. Both are carbon ion examples only because all are minus only. Done. Here when I take, let me apply the first. First of all, let me see whether it is minus I effect or minus I group or plus I group. So all are methyl groups only in this. All methyl groups or alkyl groups are electron releasing groups. Electron releasing groups means, always remember, ERG means it is plus I effect. Remember this concept. Second case, NO2 electron withdrawing, Cl electron withdrawing, NO2 electron withdrawing. This is electron releasing. So here in this case, you all have electron withdrawing group, that means minus I effect. Correct? Now compare this with this. Minus I effect groups are more, stability is more. Now minus I effect group here, tertiary. Okay, let us come back to this first. Let us write this. So minus I effect here, electron withdrawing group. Let's see. Here I have nitro, you have Cl, nitro, and this. Here nitro is directly linked to the carbanion. Here nitro group is a bit adjacent to the next carbanion. Here chlorine group is there. When I see nitro and chlorine among both, nitro is more electron deactivating group, means electron withdrawing group. It is a stronger electron withdrawing group or electron deactivating group compared to chlorine. Now let us number this. This is 1, this is 2, this is 3, this is 4. Okay, right. Now this is stronger, isn't it? I said just now, it is more electron deactivating. So this carbanion is more stable. Next comes the same one with nitro. Wherever nitro is there, that one you need to write first. Why? Because it is a strongly deactivating group compared to chlorine. Now, so next comes 3. After that comes 2. After that comes 4. This is the order. So now this is what is I'm trying to tell you. Now let's come back and see the next concept, that is stability directly related to your so inversely related to plus I effect. More of plus I groups, stability will be less. Correct? Okay. More of plus I effect groups are more means stability will be less. If stability is more means plus I effect group should be less, the other way round. So once again, this particular thing, among all these, which has more plus I groups, this electron releasing groups. Let us number this: 1, 2, 3, 4. Correct? Now see, according to the order, stability, let's see which is more stable among all these. Whichever has less plus I group, that is more stable. Which has less plus I group? 1. Correct? 1, because only one methyl group is present. 1 is more stable then. After 1, what is the next one? This is, okay, 3. This one, no? 3. This is more stable than 4. This is more stable than 2. Just see here. Once again, let us read and understand. More of plus I groups. Which is more? This is more. 2 is more. Whichever has more of plus I groups, the stability will be less. See here, more of plus I groups, stability is less. Come back down. More of minus I group, stability will be more. More of minus I group means here more means it is closer to the, means it is attached directly to the carbanion, stability will be more. Direct. Right? This is how you have to reason the question. Hope this concept is clear, students. Let us come back and learn one more example. Right. Now let's see the next application of your inductive effect. What was the first application? It is explaining the stability of carbocation. Next application was explaining the stability of carbanion. Now let us see the basic nature of aliphatic amines. Done. And then last application would be acidity of carboxylic acids. Done. So when I speak about basic nature, first of all, always remember in terms of electron withdrawing group and electron releasing group. Till now, I hope you understood what is electron withdrawing and electron releasing group. Let's write that. It's simple. Remember this. Electron releasing group, ERG. Releasing group means always plus I effect. Electron withdrawing group means minus I effect. Remember, if electron with releasing groups are there, what will happen to the basic nature? We are speaking in terms of basic nature, that's right. Whenever there is an electron releasing group present, understand, basic nature increases. Whenever electron withdrawing group is present, basic nature decreases. So already I have made one video with electron releasing, electron withdrawing group. Like suppose if electron releasing group, alkyl group, OR, OH, like that. Electron withdrawing group, chlorine, isn't it? Nitro, cyano, all these are electron withdrawing group. So remember this. Next important concept which you should remember is, if I have to speak about in terms of the stability, right? if I have to speak in terms of basic nature, not the stability, I'm sorry for that. So in terms of basic nature, remember this important clue. What is that? Basic nature of amines is directly related to plus I effect. Next important thing, basic nature of amines is indirectly related to minus I effect. What does that mean? That means if more of plus I groups are there, that means more of electron releasing groups are there. That means basic nature will be more. Same thing. Next, if more of minus I groups are there, that means electron withdrawing groups are there, the basic nature reduces. Right, using this concept, I'll solve this. Now among all these, right, so write the order basic nature, or write in the decreasing order of basic nature. That means the last one would be least basic. Now among these, I said this is primary amine, secondary amine, tertiary amine. Tertiary means there are 3 alkyl groups. Okay, let us write that. Suppose this is primary amine, this one. This is secondary amine. This is tertiary amine, correct? Ammonia and C6H5NH2. Now I have to write the order. I said more of alkyl group, that means more of electron releasing group, means more of plus I effect. That's it. So this has plus I effect, this also has plus I effect, this also has plus I effect, because it is alkyl group. Now compare. Among these, more of alkyl groups is this, that means it has to be 3. Then comes greater than 2, then comes 1, then comes ammonia, then comes C6H5, because it is electron withdrawing group, benzene, NH2, like this. This is the order. Normally if I have to see, the order will be like this. But what is the order? This is not the correct order. Correct order is 2 degree greater than 1 degree greater than 3 degree greater than ammonia greater than C6H5NH2. This is the correct order. Remember, let us write the reason now. This is the correct order. Why is this? Because when I speak about tertiary alkyl group, here what happens in case of tertiary alkyl group, you have what is important thing, one pair. You have 3 bulkier alkyl groups. When 3 bulkier alkyl groups, what is the concept? Steric hindrance. Lot of, this bulkier group, this bulkier group, it creates lot of steric hindrance, the bulkiness on the nitrogen atom. So ability to donate this electron pair will become difficult, right? So first important thing, why is tertiary not more basic than secondary and primary? First reason, due to steric hindrance of alkyl groups. The steric hindrance, it will not allow the nitrogen to donate the electron pair. Okay, I'm not writing the full sentence. So because of this bulkiness, that the electron pair is not, if it is not donating, it is not basic, it's less basic in nature, isn't it? So steric hindrance of alkyl group reduces basicity, right? The next case, because of this bulkier group, the solvation effect, you all know, I think, solvation effect, because of that the solvation effect also is very less because of this bulkier group. So solvation effect also reduces basicity. Okay, this is the concept. So the correct order is this. This is the wrong order, don't write that. So secondary greater than primary, primary greater than tertiary, tertiary greater than ammonia, ammonia is more basic than this one, aniline, right? Yes. Now let's come back and learn the next application of inductive effect, that is explaining the acidity of carboxylic acid. Earlier what did we see? We have seen how inductive effect was useful in explaining stability of carbocation, that is, we've already seen. Then we have seen how it was useful in explaining the stability of carbanion, that also we have seen, and certain examples also were discussed. Then I've explained you how is this used in explaining the basic nature of aliphatic amines. Now I'll be teaching you how is inductive effect useful in in explaining acidity of carboxylic acid. So we very well know in carboxylic acid, why are carboxylic compounds called as, means why are they called as acids? Because they release H plus ion, that is understood. But as a grade 11 and grade 12 student, you should be clear carboxylic acids, and basically when you dissolve it in water, they dissociate into carbozylate ion as well as H plus ion. That is what is the concept. So what am I trying to tell you? Whenever I take acetic acid, like carboxylic acid, when I dissolve it in water, it dissociates into CH3CO minus and H plus. Because it releases this H plus, we are saying it is acidic in nature. But what is important, why is it releasing H plus? Because when I see this carboxylic acid, carboxylate ion or carboxylic ion, anything, this is carboxylic acid and this is carboxylic ion or carboxylate ion, anything. So when I compare these two, important concept is carboxylic acid or carboxylic ion is more stable than carboxylic acid. That is the first important thing. What am I trying to tell you? Carboxylate ion, carboxylic ion is more stable than carboxylic acid. Why? That is first reason which you should know. Because when I see carboxylate ion structure, what is the structure? This is CH3, C, double bond O and single bond. Here when I see carboxylic ion or carboxylate ion structure, here in this case there is separation of charges. Means there is dispersal of charges between two oxygen atoms. What charge? Negative charge. That means here, once suppose there is a negative charge here. This shows resonance, because this is stabilized by resonance. Once the negative charge is shown, so okay, I should not put negative here, I should put negative here. Yes. So negative charge on one oxygen, when it shows its resonance stabilized, so when it shows resonance, this charge shifts here and the double bond shifts here. So CH3, C, single bond O and double bond oxygen. Now see here, negative charge is shared or it is dispersed between one oxygen here and one more oxygen here. That is why carboxylic acid is carboxylic ion is more stable than carboxylic acid. Once again, carboxylate ion or carboxylic ion is resonance stabilized. Why? What happens here? There is separation of charges between, or the separation of negative charge between one oxygen and second oxygen. More is the separation of charges, more is its stability. Remember that. Let us write that. Okay, first let us write the resonance stabilized one. This is a resonance hybrid of, instead of CH3, let me take R, C, oxygen, oxygen, resonance stabilized, overall charges minus. So what are we writing? More of charge separation, more of charge separation. What is more? More of charge separation, more is its stability. Okay, more is its stability. So right, that. So how is it related to acidic nature? More is its stability, more is its acidic nature. Let's see how it is. So now this is a concept. From here I'll be taking you into the concept of inductive effect. The same carboxylic ion or carboxylate ion, when I take that, suppose if I have an electron releasing group or electron withdrawing group around this. Let me take both the conditions and explain this. So now I will be taking carboxylic ion. Why are we taking that? Because as I said, it is more resonance stabilized. Yes or no? Yes. Right. Now let's come back and see what happens, or we've already started in applications of inductive effect. We'll see what happens when you have a minus I effect groups and plus I effect groups on the particular acid. Done. So suppose if I as I said, I'm going to take the carboxylate ion. We also studied why I'm taking carboxylate ion, because it is more resonance stabilized and there is dispersal of negative charges. Fine. So now I'm going to take the carboxylate ion. What is carboxylate ion? Basically, this is something like the CH3, C, oxygen here, resonance stabilized. This is what is the carboxylate ion. But here what am I going to do? Instead of the CH3, now I'm going to take an X. Here in this case I'm going to take Y. So what is the difference now? This is resonance stabilized and this is here X is electron withdrawing group. Okay, so X is electron withdrawing group. Now here Y is what? Electron releasing group. Electron withdrawing group always shows which effect? It's going to show minus I effect. Electron releasing group is going to show us plus I effect. Correct? Yes, this is the concept. Now I said, whenever there is an electron withdrawing group, arrow on this side. Whenever there is an electron releasing group, arrow on this side. What happens here? The electron withdrawing group is going to disperse the negative charge on oxygen. So it's going to disperse, it's going to drag the electron density here so that the negative charge, there is a cleavage of this bond. So the negative charge is dispersed between oxygen and oxygen. So first important thing is negative charge is dispersed among two oxygens. Here what happens? It's donating more and more of electrons. So is there any dispersal or distribution of charges? No, isn't it? So negative charge is not dispersed, or it is less dispersed, not dispersed. Done. Now what is this concept now? When negative charge is dispersed, more of the negative charge dispersed, more is the stability. So what will happen? Because of this, stability increases. Done. Here, because of this, stability decreases. One more relation, as the stability increases, acidic nature or acidic character increases. The same thing the other way, acidic character decreases. That's it. So remember always, whenever there is an electron withdrawing group, acidic character increases. Whenever an electron releasing group, acidic character decreases. Now let's come back and see certain examples based on this, so you'll have a clear understanding about the concept. Right. So let's come back and see some examples based on acidic character. So what did we learn in the previous video? We said whenever you're speaking about acidic character, think about your concentration should go on electron withdrawing group. When an electron withdrawing group is there in the particular example, that means your acidic character will be more. That, remember that. Right. So now based on that concept, let me see. They've given me 1, 2, 3, 4. I have to arrange the decreasing order of their acidity. As soon as this is given, just put numbers 1, 2, 3 and 4. Done. So acidic character means, what should you remember? As I said, electron withdrawing group. So in the first case, do we have electron withdrawing group? Yes. In the second case, do we have? No. In the third case, no. Fourth case, no. But what is important? I have to arrange according to the decreasing order. The last one will be least acidic. The first one will be highly acidic in nature. So whichever has electron withdrawing group, EWG group, that means minus I effect group, that will be more acidic in nature. Done. That is what, because it drags electron density, there is a site created and releases H+. So first is highly acidic in nature. Next, now I have to compare between this and this and this. So here there are more alkyl group. So more alkyl group means which one? This is electron releasing group. Which group is this? Plus I group. Here also you have two plus I group. So compared to this one and this one, this is acidic in nature, isn't it? So we have already seen, because it releases H+. Next comes 3. Now greater than, this is more acidic. Now greater than compared to this one too, here there are 2 electron releasing groups. Here how many? There are 3 electron releasing groups. Electron releasing groups will reduce the acidic character. So this one comes 4 and this comes 2. This is the order. This is least acidic, this is highly acidic. Let's come back to see this. Again the same concept. Here in this case, COOH group is common. But what is different? The electronegativity, negative element is different. Higher the electronegativity of the element, more is electron withdrawing nature. More is electron withdrawing nature, higher is the acidity. Now let us write that. What I said, first thing I said, higher electronegativity. Done. Higher is electron withdrawing nature. When higher is electron withdrawing nature, higher is minus I effect. When minus I effect is higher, obviously it is more acidic in nature. More acidic in nature. So let us write number the compounds given. This is 1, this is 2, this is 3. Now, among all these, which is higher electronegativity, first comes fluorine, greater. Next one after fluorine, next is after fluorine, chlorine, 3. After that is bromine. So this is the order. Let us see some more examples, where you need to arrange the compounds given compounds in decreasing order of their acidic nature, right? So here what did they give us? 1, 2, 3, 4. 4 compounds they have given us. Let us number them 1, 2, 3, 4. It's easy for us. Now what is the concept? More of the electron withdrawing group. That means more of minus I effect. That means more of the electronegative element. Higher is acidity. Now in this case you have fluorine, one electronegative element. This is bromine, iodine and chlorine. Easy, isn't it? What is the electronegativity order? Fluorine greater than chlorine, greater than bromine, greater than iodine. So arrange it. So wherever fluorine is there, that is highly acidic. After fluorine, where is chlorine? Greater than 4. 4 is greater than 2, 2 is greater than 3. This is the order. Done. Let's come back and see. Here again, 1, 2, 3 different acids are given to us. But what is the difference? Here you have 3 electronegative atoms, that's chlorine atom. Here 2 electronegative chlorine atoms. That's okay. 1 is there. Here 2 are there. So more of electronegative atom, that would be stronger acid, greater. Then comes 3, then comes 2. This is the order. Let's come back to this last. What is this now? All are acids, but only difference is position of the halogen or the electronegative atom. Here, halogen is present in alpha position. Halogen is present, this is alpha, this is beta, this is gamma. Here, halogen is present in alpha and beta position, and this is where it is present. Let us number this. Okay, 1, 2 and 3. Now one thing you should remember, farther is a distance, means if the halogen is present adjacent to the carboxylic acid, then it is highly acidic. If the distance increases, inductive effect decreases, acidic nature also decreases. Once again, if it is closer, that is highly acidic. If it is very far, it is less acidic, because the effect we've studied, isn't it? When it goes to C4 carbon, the inductive effect, it becomes negligible, right? So this is very close. So 1 is highly acidic compared to 3, which is highly acidic compared to 2. This is your concept. So this is how you're going to do, or this is how the inductive effect helps in explaining the acidic nature of carboxylic acids. Welcome back, students, to one more session. Right, so today we're going to learn the differences between tautomerism and resonance. So we've already seen the resonance concept, we've seen the tautomerism concept, where there is a dynamic equilibrium existing between keto and keto form and enol form. Right, so now today we'll be seeing the differences. So whenever you're writing a differences concept, first remember you should write the criteria on the left hand side. So on what criteria we are going to differentiate, like this, right? So I've picked up these criteria and start discussing. So when we speak about tautomerism, change of position. So in tautomerism we have seen what happens, an atom changes place, but in resonance it involves what? Change of position of pi electrons, correct? Right. So let us write, in tautomerism an atom changes place, correct? Because from keto form, double bond O, it will become OH in all form. But here in resonance, what happens? It involves a change of position of pi electrons, or I can say unshared pair. Yes, Unshared electrons. Unshared electrons. Now, when I say separation, tautomers are different compounds, so they can be separated by suitable methods, right? Tautomers can be separated. When it comes to resonance, the resonating structures cannot be separated. Why? Because they are imaginary structures. We are assuming, okay, this is going to shift from ortho, again para, then ortho, and finally forming resonance hybrid. So they cannot be separated. Cannot be separated. Why? We like the reason, because they are imaginary structures of same compound. Separated as they are imaginary structures. Okay, they are imaginary structures. Fine. Imaginary structures. The next criteria, let's see. Suppose functional groups. We are speaking of functional groups. So in tautomerism, two tautomers have different functional groups. One is the keto form, one is the enol form. Here it is, right? Two tautomers have different functional groups. But in resonance, what will happen? In resonance, whatever this one is there, they have same function group. Only canonical structure. In that canonical structure, they have same functional group, right? In all canonical structures, in all canonical structures. Canonical structures of a resonance hybrid. This is what is important of a resonance hybrid. Okay, hope students this is clear. Now, equilibrium. So in tautomers, what you will say, there is a dynamic equilibrium which exists. Dynamic equilibrium, I also told you in the earlier video how does it shift, which is the maximum percentage. But in resonance, only one compound exists, resonance hybrid. Only one compound, that is resonance hybrid, exists. Compound exists. Now suppose if I speak in terms of stability. In tautomerism, what happens? Like basically, the concept of we say dynamic equilibrium, isn't it? Right. So in resonance in a molecule, what happens? It lowers the energy and it stabilizes the compound. But no such effect is seen in tautomerism, right? What are we saying? In resonance, or when molecule shows resonance, what will happen? Resonance lowers energy. So when the energy is lowered, what will happen? Stability of the compound the resonance lowers energy. So what will happen? Stability of the compound increases. When the stability of the compound increases, what will happen? The reactivity decreases. Okay, now no such effect is observed, isn't it? It is only transfer, and one is the keto form, one is the enol form. So no effect or no such effect is observed. Well done, students. Yes. Now let us see last criteria. So occurrence. So resonance occurs. Where does it occur? Resonance occurs in planar molecules. Correct? In planar molecules. What happens? But atoms of tautomers, they may remain in different planes as well. Correct? Atoms of tautomers may remain in different planes. Different planes. Last one. So representation. How do I represent tautomers? Tautomers are indicated by double arrow. Indicated by double arrow. That means they are indicated by like this. Between two isomers. But when it comes to resonance, it is indicated by single or you say double-headed single arrow. Double-headed single arrow. Here it is double arrow, here it is double headed single arrow, that is this one. But here it is between two isomers. Here it is between the canalical or resonating structures. Okay, so double arrow between two isomers. Double-sided arrow between canonical structures. Right, so these are the differences, students. So thank you for watching. I'll meet you again in the next video. Very important, reaction intermediates. Thank you. Welcome back, students, to one more session of your GOC chapter. So till now we've been dealing with different topics like inductive effect, hyperconjugation, metamerism also I've taught as a part of isomerism, tautomerism. Then I've also taught you the concept of electromagnetic effect. Now in this video we'll be learning about the concept of resonance, right? So resonance, particularly whenever you're learning a particular concept, you have to be very clear about the definition. You need to be clear about the rules for writing the resonance. You need to be clear about the types of resonance as well as resonance energy, right? So before we go into the concept, let's first start with the thing. What is that? That is called definition of resonance, right? So basically, whenever I speak about resonance is, it is a process, just like inductive effect, hyperconjugation, which we have seen. First we will start. It is a process. Okay, let us first write, then understand. It is a process. Okay, what are we doing in this process? We are just taking in which a single compound is considered to be a hybrid of two or more canonical structures. Okay, this is one more word which I have introduced. What are we trying to tell? It is a process in which a single compound is considered to be a hybrid of two or more canonical structures. Means we are going to consider one compound where that undergoes delocalization of pi electrons, and finally we show a resonance hybrid also. This whole process is called resonance. Okay, now we'll also see what are canonical structures. So during this process, what is happening? Most important thing is there is, as I said just now, delocalization of pi electron happens here. So remember, whenever your teacher, if you don't remember this paragraph, you can write delocalization of pi electrons. So that is what happens in resonance. Done. So now what are canonical structures we will see. So we have written the first definition. Now let us come back and write what is canonical structures. So canonical structures, the other name given to canonical structures, we can call the canonical structures as contributing structures. We can write like that, contributing structures. You can also call canonical structures as resonating structures. So this is what is your canonical structure, resonating structures. So basically, what are these, right? So what happens is, like, I have a molecule. Let us assume I have a molecule. I have to explain the different properties of the molecule. When I can't represent all the properties of the molecule, what do? I can what that particular molecule I need to understand. Okay, I'll again come back. So when all the properties of the molecule cannot be explained by a single structure, then what do? I start drawing many structures of that. Those many structures are called canonical structures. Once again, when whatever molecule I have to study, suppose I need to explain the properties. If I'm not able to explain with single structure, I'll try to draw different structures and finally explain the properties. Such structures are called canonical structures. So what are we going to write? What are canonical structures? When all the properties of a molecule cannot be explained by what? By a single structure. Then what do? I start representing the molecule. Okay, single structure, then such molecule is shown by many structures. Okay, many structures. So those many structures are called canonical structures. Hope this is clear. Done. So now I'll be taking you into examples, or how to draw resonating structures, or how to draw the canonical structures. But before we draw the examples, always remember you need to add some more important concepts based on this. What are they? Definition I have learned. I've learned the meaning of canonical structures. Now I'll be will be knowing about how or what are the different characteristics. Whenever you have to draw, what are the different characteristics you have to remember while drawing canonical structures or resonating structures. Right. So before we have learned the definition, we have learned what is meant by canonical structures. Now let us write the characteristics of canonical structures. Right. So basically the canonical structures, they have difference in electron distribution only. That is the only thing. Right. First important, canonical structures have difference in electron distribution. Let me finish off the characteristics. I'll show you with an example also. Electronic distribution only. Right. So whenever you're drawing a canonical structures, how are we going to show? The canonical structures are shown by, I'm writing canonical structures as CS. Okay, so canonical structures are linked or denoted or shown. Okay, that is right, or shown by a double-sided arrow like this. So one canonical structure is linked to the other by double-sided arrow. Then, so in the canonical structures, the important thing is they should be planar or nearly planar. Okay, canonical structures should be planar or nearly planar. These are all the characteristics, right? And important thing is, whenever you're drawing canonical structures, remember total number of paid and unpaid electrons are also same in canonical structures. That is also important thing which you should remember. Okay, yes, total number of paid and unpaid UN. Okay, unpaid electrons are same in canonical structures in CS. Right, fine. Next, the position and arrangement of atoms are same. Means when you're varying, the position and arrangement of atoms should be there in that molecule only. Let us write the fifth point. Position and arrangement of atoms are same in canonical structures. Okay, now we have written so much, isn't it? Let's see what did I write and how should we relate with an example. Right, so first, suppose if I take an example, what are we going to do in the example? Right, let me take this CH2 double bond CH single bond CH double bond CH2. What is this one? This is called, first let us count, 1 2 3 4 but. In which position do we have double bond? In first and third position. So this is 1,3-butadiene, correct? Yes, diene. 1,3 means first position, third position there is double bond present. Done. So here I have to draw canonical structures for this. Now I said they're going to be denoted by or represented by the double-sided arrow, isn't it? Yes, when you denote with the double-sided arrow, what's going to happen here? Just see, the first, this double bond, this one is going to shift. Okay, yes, this double bond is going to shift here. Fine, and this double bond is going to shift here. So how does this look when this is when a bond is broken here? What happens to this? This attains a partially positive charge. Okay, single bond CH, double bond has shifted here. This becomes CH, and because this is bond, this attains a partial negative charge. Further, I can draw one more canonical structure to this. How can I draw? the other way. Now this will attain negative charge and this will attain positive charge. So this becomes CH2 means you're shifting, you're dropping this here, you're shifting this here. Then when you're shifting it here, this also becomes minus single bond CH, double bond CH, CH2. So this is your canonical structure. I told you, isn't it? Canonical structures have the electron distribution. First point right. Then denoted shown by double-sided arrow. That also is right. Then total number of paid and unpaid electrons are the same. Total number of paid and unpaid electrons are the same in all the three. Next we said position and arrangement of atoms are same in canonical structures. It is only represented in that molecule only, isn't it? Now let's take one more example and see. Suppose if I take this example, let me write it as example 2. Right. Suppose I have one more alkene. Alkene is compulsory. Now I am denoting it by Lewis dot. Now count 1, 2, 3, 4, 5, 6, 7, 8. Now I have to draw a canonical structure for this. Immediately put a double-sided arrow here. Okay. Yes. So now what happens? This electron shifts. This double bond shifts. What do we get now? I am going to get minus here. This becomes single bond CH and Cl has lost, so this attains a positive charge in this way. So this is how you're going to draw the canonical structures or resonating structures. Hope a student it's clear with the example. Right, and important thing is all of the structures must have proper Lewis structure. Whenever you're drawing, Lewis structure should be proper. Don't make it just like that. Properly you have to draw and then only rearrange it. Right. So next, what is the criteria for drawing the Lewis structure? What is the criteria for drawing resonance? So let us write criteria of resonance. When do we draw? Means what should we remember? What is important for showing a resonance, or which will show resonance to us? So basically, resonance changes bond length. Correct, right? So that means when I take benzene molecule, right, first let us write it changes bond length. What? Suppose if I take benzene, C double bond C, the bond length is 1.39 angstroms, and it is an intermediate. This value is an intermediate between C, which is equal to 1.54. and C double bond C, which is equal to 1.34 angstroms. Right? Yes. Next one, resonance energy. Next concept. Next concept which the resonance depends is resonance energy. Resonance energy. So what is this concept of resonance energy? Let's see. Right? So resonance energy, when I speak, it is a difference between the hybrid and the most stable canonical structure. What is that? Resonance energy is defined by, it is a difference in energy between hybrid and most stable canonical structures. Nickel structure. This is called resonance energy. Okay, right, fine. Suppose if I take benzene as an example, I am taking example as benzene. We very well know benzene shows delocalization of pi electron, so it's going to form a resonance hybrid. Correct, right? Finally, it shows all the canonical structures and then forms a resonance hybrid. So I said the difference in energy between hybrid and most stable canonical structures, I said. Now let us draw one graph related to this. What is this? This shows on the y-axis I'm going to take resonance energy of benzene. Resonance energy of benzene. Done. Yes. On the y-axis I'm going to take total energetic structure. This one would be total energetic structure. Okay, energetic structure. I'm not writing the full form, right? So I said benzene shows resonance. Correct? It shows different canonical structures. Now let me draw one of the structure of benzene that represented by the pi electrons. This is one canonical structure. Okay, and here one more I'm drawing. Right? So this is a most stable structure of this. Okay, yes. Now here you have other canonical structures, other canonical structures. Okay, now what is the difference between this one and this one? The difference here is between, I told you the energy difference between the hybrid and the most stable canonical structures. Most stable canonical structures and the hybrid, that is, here it is 36 kilocalories. So this is called resonance energy. The resonance energy is the difference between the hybrid and the most stable canonical structures. So this resonance energy, means the concept or the criteria is, the first one, it depends change in bond length. Next should be resonance energy. Now, what is important thing which you remember? Always remember important concept about resonance energy. The first very important thing here, important thing is resonance energy is directly related to number of canonical structures. Number of canonical structures. First point. Next, resonance energy is directly proportional to stability. Second important thing you have to remember. Resonance energy, see, I said directly related means it will be inversely related to reactivity, isn't it? Resonance energy inversely related to reactivity. Right? Next, resonance energy is equal to expected heat of hydration minus actual heat of, not hydration, hydrogenation, I'm sorry, actual heat of hydrogenation. Okay, this concept is explained in hydrogenation is addition of hydrogen, isn't it? Yes. So these are the factors on which the resonance energy depends. Now, so next important thing, what will happen when what is the use of resonance in benzene? I told you resonance is directly related to stability, isn't it? Right? So because of the resonance, benzene is quite stable. And what does it do? It gives us a lot of electrophilic substitution reaction, isn't it? Where we show I've also shown you the mechanisms of electrophilic substitution reactions. Different types of electrophilic substitution reaction benzene shows due to resonance only. Right? Fine. So next important criteria I have studied. I have studied about the definition. I have taken an example. Correct? Now, what is the next important thing? Let us show the order of stability of different canonical structures. Right? So before I go into that, let us see the types of resonance and come back to that topic so it's clear. Types of resonance. So basically, resonance is of two types. One is isovalent resonance, and the next one is heterovalent resonance. Isovalent resonance and heterovalent resonance. So isovalent resonance means same number. When same number of bonds and same type of charges are present, then it is called isovalent. What is that? Isovalent is when same number of bonds and same type of charges are present. This is isovalent resonance. Suppose if I have to take hetero, my line is not straight, I'm sorry for that, students. When I take heterovalent, hetero means different, isn't it? Right. Iso means same number of bonds and same type of charges. But when it comes to heterovalent resonance, you have to remember different. Hetero means different. When different number of bonds, and charges are present. Okay, let me take the examples now. So in isovalent, when I take the example, I said same number of bonds and same number. Let us see here. SO2, NO2, CO3 minus 2. Isn't it? See here, all two bonds. Here, same type of charges, minus 2. Yes. Now let us come back to heterovalent. When I take heterovalent, best example is buta 1,3 diene and vinyl cyanide. Both are different. Charges are different and even the number of bonds also are different. Yes, so this is your type of resonance, students. Now let me come back and meet you with the different stability of different chemical structures, taking different examples. Welcome, students. So in the previous video, what did we learn? We have learned the concept of resonance. I have taught you what is the definition of chemical structures. I have also taught you why are we, like, what is the use or criteria for showing resonance. I also told you because of resonance only benzene is showing different electrophilic substitution reactions, right? Like sulfonation, Rayleigh-Crafts acylation, alkylation, nitration, all those. Fine. Now we're going to study about a concept called stability of different chemical structures. We will see the stability, what happens when I take a non-polar molecule or when I take a polar molecule. How is the stability? Right. Suppose if I take a non-polar structure, okay, non-polar structure is always more stable than polar structure. Remember that. First important thing, a non-polar structure is always more stable than a polar structure. Polar structure. Right. Let us see the order now. Right. This is a non-polar molecule. Correct. This is more stable than, see this, now this has become polar, isn't it? This is more stable than so remember, charges are apart, so this is less stable. Why is this is less? Okay, this is most stable, this is less stable. What is the reason here? Reason is charges are apart, so less stable. Right? Done. Suppose next thing, if I speak in terms of polar structures, okay, let us see the next one, next stability concept. In case of, I'm taking only in terms of polar structures. Polar structures. Yes. So remember here, greater the number of covalent bonds, greater will be the stability. Next important thing is greater the number of covalent bonds, greater will be the stability. Right? Yes, students, clear? Yes. Now let us take an example. I have two different one in this example. Let's see which is more stable. So I have CH3, C. This is one example. This is one example. Now see which has more covalent bond. This has more covalent bond, isn't it? Triple bond here. So greater the number of covalent bonds, more is the stability. That means in terms of stability, this is only 2. So this is less stable than the other one. Okay, right. Next one. Let's see one more. The chemical structure, in which each atom has octet state is more stable one. Okay, that means whichever chemical structure has more octet configuration, that will be the stable one. Okay, the chemical structure which has octet or 8 electrons will be more stable. That means, suppose if I take an example like this. Now count the number of electrons here. Here 1, 2, 3, 4, 5, 6, 7, 8. Total are how many? 8 electrons. Here 1, 2, 3, 4, 5, 6. Here 6 electrons. So which is more stable? This is whichever has 8 or octet configuration, that is more stable, I said. Let us take one more example and see. Here, next criteria. If I take an example of this, let me take an example and then explain you. N double bond N plus. Okay, 1, 2, 3, 4. Yes. Okay. This is in showing chemical structure of this. Let me first finish off and then come back to you, explain you what am I writing. Yes, this will become unstable N plus triple bond plus. 1, 2, 3, 4, 5. This is unstable. This is most stable. Okay, what do we write? Right. So if the same charges are closer, see here, this is plus, this is plus. If the same charges are closer, the structure will be unstable. If the charges are separated, okay, the charges are separated. See here, in this case, this is minus, correct? So the charges are separated, they are more stable. The charges are close by, they are unstable. So if same charges, write down, if same charges are closer, structure will be unstable. So remember all these things, right? Next important thing which you have to remember, right? So the chemical structure in which positive charge is on the positive atom and negative charge on the negative atom is more stable. That means, suppose, let us write first the canonical structure in which positive charge is on positive atom. Okay, what do we write here? Positive atom, and negative charge on negative atom is more stable. This is more stable. Okay, right. How do we write this? R, C, R. This is plus. Okay, this is minus. How well? One more. R, C, R. Okay. Now compare this. I say the canonical structure, both the canonical structures, okay, means here in this case, right, the positive charge on the positive atom, see here, carbon positive and negative charge on negative atom will be more stable. Okay, here in this case this is minus. So carbon 1s2, 2s2, 2p, 2. Right, so positive charge, if it is in the positive atom and negative charge in the negative atom, that is considered to be more stable. This is here, see here, it is reverse order. That's why this is more stable. So let us recollect once again. Whenever you're writing or stability order is, non-polar structures are always stable than polar structures. Point number 1. What is the next important thing? Greater the number of covalent bonds, greater will be the stability. What is the other one? If positive charge is present in the positive atom and negative on the negative, then again it is stable. Next important criteria, we said, if it has octet configuration or 8 electrons present in the structure, then the canonical structure is more stable. Next thing, we said, if the same charges are present, plus and plus, closer to each other, then it is unstable. It should be separated. Charge separation should be there. Then only it is stable in nature. So these are the stability order, students. Let me come back and meet you with the next topic, that is your mesomeric effect. So welcome back, students, to one more session of your general organic chemistry. Today's topic, we're going to learn the concept of mesomeric effect. In the previous video, I've taught you what is the concept of resonance and what is the stability order in terms of polar molecules and non-polar molecules. Please watch the earlier videos also. Right, till now I have covered different topics like hyperconjugation, inductive effect, electromeric effect, then tautomerism, metamerism, right, plus sign, inductive effect, plus sign, minus effect, like that. Then I've also taught you the differences between tautomerism and resonance. Right, now in today's topic we're going to learn about mesomeric effect. Right, so whenever you're learning a concept, I told you, first important thing, try to write the definition. If you know the definition, then you can follow it with the examples, types, and further you can also show the explanation in terms of a clear explanation in terms of taking an example. So whenever I speak about mesomeric effect, remember it involves complete transfer of pi electrons. Remember what is important, what the keywords, we will first write the definition. So mesomeric effect involves complete transfer of pi electrons or lone pair of electrons towards a more electronegative. Okay, electronegative means electron withdrawing, means it will try to drag the electron density towards an electronegative species. Now where is this all happening? In a conjugate system. This is important. So in the exam, whenever you're writing, remember keywords is it involves complete transfer. Which transfer? Pi electrons. Where? In a conjugate system. Right. So what are conjugate systems? Let's see. So let us write the heading. What are conjugate systems? Conjugate systems. Done? Yes. So conjugate system means, suppose if I take a benzene molecule, right? Example, say here, benzene. Okay, let me take one more. Let us write the name, benzene. One more example I am taking is vinyl chloride. One more example which I am taking is 1,3-butadiene. Okay, let me write the structures and explain. So vinyl chloride means CH2 double bond CHCl, isn't it? Now as soon as this is written, draw the Lewis dot 1, 2, 3, 4, 5, 6, 7, 8. Done? Yes. Now here butadiene. But means 4 carbons. 1, 2, 3, 4. First one and third one you have double bond. Correct? Now fill in the hydrogens. CH2, then CH2. For this is CH, this is CH. Now fill in the sigma bonds and pi bonds. Right? So this is a sigma pi bond. Now this is again sigma bond. Here sigma pi. Again you have sigma. Here sigma and pi. Correct? Now what are you finding here? Here there is alternate sigma bond and pi bond. See here, alternate sigma bond and pi bond. Alternate sigma bond and pi bond. Here also alternate sigma bond and pi bond. So wherever there is an alternate sigma and pi bonds, such systems are called conjugate systems. Remember that. Such are called conjugate systems. Alternate sigma and pi bonds, just like this, and like this. Those are called as conjugate systems. Done. So here, what happens in the systems? There will be shifting of pi electrons. When the pi electron shifts, what happens? They start giving, or shift, once they shifted, they give a permanent polarity on the chain. Okay, what did I say just now? Let's see. I said, if I take an example, first of all we said when there is alternate pi bond and a sigma bond, isn't it? And that too, they are in a conjugate system, means there should be alternate pi and sigma. What happens during the shift? I said it transfers or shifts to the more electronegative atom, we said. Suppose if there is no more electronegative atom concept, it's just shifting. What will happen during the shift? There is it starts giving permanent polarity. Let us write that. In such systems like conjugate systems, pi electrons shifting takes place. What does it do? Giving a permanent polarity on the chain. Right. Suppose if I take benzene, okay, see, this is one structure of benzene. This is it shows canonical structures in this direction. Let us take one more. Let us take one more example of butadiene. That is 1,3-butadiene. Example 1, example 2. So CH2 double bond CH, single bond CH, double bond CH. So in the first case, what happens? There is shift of double bond here. Next, this also shifts during this process. What happens? This is losing, this attains, CH2 becomes the first case plus single CH, double bond CH, single bond CH2 minus. Correct? Fine? Right. So here, what are you observing? It can be the other way also. This falls here, this jumps, and finally this also may have the negative charge, isn't it? Let us see that also. This drops here, this bond shifts here, this also. So this becomes H2 minus CH, double bond H. Correct? Now, what are you finding? The terminal carbon, whatever is there, is positive in nature. Remember, this is what is important. So it gives permanent polarity inside. So whenever it shows mesomeric effect, the terminal carbon, whatever is there, the terminal carbon is positive. Is positive in mesomeric effect. Remember that. Suppose if I have to speak in terms of mesomeric effect and inductive effect, what is the difference? If somebody asks you, what is the difference in between mesomeric effect and inductive effect, you can directly tell this. Mesomeric effect and inductive effect. So mesomeric effect, what did we see? We seen, let me represent, I've taken an example, directly that earlier example I have taken, right. So here, this is what we have seen in the earlier example for 1,3-butadiene. Here, no effect of charge intensity, means the charge intensity is the same. There are 4 carbons, isn't it? 1, 2, 3, 4. No effect on charge intensity is seen, whether they shift this direction or whether they shift in that direction is seen. So it will be the same at C2 and C4. Or you can write it as C1 and C4. C1 and C4. So it will be the same. No effect. It's just shifting. You're either shifting this direction or shifting that direction. But when it comes to inductive effect, what happens? If the chain is longer like this, it goes on and like this. There is an X atom. I said towards the more electronegative atom it drags, isn't it? So this becomes, when it drags in this way. So this is 1, this is 2, this is 3, this is 4. It becomes partial negative, partial positive. Correct? So now in this case, what happens? As we move away from the halogen atom, inductive effect decreases. And what are you observing? You're observing that charge intensity also decreases. Here it remains the same. No charge, no effect on charge intensity. Here it is the same. Charge intensity decreases. This is what you're going to tell when somebody asks you what is the difference between mesomeric and this. This is only transfer here, but here there is charge intensity decreasing. Right? Now, next, let's come back and meet in the next video. That is your types of mesomeric effect, or means types of mesomeric groups, that is minus M effect or minus M affecting groups and plus M affecting group. And also I'll also explain you how the mesomeric effect, how will it explain the effect of mesomeric effect on aryl carbocation, carbanion, basic nature of aromatic amines, and acidic nature of phenols. Thank you for watching, students. So welcome back students to one more session of your general organic chemistry. So in the previous video I've taught you what is the concept of mesomeric effect. That means what did we learn? We said it is a complete transfer of pi electrons, or you're going to transfer a lone pair of electrons. Where are we going to transfer? We're going to transfer towards an electronegative atom. That is what we have learned. Today in this video we are going to learn the types of mesomeric effect. So basically we have two types of mesomeric effect. One is plus M effect and one is minus M effect. Let us divide the page into two equal halves. Right. So plus M effect in groups and minus M effect in groups. Done. So in plus M effect, what is going to happen? The electrons are transferred towards the conjugated systems. By whom? By electron releasing groups. Once again, I said there is complete transfer, but here important, in plus M effect, electrons are transferred towards the conjugate system, where there is what are conjugate systems? This is alternate sigma and pi bond, isn't it? Towards the conjugate system by electron releasing groups. Okay, those are called as plus R groups or plus M groups. Okay, what are the examples? Means here electrons will be transferring towards the conjugate systems. Which one will do this work? Electron releasing groups will do this work. Right? Right. For example, alkyl groups are electron releasing. NH2 electron releasing, OH electron releasing, NHR are electron releasing, NR2 electron releasing, and OR electron releasing. Okay, right? Fine. So these particular thing, all these examples, electron releasing group. I'll be showing you with an example, then you'll understand. And you know, whenever these groups are present, the central atom, whatever is there, has a lone pair of electrons to donate. That is what it donates. That's the reason it keeps donating. And whenever there is a plus M effect or plus M or electron releasing groups, what are where will they direct? They are always ortho and para directing groups. All these are ortho and para directing groups. Remember this. So when they are ortho and para directing group, what will happen? It will increase the stability of the molecule. Increases the stability of the molecule. Remember that. Now when I come back to minus M effect, here it is different. Electrons are attracted from the conjugate systems to the electron withdrawing group. Here what do we say? Electrons are transferred towards the conjugate system. I said towards. Now this is away from the conjugate systems. Let us write that. Electrons are attracted from conjugate systems. Which was attracting? By electron withdrawing groups. Electron withdrawing groups. This is electron releasing groups. This is electron withdrawing group. What are the examples? So these are called as minus M groups. Examples. What are the different examples? OR2 plus cyano, CX3, COOR, SO3H, NO2. All these are electron withdrawing group. All these groups are meta-directing groups. Meta-directing groups. So when it is meta-directing, what will happen to the stability? Stability automatically reduces, isn't it? The stability decreases. When such groups are present, they reduce the stability of the particular. So that's why we call this minus M effect. Right. Let's see. Now I said plus M effect and minus M effect. Let us take an example and explain. So when such groups, let me take one example with R. So what am I showing? I'm showing you plus M effect first. I told you example. Here I'm going to take an alkyl group. So I'm going to take a benzene ring and I'm going to show you with CH3. Now CH3 is an alkyl group and this is called toluene. So when such groups are attached to benzene ring, these are our plus M effect groups. What will do? They will increase the electrophilic substitution. Right? What are they doing? They are ring activating groups. They will because they keep donating the electrons, isn't it? They're ring activating. Which direction they activate? Ortho and para directing. Right? So they start increasing the electron density at this position. Let us see certain listen the resonance of this by drawing the chemical structures. Let's start. How do they do? First, in the first step, this bond is going to shift here. Okay, let me take in the other way. Let me not take like this. Let me take in this way so that it's easy for you. Okay, let me not do this. Leave this one. Okay, I'm sorry. Let me strike this off and come back again. Right. So, let me not confuse you all first. Benzene ring. I'll draw in this direction. CH. Okay, now this is right, isn't it? Right. In the first step, this bond shifts. Double and double can't be together. So this pi bond shifts here. So draw the canonical structure. How does this look? This one, this bond is going to shift. The electron density shifts here. At ortho position, you get minus. Fine, done. So here, let me finish off this. This has become double bond because the pi bond, sigma bond has shifted here. Hydrogen, and this is plus. Now in the second step, the electron density, now see here, you're creating a site for the electrophile to come and join here. Yes, because the electron density is more. Now this bond is going to shift here and this bond shifts here. So what do you get? You get minus minus double bond C H H H. Now one more. This bond is going to shift here and this bond will shift here. This minus. Now see here. Now what's happening? These are all electron releasing groups or plus M effect groups. So whenever they are attached to the benzene ring, what will they do? They are creating, means there's a site for the electrophile, electron deficient. You're creating means the electron, because they're releasing electrons, and electron density, more of electron density is observed at the ortho position and para position. So that's why whenever electrophile comes and attacks at the ortho position, electrophile comes and attacks at the para position. That's why they are, what are they? They are ortho para directing groups. Ortho para directing groups. So whenever there are ortho para directing groups, what will happen to the stability? I said stability automatically increases. Correct? Right. Now let us come back and see minus M effect groups now. So minus M affecting groups. So we've already seen minus M affecting groups. What are they like? Cyano group, CX3, like the halogen, if the halogen is present. Correct? Let me take an example with CX3 and C. I have a benzene ring, pi electrons, and now I have an minus N group, that is electron withdrawing group with 3 halogens. Okay, right. So done. So first important thing, whenever I have minus M effect, that means electron withdrawing group means the more electronegative atom starts withdrawing electrons towards it. When this is withdrawing the electrons, this bond starts shifting because it tries to drag the electrons towards itself. Right. What do we get? We get a benzene ring like this. This bond is shifted, becomes double bond. Now this is C, X, X, and this is a negative charge. Now further, denoted by the double-sided arrow. The next step. What happened here? The bond is shifted, so this becomes plus, isn't it? Now this bond is going to shift here because this has become deficient. So what do I get? I'm going to get this way, double bonded systems, conjugate systems we said, isn't it? This becomes X minus. So now the bond has shifted, so this attains a partial positive charge. Not partially positive charge. Then to satisfy this bond shifts here. Now here there's a site created, so this becomes positive. Right. So when such groups are attached, what do? They decrease the electrophilic substitution, that is, they are ring deactivating. Okay, ring activating and meta-directing groups, they're also meta-directing. What do? Because of this, they reduce they decrease electron density to ortho and para positions. See here, ortho and para position, the electron density or electron distance is less. What will happen? In ortho and para positions, there is electron density, means the electron cloud formation is less. Where will the sun go? Automatically it will direct it to meta position here. When it is directing it to meta position, what will happen? Meta position, it will destabilize the ring. Correct? Yes. So this is what is a concept. These are meta directing. Minus effect to M effect means meta directing groups, which will reduce the stability. Reduce the stability. Right. So thank you for watching, students. I'll come back with the next topic in my next video. Welcome, students, to one more session of your general organic chemistry. So till now we have done a lot of different concepts. I taught you what are the different electron displacement forms, that is your inductive effect, hyperconjugation, electromeric effect, mesomeric effect. That also I've taught you, plus M, minus M. In inductive effect I've taught plus I, minus I group. Like that I've covered all the topics. After that I've taught you a topic, that is metamerism, tautomerism. I also have taught you the concept of hydrogen bonding in the previous video. So the last video which I discussed was hydrogen bonding and the effects of hydrogen bonding, or the important questions on hydrogen bonding. Now in today's topic we are going to discuss the next topic, that is reaction intermediates. Done. So after the electron displacement effects, let's directly come to this, that is reaction intermediates. So basically whenever you're studying in chemistry, there are different reaction intermediates which are formed. When you perform a reaction, different intermediates are formed. What are they? Let us list out. So we have a reaction intermediate called carbocation, which is formed. Carbocation, right? This is denoted by the positive charge. Done? Yes. So we have one more class of reaction intermediates. Those are called as carbanions. Okay, right? It is denoted by the negative charge. We have one more category called intermediate called free radicals, which are formed. We denote free radicals by a dot. That also I'll show you. Right. After free radicals, one more category which is formed as in reaction intermediate are called carbenes. Done. After carbenes, there is one more category which are formed are called nitrines. Done? Yes. For all of these, we'll be studying the preparations, we'll be studying the structures, we'll be seeing how are these formed, like in which name reactions these are formed. All the information I'll be giving you. Right. So first important thing, let us start with the preparations of these reaction intermediates. Now, so when I start with the first preparation, right, let us write the heading, preparation of first carbocations. I'll be taking how are these prepared or how are these formed, during which reaction these are formed. So basically when I take the preparation of carbocation, I can prepare, or we can see the formation of carbocation in simple thing, that is heterolytic fission. That is the first important reaction where I can show you the formation of carbocation, right? Heterolytic fission. Okay, so hetero, we have basically two types of fissions, isn't it? Fission means breakage. Homo means two equal halves. Hetero means two different, means two equal halves. Both the atoms will be similar. In heterolytic, both the atoms will be different. Right. So suppose if I have to form the carbocation, I said carbocation is denoted by what? It is denoted like this, C plus. That. So this is be linked, right? So this is your positive charge. First in heterolytic fission, I said, for example, if I take, now I have, see here, now it is heterolytic because two atoms are different. Homo means both will be similar, hetero means two will be different. Right. Now when there's a fission happening here, right, so there is a pair, I'm denoting the electron pair like this, one by dot, one by cross. So when there is a cleavage in this direction, what happens? This halogen, whatever is there, is highly electronegative, it will try to drag the electron density towards itself. When it drags, what will happen? It will break up into two equal halves. One X, that is, which is electronegative, is going to take or pull up the shared pair of electron, and the left out carbocation is going to form. This is how the carbocation is formed. Now, if I have to see the next formation, I can show you protonation of alkenes. So, alkenes, when they are protonated, when an H plus protonation of alkenes. So, what is protonation? Protonation means, okay, let me draw the slide. Protonation means addition of a proton. H plus. We are adding H plus to this for an alkene. When I add H plus to the alkene, how does it form? Let us see. Now I am taking an alkene, double bonded around carbon 4. Here to this I am adding a proton. When I add a proton, what will happen? There is a cleavage of this bond, isn't it? Yeah, the bond. And what is it? How does it look? There is here, right? So this proton, this particular bond is broken and it is pulled out by this. So part of this is broken. One is shared by this carbon, one is shared by this carbon. So this proton comes and attacks this carbon. So it becomes C plus single bond is formed, H and H. See here, there is a carbocation formation, yes or no? Yes. Now let's see one more. Now we'll see again the formation or the preparation of carbocation from alcohols. It's the same concept again. It is also same protonation. Let us take protonation, as I said, it is addition of H plus. So protonation of alcohols. Done. So again I'll be adding H plus only to alcohols. In the earlier case I have added to alkenes. Now I'll be adding to alcohols. So alcohols, let me take ROH is an alcohol. Now I'll be protonating this to, that means I'll be adding. Once I add, what will happen? You have this also as a mechanism in NCERT, hydration of alcohols. That is, no, hydration means their protonation step will also come during adding that H plus ion, right? So it's an NCERT question. See the mechanism. Now, first thing, during protonation, when I'm adding this, right, just see here, this proton is going to go and adding to this particular oxygen. It's protonating. How does this look? This is your R, this is your oxygen, lone pair of electron, plus, because one bond is shared by this, one is hydrogen, one more is hydrogen. Further, what's going to happen here? See here, when I say R, that's nothing but alkyl group, isn't it? Yeah, there is a cleavage of the bond here, like this. Water molecule comes out, and what is formed now? Yeah, see here. You see here R CH2 means there is one group already there. So I'm showing that as R CH2. Okay, that is plus. Done. So this is how is a formation of a carbocation, a preparation of carbocation. This is the first step, this is the second step, this is the third step. Now let's come back and see the preparations of your carbanions. So let us write, we'll be learning preparations of carbanion, the next reaction intermediate. Carbanion or carbonium ion. Right. So here the carbanion, it is denoted by what? It is denoted by C minus. This is again right. Fine. So in carbanion formation, the simplest method, again I'll be taking heterolytic fission only. Heterolytic fission. This is the same thing which we have used for carbonium ion. Suppose, which one heterolytic fission? I'm going to show you the heterolytic fission of alkenes. Okay, I'll be taking alkenes and doing it. Suppose if I take an alkane, that is your methyl. So here, what's going to happen here? There's a lone pair. Okay, one denoted by dot, one is denoted by X. But here, the alkene I said, one more hydrogen is here. So what's going to happen? When there is a fission, heterolytic means two different. When there is a fission here, observe carefully, this pair of electron is pulled up by this methyl group. When it's pulling up, it's getting excess, isn't it? It's becoming CH3 minus. One pair of electron is pulled up by this, and the leftover is proton. Fine, right? So this is how it's forming. This is the way we are going to prepare carbanions. This is how, because one electron pair, this pair of electron is pulled up by the methyl group, means it is shared by, it's pulled by this. I should not say shared, it is pulled by this. So when this is pulled by this, what will be left out? It is excess of electrons here, and the leftover H plus is here. Done. Now let's see the preparations of free radicals on the next page, and the big full page. So when I have to speak about the third reaction intermediate, so preparation of free radicals. So when I have to speak about free radicals are very short-lived species, very short-lived. Again, here I'll be showing free radical formation. We have different examples. Just specifically I've picked a few only. Here I'll be speaking about the formation of free radicals in homolytic fission. Homolytic means what? As I said, homo means between two similar atoms. Suppose if I have an element, means a particular atom like this. Both are homo. Okay, simple, the same thing. Now, suppose if I have a specific example. See here, Br and Br or Cl and Cl. Okay, both are similar. Now suppose when this is exposed to sunlight, okay, this is broken up into free radicals 1 and 1. It's the same with Br also. It's the same with Cl also. Suppose if I introduce, but important thing is it occurs in the presence of sunlight. So when it occurs, there's a cleavage of the bond and it forms chlorine free radical and one more chlorine free radical. Let us take one more example. Suppose if I take a long chain alkane like this. Suppose if this is exposed to H nu light, right? So there is, what does it do? In the presence of sunlight, homolytic fission occurs. Yeah, and what is it going to form? It's going to form free radicals, two different free radicals. Where? Just see here. First important thing, I'm taking it here. CH3, CH free radical, CH3 plus H plus. See, this is how the free radical is formed. Now, let us see the formation of free radical by one more method. What is that method? Let's see. There is a process called thermolysis. Hope you would have seen that thermolysis process. Thermo means in the presence of heat, because I said free radicals are formed only in the presence of heat. Thermolysis means lysing a molecule, an organic molecule in the presence of heat. That is thermolysis. So in thermolysis, what are we going to do? We are going to take an organic molecule. I am preparing free radicals now, right? So I am going to take an organic molecule. What will I do? I will introduce this to high temperatures. So when I introduce or take this organic molecule high temperature in gas phase, I'm going to take this high temperature and a gas phase. What's going to happen? Free radicals are going to form. Let us see, taking one example. Right. Suppose I have, just see here, PH, C double bond O, H. Now I'm heating this. Now this is a peroxide, isn't it? Now I'm heating it high temperature, that is almost 80 degrees to 100 degrees centigrade. When I heat this, what will happen? There is a lyse, it means there's, see, this means a thermolysis. Thermolysis, we are lysing using temperature, high temperature or heat. This particular molecule I'm going to cleave. Where will it cleave? Exactly, this is a peroxide, you need to hold, and exactly it's going to cleave here in between oxygen. When it cleaves, this is one molecule, this is one molecule. Together I'll be writing as 2. So copy the same thing, it is PH, C, double bond O, oxygen. Correct? Yes. So now what's going to happen? This bond, whatever is there, okay, this particular thing is going to shift. When this shifts here, what is going to happen? This also shifts, and finally what do I get? There is a cleavage of the bond here and 2 phenyl free radicals are formed and carbon dioxide is out. So here this is the we try to prepare one free radical using the thermolysis. See here I've used. So what will happen? Because why is this cleaving? Because the bond energy of oxygen, whatever bond energy of oxygen is there, that is, very small. That is only 30 kilocalories per mole. That's why there is a cleavage at peroxide. If somebody asks you why at peroxide only, then why it is not cleaving somewhere here, you can say since bond enthalpy of oxygen, how much is it? It is only 30 kilocalories per mole. That's why we are cleaving it here. This is how your free radicals are prepared. Now let's come back and see the preparation of carbenes, the next reaction intermediate, preparation of carbenes. Right. So carbenes basically are denoted by C. This is how you represent your carbene. How will I prepare? Here I am going to prepare carbene from haloform reaction. Haloform. Okay, so what is halo form? It is nothing but CHX3. I am not specifically saying if I take iodine, it will become iodoform. In case of X3, if I take iodine, it will become iodoform. But here it is called halo form. This halo form reaction, what are we going to introduce? We have to introduce alcoholic KOH, isn't it? So when I introduce alcoholic KOH, there is a cleavage of this. And what will come out? Hydrogen is out and CX3 minus. Further, this gets converted to CX2, the same thing, plus X minus. So now this, this is your halo, this is your carbene. Now it is with halogen, isn't it? So we call this as halocarbene. Halocarbene. This is how the carbenes are prepared. Now let's come back and prepare nitrines, the last class of reaction intermediates, that is preparation of nitrines. Nitrines basically are denoted by, like if I have to specifically say, I am taking with an alkyl group, nitrines. This is how you are going to show. How will I prepare this? I can prepare nitrine in the presence of light. How does it do? Let us take one first example. I'm going to take an alkyl group, that is nothing but RN3. So I'm writing it here in this way. Okay, RN3. This is when introduced in the presence of H nu, when in the presence of a photon. What will happen? There is a cleavage. This bond is broken. Yeah, here exactly. There's exactly cleavage, and what will happen? This nitrogen comes out in the form of a triple bond, and the leftover are N 1, 2, 3, 4, 5, and 6. Right. So this is where it's called, or this is how the nitrine is formed. Done. Fine. So further, let's see one more. I can also prepare nitrine from, taking a different example, that is called diazomethane. What is diazomethane? Let's see. From diazomethane. What is diazomethane? Diazo means N. Azo is nothing but nitrogen. N triple, okay, in double bond, because I'm linking this with CH2. CH2. This is plus, this is minus. When you're introducing this diazomethane, because we have written this diazomethane, we are introducing the presence of sunlight. First important thing, this nitrogen. Right, okay, I think little bit this one I did, okay. Where will it cleave? The nitrogen part, we are taking diazomethane, that's fine. But here, what is it cleaving? It's cleaving here at this point, N2. But important thing, we are forming a carbene here. Just see here. This is what is a small thing change. Here we are trying to prepare carbene. Let's see. This particular thing, reaction. Here halo form and one is carbene. I've explained here. Only nitrine I've explained one reaction. Here we are trying to prepare carbenes. I'm sorry for that. Just note it, carbene. This is nitrine. So these are the different preparations, students. Let me see what have I taught you. First thing I have taught you, let me take one after the other. I have taught you the preparation of carbocation. Then I have taught you, first one we have discussed what are the different reaction intermediates. Then we have seen the preparation of carbocation. After reaction of carbocation, then I have taught you the preparation of carbanions, isn't it? Right? So we have seen the preparation of carbanions. This is the preparation. After carbanions, I have taught you the preparation of next one, that is free radicals. In free radicals, we have studied two preparations. One is homolytic fission and one more is thermolysis. After thermolysis, gradually, I taught you the preparation of carbenes. So this is one preparation of carbene and the second preparation is this. This is the second preparation. Then the last reaction intermediate, that is nitrene. I have prepared nitrene. I've shown you here. This is the preparation for nitrene. So this is done. We are done with the preparations of reaction intermediates. I'll meet you again in the next video with the structure of the reaction intermediate, students. Thank you for watching. So welcome back students, to one more session of your isomerism topic, right? So in previous video, what did we watch? We have seen the first type of isomerism, that is structural isomerism. In that we have seen chain isomerism, position isomerism, functional isomerism, metamerism and tautomerism. I've already taught. Please watch, just check in the playlist which is already kept. Right. So now in today's video we'll be watching about geometrical isomerism as well as optical isomerism, which is a part of stereoisomerism. Done. So now I have to speak about geometrical, as the name suggests, right? Nothing, like it's simple basically. Here, in this type of isomerism, what will happen? We'll be basically studying about a double bond. Means here we'll be speaking in terms of double bond and the arrangement of atoms around the double bond. So here, these particular isomers have same structural formula. But in which respect we are speaking? We are speaking in terms of a double bond, and there will be an arrangement or there will be a difference in arrangement of atoms of groups around the double bond. Okay, this isomerism exists basically in arrangement of atoms or difference in arrangement of atoms around the double bond. Correct? So basically geometrical isomerism is of two types. One is cis isomerism, one is transform, or it can be studied as cis form and transform. Cis means on the same side, trans means opposite side. Remember, same side. Trans means opposite side. Let us take certain examples and see. Suppose I have a double bond like this. Around this, 4, done. In case of cis form, let me take AA, same side, BB, same side. So this is cis. Suppose I have to do trans, again double bond, 1, 2, 3, 4. AA an opposite side, BB an opposite side. So this is transform. Yes, you can write the same with X, Y, anything. You can take any other group. Suppose if I take an example for the geometrical isomers, the same thing. I'll be taking with an example called as cis butene. One isomer. Here I'll be taking trans butene. I told you, no, double bond we have to take. So but 1, 2. Okay, done. 4 bonds. But means 4 carbons. Cis means same side. CH3, CH3. So remaining hydrogen for this, hydrogen for this. So cis butene. Both the groups means these AA is CH3, CH3. BB is hydrogen, hydrogen. Now it trans, when I take trans case, 1, 2, 3, 4. One CH3 is here. The opposite one will be CH3 here. Hydrogen is here, one more hydrogen. So the opposite sides is trans. So this is your geometrical isomerism. So only difference is here you have to remember. In geometrical isomerism is shown by alkenes, and there is different in arrangement of atoms. Right? So which type will show geometrical isomerism? Which have a type of, means the compounds having the molecular formula ABC is equal to CXY, or a simpler structure, a compound having ABC is equal to CAB. Such type will occur in two forms and they exhibit geometrical isomers. So this is what is important. Remember this. So if you remember this, if you are in the exam, if they give you ABC and CXY as well as ABC and CAB. Right. So let me come back and meet you all with optical isomerism. Thank you for watching, students. Right. So welcome back, students. So here we've already learned about geometrical isomerism. In today's session we'll be seeing what are we going to learn in optical isomerism. So little bit, important, it's difficult topic for most of the students, but it's easy. Let me try to make it easier for you all. So whenever you're learning optical isomerism, the different concepts which you have to study for the exam, remember you need to study about the different concepts. Let us see first what are the concepts I'll be teaching. I'll be teaching you basically the definition of optical isomer. Definition of optical isomer. After that, I'll be also teaching you what is optical isomerism, or okay, I'll tell you what is meant by optical activity. Optical activity. After that, I'll be teaching you the difference, or the concept of optical isomerism. Concept of optical isomerism. I'll be teaching you what is meant by specific rotation. I'll be teaching you about what is meant by chiral carbon. I'll be teaching about elements of symmetry in this. Elements of symmetry. So in elements of symmetry you have what? You have plane of symmetry and you have center of inversion. Then you have alternating axis of symmetry. Alternating axis of symmetry. Axis of symmetry. I'll also be teaching you all about apart from these topics, I'll be teaching you about the concept or examples of enantiomers. I'll be teaching you about diastereomers. I'll also be teaching about racemic mixtures. I'll be teaching you about resolution. I'll also be teaching about racemization. Right, so I already did one video how to calculate the possible stereoisomers. Okay, let me take one example. How I'll be teaching you how to calculate possible stereoisomers in compounds. Stereoisomers in compounds. So I'll be dealing with all these topics gradually, one after the other. I'll be also teaching you about the different RNS systems, DL and L systems also. Right. Thank you for watching, students. Let us meet again with a clear explanation of the different concepts of optical activity or optical isomerism. So welcome, students. So in last video we have studied about the reaction intermediates. We have seen its preparations, we have seen its structures, then we have seen the different questions based on reaction intermediates. So as I'm doing the different JEE NEET series, I'll be doing different questions based on GOC. Please be a part of that and keep watching it. Now in today's class we'll be studying about the isomerism concept. So now I've come to GOC 1, so I'll be gradually doing all the concepts. So whenever I speak about isomerism, what is isomerism? It is the study of organic chemistry. Means basically here iso means same, similar. Merism means unit. Merism means the study of that. So isos means equal. Meros means parts. Let us write that. Isomerism in this. Isos means equal. This particular thing. Meros. Meros means parts. Let us see this. So in isomerism, when I have to speak, there are a particular classification. First we will learn that, then come back to the examples. So isomerism is basically studied under two headings. One is structural isomerism and one more is stereoisomerism. Okay, right. So again, structural isomerism, we have different categories, that is chain isomerism. It is also called as nuclear isomerism. We'll be learning about position isomerism or positional isomerism. We'll be studying about functional isomerism. We'll be studying about metamerism, which I already did. Metamerism I already discussed. Please watch. Tautomerism also. Stereoisomerism is again studied under two categories, that is geometrical isomerism, where we'll be studying what cis and trans isomers, and we'll be studying about optical isomerism also. Optical, where I'll be teaching about enantiomers, diastereomers, R and L systems. I'll be teaching about all. So I'll be clearly explaining what is optical isomerism, taking different examples. So when I go with the first one, let's start with the first one, that is chain isomerism. So simple it is, nothing much big. Let's write chain, or it is also called as nuclear isomerism. Nuclear isomerism. So what are we going to see? Let's see an example and then understand. So the other name, if I have to say chain, it is also called chain isomerism, nuclear isomerism, or it is also called as skeletal isomerism. Skeletal isomerism. Right. So basically, let me take an example. I am taking an example of ethanol and I am taking an example of dimethyl ether. I am taking an example of orthodichlorobenzene, and I'll be taking one more example of metadichlorobenzene. Okay, orthodichlorobenzene, metadichlorobenzene, I think we will take it in functional isomerism, positional isomerism. Let us write here only. I'll be taking here positional isomerism. Okay, both I'll be explaining in the same page. Metadichlorobenzene. Okay, what am I trying to explain? Let's see. So when I have to see the structure of ethanol, two carbon chain. So let us write CH3. This is ethanol is CH3, H, CH, H and OH. This is ethanol because two carbon chain. Here dimethyl ether also is two carbon chain, CH3, O, CH3. Now what happened? It is the same carbon chain, but we are representing in different forms. The skeleton has changed. So chain isomerism, isn't it? Right? So basically the difference, or what can we say, this type of isomerism arises when there is a difference in structure of carbon chain. So here it is arranged like this, but here the structure of carbon chain is arranged here. So chain isomerism is basically the difference in the structure of carbon chain. Done? Yes. So let me see position. In position isomerism, look here. I have a ring, benzene ring. Here also I have benzene ring. I said orthodichloro. So there is two chlorine rings, one at the ortho position, one, this is metadichloro, one here, one here. Now what are you observing? Position isomerism is basically the compounds possessing same molecular formula. Both the molecular formula is same, but what are they doing? They differ in the difference in position of the functional groups, isn't it? Molecular formula is same, C6H4Cl2, but they differ in the position of the functional groups. Here it is 1, 2, here it is 1, 3. So difference in the position of the functional group. They differ in the properties also because of the difference. So this is your chain isomerism and this is a position isomerism. So in chain isomerism, they differ in difference in the structure of carbon chain. In position isomerism, the difference in the position of the functional group. That's where the name is given. Right, students? Right. So let me come back and explain you in the next concept, that is functional isomerism, very clearly. Thank you for watching. So welcome back, students. Now we'll be learning about the next type of isomerism, the important thing, that is functional isomerism. So what have we learned? We have seen already chain isomerism or nuclear or structural isomerism. Then we also seen the position isomerism. Right. So now today's class will be studying about a different way of learning functional isomerism. Let's see. So functional isomerism, as the name suggests, what does it mean? Here any two compounds have the same molecular formula, but they possess different functional groups. That is the functional, those are called functional isomers. Once again, any two compounds having same molecular formula but possess different functional groups. Those are called as functional isomers, and the phenomenon is called functional isomerism. Done. So here I have to explain, or we will take different examples. Suppose, so let us start with the first lesson, that is your alkenes. We have started with haloalkenes, isn't it? In haloalkenes, okay, let us go to grade level. We have studied hydrocarbons chapter, that is your alkenes and alkynes. Suppose if I have to take an example, right? I am taking an alkyne. What is that? That is nothing but 1-butene, right? So 1-butene, let us write the structure. So CH3 single bond, CH2, C triple bond, CH. Now this is butane, 1-butene, 1, 2, 3, 4. Now this 1-butene, that is triple bond, it is isomeric. Means this butane is an isomeric with 1,3-butadiene. 1,3-butadiene. Okay, I have to write comma in between. Wrong, it is 1,3-butadiene. So what is this 1,3-butadiene? Let's see. So 1, 2, 3, 4. In the first position and the third position, you have double bond. So you fill in the hydrogen, CH2. This is CH, this is CH, this is CH2. So here what happened? These two are functional isomers. Why? Because they have same number of carbon atoms. Same number of carbon atoms, but only differ in their, here it is single bond. It is so here it is triple bond, here it is double bond. So your triple bond is an isomeric, or it may be isomeric with double bond sometimes. So these two are also functional isomers. Now let me come back to your grade 12th different functional groups which you have studied. Suppose if I take an acid, right? Let me take an acid, that is propanoic acid. So propanoic acid, how many carbons? In propanoic acid you have 3 carbons, 1, 2, 3. Propanoic acid, so CH3 and CH2. So this propanoic acid is in, or it is an, or carboxylic acids are isomeric with esters. Always remember, acids are isomeric with esters. Now which ester I'll be taking? I'll be taking methyl ethanoate. Let us see how many are there. So this is acid group. Now I'm writing ester group. So ester group is methyl ethanoate. See here, 1, 2, 3 carbons, 1, 2, 3 carbons, but here the group is acid group. Here the group is ester group. Correct? So acids are in isomeric with esters. Remember that. Let us take one more example. Cyanides are always in isomeric with isocyanides. So example is, here I am going to take RCN. This is cyanide. This is RNC. This is isocyanide. See here, number of carbons of 1 only, but cyano group is isomeric with isocyanide. Triple bond with double bond, acids with esters, cyanides with isocyanides. Now let us see one more class. Next, ketones are in isomeric with aldehydes. Okay, let us write. Ketones are functional isomers with aldehydes. Let us write a ketone. I am going to take CH3, CO, CH3. This is what? This is acetone. So same thing I have to write with acetaldehyde. Why? I said the number of carbon means the molecular formula should be same in both the cases. So here 1, 2, 3, 1, 2, 3. But here the functional group is ketones. Here the functional group is aldehyde. So what is the name of this? This is acetaldehyde. Done. Now, cyanides are over, acids are over, your ketones are over. Now, ethers are in isomeric with alcohols. Let's take. Suppose if I take an example of this. Same carbon. Right. 2 plus 2, 4. 2 plus 2, 4. 5 plus 5, 10. 9 plus 1, 10. So what is the name of this? This is called diethyl ether. Now 4 carbon chain is what? But. This is butyl alcohol. So ethers are in isomeric with alcohols. Means this is a functional group alcohol. Means functional group isomers. Right? So one is ether, one is alcohol. Right. Now let's see. I think we have covered ethers, we have covered ketones, we have covered cyanides, we have covered acids. Now let's come back and see one more. Nitroalkanes are in isomeric with alkyl nitrite. Let us see. Nitroalkane are in arrow double bond O. Here R O N double bond O. See here. Nitrogen, nitrogen, oxygen, 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 nitrogen, nitrogen. So are they now isomeric? Same molecular formula. Done? Right. So now let us see further. Next class. Here if I take butene, okay, means alkenes. Alkenes are isomeric with cycloalkenes. So butene, if I take butene example, 1, 2, 3 double bond. This is butene. Fill in the hydrogens, 3 hydrogens, 2 hydrogens, 1 hydrogen. So 1, 2, 3, 4, C4. So cyclo compound. So I'll be writing 1, 4. This is C4. This is nothing but cyclobutane. The same thing I can also write with methyl cyclopropane. So that is your CH3 group. This is methyl cyclopropane. So alkenes are in isomeric with cycloalkenes. Done? Yes. Fine. So now one more. Let's see. Anything else is there? Alkenes are over. Butyl alkynes we will write. So alkynes are in isomeric with cycloalkenes. Alkynes are in isomeric with cycloalkenes. Let us take an example. Alkyne 1, 2, 3 triple bond. Fill in hydrogens. This is hydrogens. This is okay. There is no hydrogen. Here it is. So what is the name of this? This is 1 butane. So how many? C4. Now I have to write with cycloalkynes. This is cycloalkenes. That is cyclobutene. Done? Yes, done. So one more. Your aromatic alcohols are in isomeric with phenols. Let us write that. Aromatic alcohols are in isomeric with phenols. Done? Yes, let's write that. Aromatic alcohols. OH, phenols. So this is called phenyl methanol. This is called orthocresol. Correct? So those two are isomers. So these are the different functional isomers, students, right? So we have one more class also, like amines, that is having same molecular formula and are also functional isomers. Those are your primary amine, secondary amine, and tertiary amine. So amines also you can include here in this category. Okay, let us write that also. So the last category I have covered alcohols, I have covered acids, I have covered ketones, I have covered that is your alkynes, I have covered alkenes. Now the last category, that is primary, secondary, and tertiary amines. So primary, secondary, and tertiary amines all have the same molecular formula. All have same molecular formula. Right? Yes. So, and their functional groups are different, means primary, secondary, and tertiary. So if I write CH3, CH2, CH2, NH2, this is which one? This is primary amine. Next one, CH3, NH, C2H5, this is secondary amine. Last one, this is tertiary amine. Done. So all these are having the same molecular formula, but important thing is there means this is called as primary amine, this is called secondary, this is called as tertiary. So functional group means same molecular formula are also function. These are also called as functional isomers. Done, students. So these are the different functional isomers. Hope this is clear. Thank you for watching. I'll meet you again with the next category of isomerism, that is stereoisomerism. Students, to one more session of your GOC chapter. So in the previous video, what have we seen? We have seen what is meant by geometrical isomerism. In that, I've also taught you, I've given you an index based on optical isomerism. I said I'll be dealing with different topics in that, right? So let us start off with optical isomerism today. Fine. So when I have to speak about geometrical isomerism, let's start first and start comparing with optical isomerism. So basically in geometrical isomerism, what do we see? We have seen the difference in arrangement of atoms around a double bond, correct? There we have got cis and trans isomerism, right? Or cis and trans isomers. Cis means on the same side, trans means on the opposite side, correct? Now, so let's say, so when I speak about geometrical isomers, the first important thing, what should you remember? You have to remember that in geometrical isomers, there are different physical properties. Like first important thing, remember they have different physical properties. So what are the different physical properties, right? The cis and trans isomer, they differ in melting point, done. They differ in boiling point. Then one more physical property like density, they differ in that, right? Fine. So, but when it comes to chemical properties, they have same chemical properties. Remember, same chemical properties. Done. But now same thing if I'm comparing with optical isomers. Now my concept is optical isomerism, so I'm talking about optical isomers in this case. So basically when I take optical isomers, important thing to remember, they are going to have same physical properties as well as same chemical properties. This is what is the important thing we have to remember, same chemical properties. Done. So now let us, with this basic idea, let's start discussing what actually is optical isomerism, or why are we calling, or why are we taking that concept of optical activity. Optical means light, isn't it? Right. So now, if I have to start explaining, simple words, when your teacher is asking what is optical activity, first let us write the definition and then go to the concept. So suppose if your teacher is asking define optical activity, now right, you have to write this simple, only just in four or five words, that is, it is action on or action of light or action on, okay, plane polarized light, action on plane polarized light. Okay, what is this word means? Let's see now. Right. Suppose if I take an ordinary light. Okay. Now ordinary light. So ordinary light, how do we represent ordinary light? Let us write that. Draw. Yeah. This is your this is an ordinary light. It propagates in all directions, isn't it? Right, all directions. Done. So when this ordinary light is sent through a nickel prism, okay, I'm sending this to a nickel prism. Let us draw one nickel prism. So this is your nickel prism. Then what happens? All these rays, they get cut off, and you get a light in one plane. This is which plane? One plane, this direction. This is one plane, okay? Yes, so this plane is called plane polarized waves. Okay, this is called plane polarized waves. Done. So what happens here in this case? The vibrations occur in all planes at this plane, this plane, this plane, at right angles to the line of propagation. Fine in this case. But as soon as you send it through nickel prism, this nickel prism, the remaining thing gets cut off, and the only one frequency light, that is plane polarized light, in one plane only you get, right? And this plane polarized light, suppose if it rotates the light, whatever you're sending, either to right or left, that means it will rotate the light in this direction towards right, in this way, correct? Yes, or it can also rotate the light in this direction. This is your left, right? So it can rotate the light in the right direction, as I have written. It can rotate the light to left direction also. Done. Yes, fine. So now this particular rotation, whatever is there, we are going to, this whole activity is called optical activity. Done. Rotating the plane polarized light either towards the right or towards the left is called optical activity. That's the concept, right? Now this particular optical activity is explained, or this particular rotation is explained by a typical word or a specific word, that is called specific rotation. Specific rotation. This specific rotation is denoted by alpha T naught, which is equal to alpha observed by L into C. Now we will write all. This is called, alpha is called specific rotation. Done? Yes. Now what is this alpha? This alpha observed is called observed angle of rotation. Observed angle of rotation. We calculate with using this formula, specific rotation, which is different for different molecules. Now what is this L? This L is called length of solution. Length of solution in decimeter. This is also done. Now what is the C? C is called concentration of active compound in gram per liter. In gram per liter. Done. Fine. Now important thing. Now you whichever along with this data, you calculate the specific rotation for different molecules. Suppose if the rotation, whatever specific rotation, if it rotates the plane polarized towards left, okay, let us write, if the particular molecule, if the rotation is rotation of plane polarized light, I am writing this PPL, is towards left, if it is rotating towards left in this direction, okay, in this direction, is towards left, then we call that form as LEVO form, and it is denoted by L form, and because it is towards the left, we denote by a minus symbol. Suppose if the rotation of plane polarized light is towards right, then I call this as dextro form. Dextro form, we denote it by D form, and the symbol is plus towards the side. Right? Fine. So this important concept, now we'll gradually go into or we'll start writing the meaning of optical isomer. Right? Fine. So let us take out this concept and start with one more. So basically, whenever I say optical isomer, important thing. First, okay, I have learned what is optical activity, then I have learned what is specific rotation. Now I'll speak about a term called optical isomer. Done. First important thing, for a molecule to be optically active or optical isomer, the important thing is there should be presence of chiral carbon, but never ensure it is optical. Even if it is presence of chiral carbon, never ensure it is optically active. That important thing you should remember. If it has chiral carbon, doesn't mean it will be optically active, but I'm writing that but also, but never ensure molecule is optically active. This is one of the condition, but with that only I can't decide optically active. Okay, done. What is important thing next? What is a chiral center? Now I say, what is a chiral center? Let us write that. Chiral center is basically have a carbon or carbon. I'll draw in with an example, you understand. Having or attached to four different groups. Okay, now let us write an example, you will understand what it is. Suppose if I have a carbon here, I said four different groups. So here I have bromine, here I have chlorine, here I have fluorine atom, here I have iodine atom. Isn't it four different types of atoms or groups of atoms? Done. Fine. Suppose if the same thing, now this carbon is called chiral carbon, as I said, chiral center or chiral carbon, which has four different groups. So this chiral carbon, same thing. If I am trying to draw the mirror image of this, I am trying to draw the mirror image. Exactly, this is the mirror image of this. Means this Cl comes here, this iodine comes the other way, bromine comes on the top, fluorine down. So let us write that. Bromine, this mirror image, Cl, this iodine on the other side, iodine, we have fluorine. Done? Yes. So first important thing is, here these two are called optical isomers. Okay, what are you observing? Suppose if I take this isomer, and right, if I take this isomer and if I take this isomer, if I try to superimpose it, can you get? That means what do you get? Here I have like this. Now here I'm taking this chlorine, here I'm taking this chlorine, I'm superimposing it. They can't be superimposed, isn't it? Right? So optical isomers are non-superimposable, or they show non-superimposable, or they are non-superimposable mirror images. Non-superimposable mirror images. Next important thing, they have or they possess a chiral or asymmetric carbon. These are the conditions for asymmetric carbon or asymmetric carbon. So with this particular thing, I can say any molecule, if it is means if somebody says, how can you prove that it is optically active? You have to remember, it is non-superimposable on its mirror image. It is non-superimposable on its mirror image, first thing. And next important, okay, chiral, it has chiral and asymmetric center. Next important, does not contain any elements of symmetry. Any elements of symmetry. Okay, now what is this elements of symmetry? We will see. Done. Now I have got a basic idea. It has a chiral center. Done. It should be non-superimposable on its mirror image. That also done. Then I said it does not contain any elements of symmetry. I said. So first of all, we have seen how does it rotate. Then we have seen what is specific rotation. Then I said gradually I have taken you into the concept. Now we'll see what is meant by elements of symmetry. Let us write. So basically elements of symmetry, when I have to write the heading, I said it does not contain, isn't it? So what are these elements of symmetry? Elements of symmetry basically is it offers, means this particular thing offers a simple device. It is a simple device. How it's going to decide whether the molecule is chiral or achiral. Okay, right? So whether the molecule is superimposable or non-superimposable in its mirror, whether the molecule lacks all elements of symmetry, it is chiral, means it's going to decide that conditions. What this elements of symmetry is going to explain or decide whether the molecule is, let us write, whether the molecule is chiral or achiral. This is one condition. Second, it's going to say whether the molecule is superimposable or non-superimposable. Superimposable or non-superimposable on its mirror image. On its mirror image. This is what it says. Right? This is what it explains us. Right. Now let's see plane of symmetry, the first one. So in elements of symmetry is again studied under what? Two important things. One is, okay, three important things, right? Three important things. One is plane of symmetry, that is denoted by sigma. Next, center of inversion, which is denoted by I. Next, alternating axis of symmetry. Alternating axis of symmetry, which is denoted by Sn. Now let's come back and learn one after the other clearly what is plane of symmetry, center of symmetry, and alternating axis of symmetry. Students, so in the previous video we have seen what are elements of symmetry, that is the different categories. What are they? We have studied about plane of symmetry, then we have seen center of inversion, then also shown you what is meant by alternate axis of symmetry. Now in this video we'll be learning about the enantiomers and diastereomers. Right, we will learn what are these with an example. We will see what are the different characteristics of these, and then gradually go into the topic of inversion, retention, and racemization. Now, so when I have to speak about enantiomers, the first important thing, so I've written both together so that you know the difference. So enantiomers are what? Basically, these are the molecules which are non-superimposable on its mirror image are called enantiomers on its mirror image. I showed you, isn't it? When I hold like this, when I take both the molecules, they are non-superimposable. So non-superimposable on its mirror images are called enantiomers. Suppose if I take diastereomer, we'll be taking examples in like just 5 or 6 minutes, then you will understand this. So when I speak about diastereomers, what are they? These are also stereoisomers. These are also stereoisomers, right? Stereoisomers which are not mirror images of each other. Okay, each other. Done. What is the difference? When I speak about enantiomers, they have same physical properties as well as same chemical properties. Chemical properties. When I speak about diastereomers, they have different physical properties as well as different chemical properties. Done? Yes. So now let us see an example for enantiomers. Then you will understand what are enantiomeric pair. Right. I am drawing the line below. Just see. Suppose if I take an example like this. Just see here. This is one benzene molecule. I have NO2. I have again NO2 again. COH. This is also COH. Now this molecule is active. When I have to draw the mirror image of this is optically active. When I draw the mirror image of this, just see here, exactly here. This is one benzene ring, again benzene ring. This is NO2. This is also NO2, COH, COH. Done. Now see here. This ring, you drawn it here. The nitro group is here. Again COH is here. Again this comes on the other way. COH, NO2. These two are called enantiomeric pairs, which are non-superimposed. If I hold this and hold like this, if I try to do the superimposing part, will they match? No, isn't it? Non-superimposable on its mirror image are called enantiomers. Remember this, right? So when I have to speak about okay, what are these called? These are called enantiomeric pairs. Enantiomeric pairs. Now, suppose if I have to speak about diastereomers, I said they have different physical properties, different chemical properties. So what are the different physical properties? Like the different physical properties are they differ in melting point, they differ in boiling point, they differ in solubilities in a given solvent, they differ in densities, they differ in refractive indices, all these things. Right, so let us learn some more points about diastereomers. Right, so along with this diastereomers, they also differ in specific rotations. We told you, isn't it? It is denoted by alpha. They differ in specific rotations. Right. So now diastereomers, how can we separate? Right. So isolation of diastereomers, because they have different. It's easy only, right? So we can also separation of diastereomers, different techniques. Let's see that. Separation of diastereomers. I can separate diastereomers by fractional distillation. Why? Because there is a difference in boiling point, isn't it? Fractional distillation methods. Fractional distillation methods, there should be difference of boiling point. So with that concept, I am doing this fractional distillation due to difference in boiling point. Then fractional crystallization. Why? Due to difference in solubility. I can also separate diastereomers by a process called chromatography. Chromatography. We have seen, isn't it? Different types of paper chromatography. There is a thin layer chromatography also, right? Why? How am I separating what factor? Due to difference in molecular shapes and polarity. So with these factors, I am able to separate diastereomers. One is fractional distillation, taking boiling point into consideration. Fractional crystallization, taking solubility into consideration. Chromatography, due to difference in molecular shapes and polarity. Now let's see an example of diastereomers. Right, fine. So when I have to draw the example of diastereomers, I am taking glucose structure. Right, fine. So glucose exists in two forms, isn't it? L-glucose and D-glucose. Right. Let us draw all the three. Fine. First, I am drawing the skeletal structure. Done. OH 1, 2, 3, 4, CH2, OH. Mondo H 1, 2, 3, 4. H2OH. Okay, and now this is a different molecule, that is galactose I'm drawing because I have to show you the diastereomeric forms. So here this is L-glucose. Then this is D-glucose. This is D-galactose. Right. In L-glucose, OH in this side, H in this side, H, OH, H, okay, OH, H, OH, H. In D-glucose, H and OH on this side, OH and H here. In the fourth one, HOH. In the fifth carbon, HOH. Now, in galactose, HOH, OHH, OH and H, H and OH. Now, this, let us number this is 1, let us number this is 2, let us number this is 3. Now see, 1 and 2 are enantiomers, okay, right? They are non-superimposable on the mirror images. If I take this and superimpose it, they will not superimpose because this comes under this, H and OH. This OH comes under H. H comes under OH. H comes under OH. So non-superimposable. Right. So 1 and 2 are what? They are enantiomers. 2 and 3 are diastereomers. Diastereomers. Right? 2 and 3. What do we write for this one, diastereomers? As I've written in the earlier video, we have written this, isn't it? See here, stereoisomers which are not mirror images of each other. Let us see. See here. Is this a mirror image of this? Let's check. OH and H, not mirror image. HOH, not mirror. First molecule only says that it is not mirror image, isn't it? So diastereomers are stereoisomers which are not mirror images on each other. Done. So this is your enantiomers and diastereomers, students. So careful. Just see, you have to remember two things: non-superimposable in mirror image, which are not mirror images. First thing. Next, same physical and chemical properties, different physical and chemical properties. This is an example of enantiomeric pair, and here when it comes to diastereomers, these are the factors. Then I have taught you with the important thing, how can I separate, means specific rotation also is different. Then I taught you how can I separate diastereomers, 1, 2, 3 factors. Then I have shown you an example. 1 and 2 are enantiomers because they are non-superimposable in the mirror images, and these are not mirror images, diastereomers. Thank you for watching, students. I'll meet you again in the next video, that is with the concept of inversion, retention and racemization. Thank you for watching. Welcome back, students. So in the previous video, we have seen what is the difference between enantiomers and diastereomers. Before that, I have taught you the concept of optical isomerism, where I have shown you elements of symmetry. Then I have shown you what are plane of symmetry. In that elements of symmetry, I've taught you the concept of plane of symmetry, center of symmetry, alternate axis of symmetry also. Now, so today we'll be learning about inversion, retention and racemization. Now, so what is inversion, retention and racemization? First of all, whenever I have to speak about racemization, first let us write the definition, right? So racemization or racemic mixture, right? Racemic mixture. So racemic mixture is basically, it is, means it's an equimolar mixture, 50 by 50, 1:1 ratio of enantiomers, right? Let us say, what is it? An equimolar mixture of two enantiomers. Equimolar mixture of two enantiomers. How much? Equimolar mix means 50 by 50, means that is 1:1. And those two enantiomers, which forms? I said equimolar mixture of two enantiomers, 50 by 50, that is both D form and L form, that is dextro and levo, where they rotate the plane polarized right towards right as well as they rotate to right. So the mixture of these, what will happen, which results in zero rotation. When they mix up, zero rotation. Because of this racemic mixture, hence the racemic mixture is, because it has got cancelled, isn't it? So the racemic mixture is optically inactive. Optically inactive. Let us take an example. right? So I'll be taking in racemic mixture we have understood. Now we'll take an example of like inversion, example of retention, which is an NCERT example, so it's easy for you to understand, right? Suppose if I've picked up this example from your haloalkanes haloarenes chapter only. Done. If I have a molecule like this, X, and it has three substituents, 1 C2H5, H, this we have studied in your SN1 mechanism, and SN2 mechanism, the concept is given there, right? Suppose this particular molecule, there are 2, 1, 2, 3, done. If the same molecule, listen, if it has, or if it shows, if the configuration of this molecule is written like this, let us name this as A. The configuration of this molecule after rotation. Suppose if I just write the rotation Y, C2H5, H, CH3. Now what are you finding here? X or Y. This is B. The mixture of A and B together. Right. Now let's see. This is a molecule. If the molecule this on after the reaction on rotation, suppose if the configuration of this molecule is retained, it is like this here, X is here, C2H5 is here, H is here, CH3 is here. If the configuration is retained, right, then it's called retention. Suppose in this case, see here, the configuration is inverted, then this is called inversion. The combination of these two is called racemic mixture, right? Right, let's see. Suppose I said for a particular molecule, if only A is obtained, right, what do we call? We call it as retention. The molecule, if only B is obtained, then we call inversion of configuration. Suppose if I get 50:50 mixture of both, then I call it as racemization. So what do we say? Racemization, there is zero optical activity, means optically inactive it is because they get cancelled, right? So this is your inversion, retention and racemization. Students, I've taken this example, as I said, I've taken it from your NCERT only. Fine. Important thing. Racemization, when I take, let me add two more things. It is the reverse of resolution. Means it is a conversion of plus or minus isomer into racemic mixture. How do we represent? We represent it by plus minus like this, right? So thank you for watching, students. I'll come back and meet you with the next type of configuration, that is a relative configuration, that is DLN nomenclature, RS nomenclature with certain examples. Thank you for watching. Welcome back, students. So in the previous video we have seen how to prepare reaction intermediates, that is carbonium ion, carbocation, your free radicals, nitrines and carbenes. Now let us come back and study the structure of these reaction intermediates. That is, the first one is carbonium ion, right? So whenever we are seeing the structure, so basically you have to remember, let's write the heading first, carbonium ion. That. So whenever you're explaining, remember for a structure, important category thing are, you have to draw the orbital diagram, you have to explain, write the type of hybridization, you have to write the bond angle, you have to write the shape also. Done. So here when I speak about carbonium ion, so we said carbonium ion is denoted by which charge? It is a positively charged species, positive charge. So carbonium ion, basically the structure looks like this. Fine. Suppose if I take in the case, I'm taking the case of CH3, like I'm taking the case of this CH3 plus. How does this look? The shape looks like this. Carbon in the center with positive charge. You have one lobe above, you have one more lobe below. There is one lobe off, as this is also one more lobe, and right. So in case of CH3 plus, there is one p orbital, vacant p orbital, right? So this is sp2 hybridized, this is also sp2 hybridized, this is also sp2 hybridized. So here, first important thing, are you finding any non-bonding electrons? No. The first important characteristic is it has no non-bonding electrons in carbonium ion. Non-bonding electrons, first characteristic. Next, when I see the hybrid, how is the shape looking? The shape is nothing but shape is trigonal coplanar. Coplanar. What is the hybridization? The hybridization is you have already seen, it is sp2 hybridization. What is the bond angle here? Bond angle is 120 degrees. And when I have to see its magnetic property means whether it's paramagnetic or diamagnetic. Here there are no unpaired electrons, all are paired, hence it is diamagnetic in nature. Diamagnetic in nature. Okay, done. So this is the structure of your carbonium ion. So when I have to see the structure of carbanion, let us see. So structure, the second category is carbanium or carbon ion or carbanium ion, or you can also write it as anion. That's also is okay. Done. So the structure, we said it looks like this. Carbon in the center. There, circle this. One lobe here. One lobe. Yes, this is important pair. This is what, there is one more lobe. Right. So here it is sp3 hybridized orbital. sp3, this is also sp3, this is also sp3. So hope this is clear, students, because with this concept I think you can write what actually is the hybridization. I'm leaving it to you. Bond angle, you can write the shape, everything, right? I'll give you this as a homework. Let's come back and see the next one, reaction species, that is free radicals. Let's write that. Free radical structure we will see. So when I have to speak about free radical structure, so free radical, as I said, it is denoted by a dot. First important characteristic of free radical is they are neutral species. Neutral. And they are highly reactive. Highly reactive in nature. And as I said, they are very short-lived. For a very few seconds only, the duration is very short-lived. They exist for a very few seconds. So when I have to draw the structure, the free radical structure, carbon in the center, I said it is denoted by a dot, isn't it? One dot. And remaining all lobes are sp2 hybridized lobes. All are sp2. This is also sp2, this is also sp2, this is also sp2 hybridized lobes. So atoms with free radicals, free or odd electrons, they have an odd electron, or free radicals are basically called, they have an odd electron, or which is denoted by single dot. So they have odd electron. Right. Again, I am leaving it to you. You can write the shape, bond angle, everything according to which I have explained earlier. Now when I take a carbene structure, let us see. Carbene. So carbene, basically there are two types of carbenes. One is singlet carbene and one more is triplet carbene. Triplet carbene. So when I take singlet carbene, let us see the structure of singlet carbene. So singlet carbene, basically you have carbon, both the things here. In the difference here is, in singlet carbene, again the same, we have sp2 hybridized lobes here. Yeah, so okay, this one I can towards this. So this is sp2 hybridized, this is sp2 hybridized, this is also sp2 hybridized. So in triplet carbene, the difference is, just see, You're drawing the lobes here. So sp2 hybridized. This is also sp2 hybridized, but here you have a pair of electrons, but here you have electrons, right? So means the spin of the electron will be one is shared here, and in this case one is shared with the same spin. So it has two electrons with same spin. It has two unshared electrons with opposite spin in one. Let us write that. In singlet carbene, it has two unshared electrons. Where are they present? They are present, or means the spin is with opposite spin in one orbital. In only one orbital it is present. You see here, one orbital. So here when I take triplet carbene, again it has two electrons with same spin. Spin is same spin, but where? In two different orbitals. In different orbitals. That is what you have to remember. And when I take this, what is the shape of this? This is linear, basically. This is sp hybridization. So that's only difference. So when I take a nitrine, when I have to draw the structure of nitrine, so it is like nitrine. Again, nitrines are of two types: singlet nitrines and triplet nitrines. Let us write that. Singlet nitrine and triplet nitrine. Let us draw the structure of this. So singlet nitrine, it looks like nitrogen here. One more bond, one lobe above and below. One has, pair. So the overall charge plus. This name, this is Z, this name, this is Y. So when it comes to triplet carbene, here we have both the electrons present in the same orbital. In triplet carbene, as I've shown in the earlier one, again two lobes. Both the electrons are present in two different lobes with the same spin. And this is your Z, this is your Y. Done. So this is how these are the structures of different reaction intermediate, students, right? So hope this is clear. I'll meet you again with the next concept, and we will see like the different questions based on reaction intermediates. Thank you for watching. Right, now let's see the alternate axis of symmetry for methane molecule with an example. Right, so in methane molecule, when I take, let us draw and understand. Suppose I said I'm going to take an example of methane molecule. Right, we will understand what is meant by alternate axis of symmetry. Done. So methane, when I have to represent the structure, one carbon, formula is CH4. Done. One hydrogen here, one more hydrogen here, the third hydrogen here, one more hydrogen here. Let us number this as 1, 2, 3 and 4. Done. Right. Now what are we going to do? We are going to do the rotation by 90 degree. Rotation by 90 degree. Here we're taking the example of 90 degree. When you rotate in this direction, right, like this, how does this look like? Carbon, this plane of this, one hydrogen, one more hydrogen, one more hydrogen, one more hydrogen. This is first, this is second, this is third, this is fourth, because you have rotated like this, isn't it? Done. Now we said once after rotation you have to do the reflection in a plane perpendicular to that, we said. Correct? Fine. So How does this look? Carbon, rotate like this, reflection on a plane perpendicular to it is it. And how do you get the hydrogen? This hydrogen one will be here, one more hydrogen here, one more hydrogen here, one more hydrogen here. So this is the fourth one, third one, second one. Okay, you're rotating like this, right? And the reflection, the plane in a plane perpendicular. Done. So this is how is, this is what is called as your alternate axis of symmetry. Students, I said a molecule possessing alternate axis of symmetry, if one rotated to 360 degree, here we set rotation by 90 degree about the axis, then followed by the reflection in a plane perpendicular to it. So this is a reflection in a plane perpendicular to it. Then this is called alternate axis of symmetry, right? Thank you for watching, students. So welcome back, students. So today in our session we'll be learning about what is the order of preference given while, like, suppose you have given different function groups, like we have studied in grade 10, grade 11 also, means basically in this chapter, in grade 12 also we have different function groups. What are they? Like you have acidic function group, that is carboxylic acid, amines, aldehydes, ketones, cyanides, isocyanides, ethers, alcohols, thiols, like that. So when such different functional groups are given, what order should you follow is what is very important. Now, so whenever there are function groups, let us first see the order. You need to remember this order, compulsory. If you just memorize this, put it in your bookshelf, whenever you see, okay, this is the order when multiple function groups are given in the particular nomenclature. So whenever you have the first preference is given to carboxylic acids. Always remember, when you have 4 or 5 function groups present in the particular sum, or means not sum, the particular example, first one whom will you give? The first order is given to carboxylic acid. Carboxylic acid. Done. So what is the carboxylic acid? How do you, what is the formula of carboxylic acid? Basically it is COOH. This is the carboxylic acid. That's a functional group which is present. After that, the next order is given to sulfonic acid. Next preference is given to sulfonic acid. So the formula is SO3H. Now, next order means, or the preference is given to carboxylic anhydride. Carboxylic anhydride. So the formula is C double bond O, O, C double bond O. After that, the next preference is given to esters in the order. Ester formula is C double bond O, OR. After ester, you will be given preference to acyl chlorides. Acyl chlorides. The formula for acyl chloride is C double bond O, Cl. After that, amides are given preference. Amides, C double bond O, NH, 2. After amides, the next preference is given to cyanides. Formula is C triple bond N. After cyanides, the next preference is given to aldehydes. Aldehydes. Formula is CH. Aldehydes. After aldehydes, then you will give preference to isocyanides. NC. After isocyanides, you will give preference to ketones. The formula is, on either side you have alkyl groups. After ketones are given preference, you will give preference to alcohols. OH. After alcohols, you will be giving preference to thiols. SH. Next preference is for amines, that is NH2. Next, the last preference is for ethers. Ethers, OR. Ketones is C double bond O. Ether is O. right? Suppose if you have any other functional groups, like if you have halogens, or if you have alkoxy groups, if I have phenyl groups, so you have to remember after all these remaining functional groups, like as I said, halo, fluoro, let us see. So what are the remaining functional groups which we have? Remaining functional groups which we have is halogens, that is X. It can be fluoro, chloro, it can be bromo, it can be iodo, right? So all these. Next, you may have some other functional groups like phenyl groups. Okay, phenyl. So phenyl formula is C6H5. You may have some other functional groups like alkyl. So alkyl, right? That is denoted by R. You may have some other functional groups like alkoxy. Those are, that is OR. Right? So what are these? All these will be always treated. They are always treated as substituents only. So remember, always treated as substituents. Remember that, always treated as substituents, right? Don't forget the students. So this is the order of your functional groups. The first one, as I said, remember, carboxylic acid, sulfonic acid. First, this is first importance. Least importance is ethers. So carboxylic acid, sulfonic acids, carboxylic anhydrides, esters, acyl chlorides, amides, cyanides, aldehydes, isocyanides, keto group or ketones, alcohols, thiols, amines, and ethers. So the first preference is given to carboxylic acid, and the last or the least preference is given to ethers. Then I told you all these groups like halogens, the fluorine, chlorine, bromine, iodine, phenyl groups, alkyl groups, alkoxy groups, they're always treated as substituents. Don't take them as a functional groups, right? Thank you for watching, students. This is a very important information. I'll be starting off with my next video, that is nomenclature of hydrocarbons. Thank you for watching. Stay connected, stay happy always. Welcome back, students, to one more session of your relative configuration, that is DLN nomenclature. So here I said I'll be teaching about DLN nomenclature. I'll be teaching about RNS nomenclature. So in the previous video I've taught you what is meant by racemization or racemic mixture. I've also shown you how is the configuration retained. I have also shown you what is the inversion of configuration. So please watch the previous video. All videos are interlinked now. So this relative configuration, when do we, like, what makes the concept, means how should we start off? First of all, this particular configuration means we're going to study for all the compounds with respect to glyceraldehyde configuration. So glyceraldehyde is taken as a arbitrary standard. Means we're going to take it as a standard and study its configuration, right? So let us write that. Relative configuration, it is a configuration of all the compounds with what? With respect to glyceraldehyde configuration, right? Why are we taking? We are going to take it as a, of which is taken as arbitrary standard, right? And we'll just write the structure of glyceraldehyde and then understand. Basically, glyceraldehyde exists in two different forms. One is D plus glyceraldehyde, and next is L minus glyceraldehyde, right? And so basically, when D plus glyceraldehyde, when I take the structure of the molecule, just see here, always in D glyceraldehyde, OH is on the right hand side. In L glyceraldehyde, OH is on the left hand side. Done? Right. And here there is an aldehyde group, here also aldehyde group. Here CH2OH group, here also CH2OH group. Now, OH on the right hand side means it is D-glyceraldehyde. OH on the left hand side means L-glyceraldehyde. Opposite to OH is your hydrogen atom. Right? So remember, OH on right, H on left. In L-glyceraldehyde, OH on left and H on right. This is the important thing which you have to remember. Right? So any compound that can be prepared means from D-glyceraldehyde belongs to D series, and whichever is prepared from L-glyceraldehyde, it belongs to L series. Now let's come back and see what is meant by RS nomenclature. So let us write the heading RS nomenclature. Right. R stands for rectus. S stands for sinister. Rectus means right. Sinister means left. Remember. Right. So basically in RS nomenclature, first important thing, what should you remember? So before going into the example, there are certain set of rules which you have to remember. So this set of rules, these are called SIP rule, C-I-P-R-U-L-E. So what does SIP stands for? SIP stands for, C stands for your can, I stands for include, P stands for prelogue. Okay, these are the SIP rule, can, include and prelogue. These were given by them, and this particular rule, we assign a sequence of priority to 4 atoms. We'll be seeing with an example RS configuration. So basically when I have to speak about SIP rules, first there are different steps to be followed. Yes, let us start with the first step, step 1. Right. So here in step 1, priority depends on atomic number. Okay, so remember here priority depends on atomic number. Suppose if you have isotopes, so in case of isotopes, what do we take? We consider atomic weight. Done? Yes. So hope this is clear. Now next important thing, if the atomic number is same, then what do? We start comparing atomic number of the second atom. Then compare atomic number of second atom, and so on. Right. Suppose if there is a double bond or triple bond, right? Let us see that condition also. When there is a double or triple bond, triple bonded atoms, then the atoms are considered to be duplicates or triplicate, means it is duplicated or triplicated. So whenever there is, once again, when there is a double bond or triple bond, then atoms are considered to be duplicated or triplicated. Triple bond atoms are considered to be duplicated or triplicated. Okay, triplicated. Let us take an example and understand this. Right? Right. So first, let me take an example. So in this example, let us follow the rules once again. Priority depends upon atomic number. Then, if you have isotopes, you have to talk about when you will be considering atomic weights. Then we said if atomic number is same, then you will be comparing atomic number of the second atom. Then we said whenever you have the double or triple bond, then atoms are considered to be duplicated or triplicated. Then here, if I take first one example, carbon, hydrogen, carbon, so 3H, Cl, Br, right? So the sequence, how do you take this? The sequence is, in such case, sequence is bromine greater than Cl, greater than SO3H, greater than H. So this will be first one, this will be second one, this will be third one, this will be fourth one. Right. Let me take one more example. CH3, CH2, C, CH double bond. Now this is a case of double bond. H2, CH3, C triple bond, CH. Now we have spoken about third, isn't it? When there is a double bond or triple bond, then atoms are considered to be duplicated or triplicated, we said. Correct? Yes. Here the CCH, whatever is there, C triple bond CH, it is, what is it equivalent to? It is equivalent to one carbon, C, C and C. Now this one, the C double bond CH2, it is equivalent to carbon, C and C. Now, so what is the sequence now? Here, for this is a sequence. In this case, according to the SIP rule, you have to remember, yes, first one would be C triple bond CH greater than C H double bond greater than C CH2 greater than CH3. So this is the order in this case. According to the SIP rule, you have to remember this. Hope this is clear, students. Now let me come back and take one more, that is step 2. Right. So when I have to take to, according to step 1, that rule is over. Step 2. Right. Fine. So in step 2, we'll how do we visualize the molecule? We will visualize the molecule in such a way that the ligand of the lowest priority is directed away from us. Right. So let us take one example and see that. Right. Welcome back, students, to one more session of your general organic chemistry. Right. In the previous video, what did we learn? We have learned about the SIP rule, isn't it? How are we going to name or learning the nomenclature of RNS system? Right. So we have already seen the step 1 of SIP rule. Now today in this video we'll be seeing step 2 and step 3. I'll also be teaching you how to deal with different, like means if they give you a typical example and they've asked you to write the RNS nomenclature, that also I'll be dealing, but not now. I'll be just giving you step 1, step 2 and step 3. Right. So in step 2, important thing, as we have seen, let us recollect once again. Suppose if I have a molecule like this, carbon, according to the first rule, I have one hydrogen here, right? The other end, I have bromine. Here I have CH3 group. Here I have chlorine. Now, according to the first SIP rule, how should we number? We have to number according to their atomic number. That is what is the thing. If it is isotopes, I said we will go with the atomic weight. Now, according to atomic number, first atomic number, bromine is greater, isn't it? Then chlorine is greater than carbon, greater than your hydrogen. So this is 4, this is 3. Okay, let us write this first number, 1. This is 2, this is 3 and this is 4. So the maximum atomic number is named first. Done? Yes. So that's over. Now in step 2, let's see. Now what are we going to do? We are going to take the same molecule and we are going to rotate the molecule. So how do we rotate? When I rotate the molecule, how should I rotate, as I say? Such that, right, the one which is marked 4. Now this is 4, isn't it? Let us number. This is 1, this is 2, this is 3, this is 4. So I'm going to rotate the molecule in such a way that the one which is ranked 4, means this particular thing, is at the back. Okay, it will be at the back. A dash line, it will be at the back. Means it will go in the other side, in this way. I'll show that also. So rotate the molecule in such a way that such a way that the atom which is ranked 4. Is or it is in the back. In the back, right? We will see that slowly as we understand, right? So in this is over, so just you rotate and keep it. Now I'll be taking you to the step 3 part. So in step 3 part, what is important understand? Here we have numbered it as 1, 2, 3 and 4, isn't it? Right. So with the 4th atom with hydrogen, we said 4th the hydrogen atom at the back. Suppose if I am going to trace the path, how? If first option, if 1, 2, 3, right? They trace a clockwise path, right? In this direction, clockwise path. Then we assign the chiral center as R, right? Then we assign chiral center as R. Remember this, right? Let's see an example for this. So how is example? I'm taking the first one. As I said, I'm shifting it towards the other end, right? Now let us take the same one, right? Hydrogen is here, bromine is here, CH3 is here, Cl is here. Let us number. This is the 1. Then after that 2, this is 3, this is 4. Suppose if the same thing, if 1, 2 and 3, if they are taking a clockwise direction like this, then what is the chiral center named as? It is named as R system, right? Suppose if the same, as I have written, the same molecule, then if they rotate as I said clockwise, then I call it as R center. Suppose if the same thing, if 1, 2, 3, if they trace and counterclockwise, okay, that means anti-clockwise direction, or we can also write it as if they take a counterclockwise path, then what do I name it as? I name it as S system. Let us see that. The same example here. See, now I am rotating it. H, Br, CH3, Cl. Number it. This is 1, this is 2, this is 3, this is 4. Right? Now let us number 1, 2, 3. If it rotates in direction, then I call the system as S system. Okay, R system in the clockwise direction, S system in the anti-clockwise direction. So hope students you are able to understand what I'm trying to explain you. Now let us take one more example which will explain what happens when we have more than one chiral center. Let us write that. So step 1 is done, step 2 is done, step 3 is done. Now further, if I take this condition, when a molecule containing more than one chiral center, then how should you name? Then what do? We are going to take the confirmation of each center, right? Each center configuration, not this in the configuration of each center is determined. I'll show you with an example. Configuration of each center is determined separately. Let us take an example and see. This is also one way of naming the system, determined separately. So let us take 2 examples and see. Suppose if I have one example here, I have COH, here COH, one is H, one is OH, here this is OH and this is H. Let us take the part B. Again COH one end, COH another end. Okay, now OH in this end, H here, OH here, H here. Done. How should I name this? First number it. I said they determine separately. 1, this is the second center, this is the third one, this is the fourth. Again 1, this is the second, 2, 3 and 4. Now I have to name this. It's going in which direction? It's going in the clockwise direction, isn't it? Right? So the system has 2R and 3R. Suppose if I take this here, see here, they are gone what? Here 2 are second are clockwise, 3 are clockwise. In this case, what happened? This has taken the anti-clockwise direction. See here, there is a shift of the molecule in this direction. So this becomes, where it is a shift, it has shifted at 2s, and this is again at 3r. So this is how we are going to name or give the or SIP rule is indicated using different examples. Step 1, step 2 and step 3. So in the 9 o'clock slot, I'll be showing you how to name or I'll give you a trick how to name if there are tricky questions given on RNS nomenclature. Right, thank you for watching, students. Right, so hope RNS nomenclature and DLN nomenclature is clear. I'll meet you now with, on my next video, the conformational isomerism. With that, all the types of isomerisms will be done. Then I'll be jumping into a topic that is nomenclature. I'll be picking up grade 11 as well as grade 12 nomenclature all together under one platform. Thank you for watching. Right, so welcome students to one more session of your GOC 1. Till now we have completed loads of topics in GOC, starting from GOC 2, then I gradually came to GOC 1. I have completed different topics like electronic displacements, inductive effect, in that inductive effect, mesomeric effect, then hyperconjugation, then I've taught you about electromeric effect, all those things. After that, I've taught you about reaction intermediates like carbenes, carbonium ions, carbocations, free radicals, nitrines. And after that, I've also taught you the concept that is in general organic chemistry 1. I've taught you what is meant by, or the classification, the flow chart of isomerism. In that, I've taken up different topics like structural isomerism as well as stereoisomerism, in which I've thought about optical isomerism and as well as conformational isomerism. So my last topic was I've given a clear explanation about the conformations of ethane, butane, propane and cyclohexane. Now in today's video, I think it's a long journey again. I'll be teaching about the nomenclatures or the concept of nomenclature, starting from hydrocarbons, that is your alkenes and alkynes, finally end up with the grade 12 nomenclature, that is till amines also. Right, I'll try to explain with cycloalkanes nomenclature also. Done. So when I have to start with the nomenclature concept of organic chemistry or organic compounds, so the term nomenclature means nothing but naming. So basically there are two systems of naming a compound. Organic compound, I can name it using the first system, that is called trivial or common systems. Okay, common system of naming. The second class is IUPAC nomenclature. IUPAC system of nomenclature. Done. Right. So when I have to speak about the trivial system of nomenclature, so here we are going to name the compound or assign the compound based on the source of their origin, means how from where they are originated. Like as you've studied in wheaten, citric acid, or if I have to trace from, it is obtained from citrus fruits, or even ant, basically formic acid from ant, isn't it? So the Latin name of ant is formica. So from wherever it's originated, we start naming it. That is a common system. Now suppose if I have to take the IUPAC nomenclature. So IUPAC nomenclature, we start based on certain rules. We start numbering the compound, organic compound, and after that, according to based on the criteria and the rules, we name the compound. So I'll be dealing with different classes in both the cases. So when I have to start with the trivial system, I have drawn a table here. We will name it. So here these are the common or trivial names. TRIVIL, trivial names of organic compounds. So here, first one, this is your methane. So compound is CH4. Here the common name is, I've just taken certain examples. The first one is methane. Right. Here the 4 carbons, so this is called N-butane. I'll explain you how to write everything, just generally I'm explaining. Here they are, okay, CH3, this is called isobutene. There are 4 carbons here, this is called 4 + 1 5, neopentane. Then this is one more with aldehyde group. This is called formaldehyde. There is one group hidden here. This is Alcohol, nothing but ethanol, 2 carbons, all. There is CO group, this is a ketonic group, this is called acetone. Then CHCl3 is called chloroform. Acetic acid, this is called anisole. This is an amine group here, so this is aniline. Like that, we have different common names. This particular thing is called acetophenone. Right, these are all the common names. Nothing, don't panic, nothing to remember by heart. I'll teach you how to do it. So basically, when I have to take the IUPAC nomenclature, so as I said, IUPAC nomenclature, first IUPAC PSC stands for International Union of Pure and Applied Chemistry. So here we are going to follow certain set of rules, very important rules, but the name of the organic compound according to IUPAC system. So what are we going to take? First, secondary prefix. I'll teach you what is secondary prefix and everything. Plus primary prefix. Plus word root. Plus primary suffix. Plus secondary suffix. Okay, this is what is the thing which we are going to follow. We will be naming it according to this in the IUPAC nomenclature. So when I have to take certain examples, see here we'll be writing the IUPAC nomenclature of alkenes. So let us write IUPAC nomenclature of alkenes. Right, so number of carbon atoms and the word root. Here we are going to take name and the molecular formula, so both the ways. So first of all, suppose if there is first one carbon, we call it as meth. Alkenes, no, that's why meth. Ane means basically ane. Here the names of the state chain consist of the word root and primary suffix. So now I'll be teaching what it is, what is the word root, what is the primary suffix also. So this is the word root. If it is C2, then we call it as eth. C3, prop. C4, bute. C5, pent. C6, hex. C7, hept. C8, oct. C9, non. C10, dec. C11, undec. C12, it is called dodec. Right? Fine. This is how we're going to write. This is the word root. Whenever you see first one carbon atom, you start it with a meth. So if it is alkene, we call it as methane. If it is alkene, we call it as methene. Alkene, methane will not exist, no. So alkene starts from the 2 carbon atoms, right? There is nothing called methane. It starts from ethene, right? So alkane also doesn't start. It starts with ethyne. So here, so alkanes start with meth. Alkenes and alkynes start with eth. Done. So here for alkanes, the primary suffix. So this is the word root. So for alkanes, the primary suffix is ane. This is the primary suffix. So according to this, I have taught you here. So what is primary suffix? What is word root? This is the word root. This is the primary suffix. For alkenes, it is ene. Correct? Right? For alkynes, it is ine. Suppose I have to take the name and molecular formula. Now here this is meth, isn't it? Now the same thing I'll be taking here. Meth. So alkene I'm taking methane. Next one I'll be taking ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, nonane, decane. Okay, so undecane, dodecane. Like that you have icosane, for 20, trioctane for 30, right? If we will write the molecular formula now. So this is basically when I have to write the general formula, it is for alkenes, it is CnH2n plus 2. That means if C is equal to 1, it will become C1 H2 into 1 plus 2. That is nothing but CH4. So methane, how much? C is equal to 1. So what is the formula? CH4. Second, it is C2H6, C3H8, C4H10. Pentane is C5H12. So hex is C6H12. Heptane, it will become C7H16, 18, 20. Decene is H20, 22, 24, 26, like that. Right? So this is the word root. This is the primary suffix for alkane. Right? Now, with the same alkane, so it will be the same for alkenes, alkynes. But there for alkenes it is CnH2n. For alkynes it is CnH2n minus 2. Done? Yes. Now, let us come back and start with the nomenclature of alkyl groups. So, what is alkyl? Basically, when I take an alkane, right, this is alkene. You take out ANE and you add YL. This will become alkyl. Okay. So, word wise, the primary suffix wise, I know it is "il." But how will I get? So, if I take an example, CH4 is methane. I'll take out one hydrogen. Okay. And I'll add any other group. Like it can be anything. Suppose if I'm adding X, that is any halogen, it will become CH3X, alkyl. It is alkyl halide, like that. Done? Right. So suppose the first alkene, methane. Correct? So here, name of the alkene is what? Methane. So how would I write this one? For alkyl group, so methane will become, name of the alkyl group, methyl. Okay, so CH3, one hydrogen less, CH3. Now, second one, I'm taking few examples. C2H6. This is ethane. This will become ethyl in case of this, with one hydrogen less, C2CH3. Further, if I write C3H8, this is your propane. This will become propyl. I'll write one hydrogen less, isn't it? So CH2, CH2, CH3. See here, count. This is C3H8. Now this is C3, hydrogen C3, 4, 5, 6, 7 only. One hydrogen less. See here, I've taken out one hydrogen. Like that it continues. Suppose if I write C10H22, this is called decane. Now alkyl is decyl. So one hydrogen less than this. Nothing but CH2, CH2 taken 8 and CH3. Now count 8. 8 to the 16, 17, 18, 19, 20, 21 only. Here there are 22. So this is how you name the alkyl group. So hydrocarbons we have seen, alkyl we have seen, right? Done? Yeah. Now let's see the nomenclature of branched chain alkenes. So let us see the rule. What is the important rule? What should you remember when we name the compound? So the first rule is the longest chain rule, and next one is longest chain rule. Next one is lowest number rule. The third rule is alphabetical order of side chain. Like that, I'll be teaching one after the other. Right. So here, when I have to name a compound, suppose an alkane is given to me, I have to name the alkane. What is the first rule you have to remember? The first rule is longest chain rule. So this is the initial step of nomenclature to identify the longest chain. As soon as a compound is given to you, you have to identify the longest chain. Then you have to start giving it. Let us see the correct way and let us see the incorrect way. So this example is given to me. Right. So first I said naming or knowing the longest chain. Let us count. Suppose if I have written a molecule like this, let me number 1, 2, 3, 4, 5, 6, 7, 8, 9. Done. So this one I'm numbering it in different way. See here, I'm starting from 1, 2, 3, 4, 5, this is 6, this is 7, this is 8. Right? Done. Here when I see which is the correct way, among both, see here, this here, it is only 8. Here, the number of carbons are 9. So which is the longest way? Which is the longest chain in both? This is the longest chain, isn't it? There are 9 carbon atoms here. There is only 8 carbon atoms here. So which is the correct way? This is the correct way. Because this is the correct way. This is the incorrect way. You should not name it, number it like this. This is incorrect because you're getting only 8 carbon atoms. So this is longest chain rule. Now next one. Lowest number rule. What is lowest number? Here, numbering of the parent chain. Now I know which is the longest chain. If numbering of the parent chain is done, how is it done? In such a way that the substituents attached, whatever substituents are attached to the parent chain, they should get the lowest possible position. Once again, whenever you are naming, what should you remember? Step 1, I have to remember it is the longest chain. After that, whatever substituents are there, the substituent should get minimum number or the lowest possible position. Right? Let us see. If I start 1, 2, 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9. Now here, if I am numbering, let me number from this way. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, longest chain is 9. That is confirmed. I should not take this, so I have taken 9, 9 both. Now here, in this case, the substituent whatever is there, out of the two ways, this is correct or this is correct? Let's see. So the substituents here are getting lowest position. One substituent is getting 2, one more substituent is getting 6. Whereas here, the substituent is getting 4 and the substituent is getting 8. So what did we say? According to lowest number rule, the substituent should get minimum or lowest position, lowest possible position. Okay, right? So here the substituent is getting 2 and substituent is getting 6. Here the substituent is getting 4. Here the substituent is getting 8. Which is right? This is correct. This is incorrect. Right, students? Hope this is clear. Fine. So longest chain rule and next is lowest number rule. After that, the third rule which we are going to follow is alphabetical order of side chain. Right. So here let's see. Basically, we have alkyl groups. In this case, you should remember the names of the alkyl groups are prefixed before the parent chain. Understood? Yes. Once again, names of alkyl groups are prefixed before which one? Before parent chain. Okay, before parent chain. Now, I know I have to give the longest chain, this one, isn't it? Now let us number 1, 2, 3, 4, 5, 6. Right? This is a first because parent chain or the longest chain is 6, isn't it? Right? Fine. So let's start naming it. I said the alkyl group should be given before the parent chain. That means parent chain always at the end. And it should be given according to the alphabetical order. So which is this group? This group is methyl group. This group is ethyl group, isn't it? This is NEET. This is EAT. According to the alphabetical order, first comes E, A, B, C, D, E. Then comes M, isn't it? So where is eth group? It is present at the position 4 ethyl. Next 2 methyl. So what is the parent chain now? 6 carbon atoms. It is nothing but hexane. Hope it is clear, students. Done? Yes. Now let's come back and do the next example. Now again same thing. First you have to give the longest chain. Right? So number it. Give the longest chain. Let's start naming the compound. Now here I'm naming it as 1, 2, 3, 4, 5, 6. Done. So here, which position you have? You have, now this is methyl, this is methyl, this is methyl. So not a problem. Start from here. 2, 2, 5, trimethyl. How many? 6 carbon atoms. This is hexane. Done? Yes. So welcome back, students. After your equilibrium chapter, okay, as on the students' request, I'm going to start with organic chemistry. Right. So in organic chemistry also, I've tried to pick up the basic thing, that is general organic chemistry, GOC. I'll be teaching you in a different way, GOC. I'll be teaching you about the concepts so that you can directly relate it to your questions. Done. So let us see the first concept in GOC which you should remember. So in GOC, we very well know we are going to study about homolytic cleavages, heterolytic cleavages, inductive effect, mesomeric effect, resonance effect, on all these effects, right? So formation of intermediate carbocations, carbenes, everything I'll be teaching you. So in GOC, first of all, I picked up a concept which is very important in terms of your examination point of view, that is electronic effects on acidity and basicity. So this is the concept which I picked. Gradually, when I complete the concept, then I'll go back to your inductive effect, hyperconjugation, resonance and everything. So what is the topic? I'm going to explain you impact of, most of the questions are asked on this, impact of electronic effects, on which one? On acidity and basicity. Okay, this is the basic concept. I'll be teaching you different concepts in this. Very important. So try to understand this. Right. So whenever I speak about acidity, now let me start with acidity. First of all, let us learn concept 1. I'll be teaching you about 9 to 10 concepts in this. First concept. What is the concept? Whenever you have electron withdrawing group, right? So suppose if you have electron withdrawing group in this particular compound. So remember, whenever you have EWG group, right? So EWG group, that is what will it have? It will have two things. What are they? Minus I and minus R effects. Okay, I'll teach you what is this also again. First remember as a concept now, right? So minus I and minus R effect containing, what do they do when you have electron withdrawing group? The first important concept which you should remember, I'm putting it in this one. You have to remember, whenever electron withdrawing groups are there, acidity, I'm talking in terms of acidity increases. Remember this. Right, so whenever you have electron donating groups in the particular compound, what two effects will be there? Plus I effect and plus R effect. Then what will happen to the acidity? Opposite it is, electron donating group, acidity decreases. Right, let us see certain examples in this. Suppose, let me turn the page. Suppose if I have a compound like this, CH3COOH. For this compound, the pKa value is 4.8. Okay. Now I have one more compound. Let's see. I have an electronegative atom, fluorine, CH2COH. I have one more compound with chlorine combination, CH2COH. After chlorine, bromine, I'm picking up CH2COH. Now after bromine, iodine, CH2COH. Now let me write the pKa value. For acetic acid, it is 4.8. For fluoroacetic acid, it is 2.7. Then after this, chloroacetic acid is 2.8. For bromoacetic acid, it is 2.9. For iodoacetic acid, it is 3.1. Now, as per the power, if I have to see, now I have to write the increasing order of this one, right? So, as First, there are two conditions. First of all, if I have to write as per the power of minus I effect, I will be writing in terms of power of minus I effect on this, right? When I have to write or the order in the exams, they ask you in terms of minus I effect, what should you write? Fluorine greater than chlorine, greater than bromine, greater than iodine. You understood? Now, so according to this effect, when I have to write the order, what will be the order? FCC2CH2COH greater than Cl CH2COH, which is greater than bromine CH2COH, which is greater than iodo CH2COH, which is greater than acetic acid. This is the first concept. So what should you remember? Whenever electron withdrawing groups are present like this, because the difference in electronegativity, right? The most important concept is you need to see in terms of this is we already know electron withdrawing group. Electron withdrawing group means minus I effect. Minus I effect means tendency to drag the electrons when the electron withdrawing groups are there. So the order also should be always fluorine, chlorine, bromine and iodine. So this is the order, right? Hope you have understood this first concept. So remember this, right? Let us go to the next concept. I'll be teaching one more next concept. See this. What is this? Let us name this as concept 2. Remember, based on the concepts only. In concept 2, now we will be speaking in terms of, now we have spoken about fluorochlorobromine iodine. Now what will happen if I have the same thing? Let's see. Now more will be the number of minus I effect containing groups. First important concept, more the number of minus I effect means electron withdrawing group effect, minus I effect containing groups. Remember this. Groups. So more will be, I'll give you an example, you will understand. More will be the number of minus I effect group. What will be more? I have to say, so as soon as you see minus I effect group means electron withdrawing group means, as I said, acidity increases. Acidity increases. Correct example, let us take. Suppose if I have a compound CCl3COH. This is one compound. There is one more compound CH2COH. Okay, one less, right? One more compound Cl2CHCOH. If I have to write the pKa value for this is 0.64. For this it is 2.8. For this it is 1.3. Now, as per the acidity order, I said more number of minus I effect. If the more number of minus I effect will be there, acidity increases, I said. So, in this particular case, which has more number of minus I effect electron withdrawing group, this compound Cl3. See here. Ma'am, what is this? You are speaking about smaller values. Smaller the pKa, larger is the acidity. We very well know that. Remember that. Smaller should be the value, larger is acidity. So here, more number of minus I effect. There are 3 chlorines. See, there's 1 chlorine, there are 2 chlorines. So the first would be this one. That's why the value is very less and higher acidity. Next, the next compound, which is this one is Cl2, this one 1.3. Next compound is this. So if I have to write the order of acidity or this one, what is the first? Let us name this as A, let us name this as B, let us name this as C. So what should you remember? More of minus I effect group, more is acidity. So which will be first now? A will be greater, then C will be greater than B. This is the second concept. Hope you have understood this concept. Right. Let us come back to concept 3. So in concept 3, what am I trying to explain you all? Just see concept 3. Right. So suppose they are asking you a question. Among formic acid, let us write that concept also. Among formic acid, what is formic acid? Formic acid is HCOH and benzoic acid. Benzoic acid. Right? What is benzoic acid? C6H5COOH. Now, among these two, if they ask you which is a stronger acid, right, and why, if they ask you this concept. So, right, let's see. Suppose if I have to write formic acid, if I have to check the pKa value, formic acid pKa value is 3.8. Benzoic acid C6H5COOH pKa value is 4.2. Smaller the pKa, stronger is acid. That is understood? Yes. So what will I write? HCOH is a stronger acid than C6COH by COH. Remember this concept. Why? How did we write? Smaller pKa value, higher is the acidity. This is the higher is the acidity. This is the concept which you have learnt already. Right? Done. So now let me first of all let us learn the reason now. Why is this one? Because when I have to see both the compounds have stabilized, I'm going to speak in terms of the resonating structures. Let me show. First of all, why is this more stronger? I'll tell you. First of all, I'm taking formic acid. This formic acid, how? This is going to show it'll get resonance. The carboxylate ion gets resonance stabilized. How? First thing, hydrogen, this carbon, this double bond O, and this 1 2, right? Now 4 minus. Now this will break up into minus and it will break up into H plus also. Let us put this in bracket. Now first thing, there is drop of electron here and the shift of bond. This forms the carboxylate ion, isn't it? This is the carboxylate ion. It is resonance stabilized. It has two canonical structures, rather, if I have to say. This in this case 2 minus because there's shift of bond and there is a double bond here. Correct? Right. Now further, if I have to draw the resonance hybrid for this, I'm drawing the resonance hybrid for this. This is hydrogen. See, these two exist between these resonance hybrid structure. Oxygen minus. What is this? This is called resonance hybrid. Resonance hybrid. Now let us learn the same for benzoic acid also. So in terms of benzoic acid, this is your benzoic acid. COH, OH. Now this is going to form two resonating structure. This also breaks up and H plus. First benzene ring. Okay, right. Now this is the bond O and this is O and pair. It's going to shift here. This also will shift here. This forms a resonance hybrid between one more canonical structure. Okay, because this is shifted, this gets O minus and oxygen double bond. Right. Now this is a resonance hybrid of what? Benzene ring, C, oxygen minus. This is a resonance hybrid. Okay, right. Now I said formic acid is more acidic than benzoic acid. Now I have drawn both the resonating structures. Both have carboxylate ion. Correct? Now let's see this. Now in this case, in this first case, where what in the case of formic acid. Now let us start reasoning it. Now in this particular case, H, C, double bond O and O minus. Okay, right. This particular H, there's no role for this H, if I have to say. It does not do anything. There's no role for this H. But when I have to write, let me write no role. Suppose if I have to take the same benzene ring, benzoic acid, both the carboxylate ions I have written, right. Now this is your which group? This is your phenyl group. This phenyl group, what does it have? It has both minus I effect as well as plus R effect. Correct? What is this? Minus A effect is what? It is electron withdrawing nature. Electron withdrawing nature. Whereas plus R effect means what? Electron donating nature. This is withdrawing nature, this is donating nature. So most important thing, what should you remember in this case? You have to remember plus R effect is greater than minus A effect. So this is the carboxylate ion, this is benzoate ion. So plus R effect donating is more. Okay, plus R effect is greater than minus A effect. So overall, if I have to see in this case, C double bond O minus, this case ion is, what will happen? What is this ion? This is benzoate ion. What will happen? Because of this minus R effect electron donating group, this benzoate ion is destabilized. When it is destabilized and less stability, and its stability is lesser than destabilized, I said, that means its stability is less than carboxylate ion, that is formate ion. So once again, benzoate is destabilized because of plus R effect. Okay, destabilized due to plus R effect. So when this is destabilized in plus R effect, what will happen? Which is more stable now? This doesn't work, isn't it? It can't donate that particular H plus. So this, because of this destability, benzoate ion. That means your this one, if I have to write, okay, let us write in terms format ion. Here it is not showing any plus R effect or minus A effect. Not a problem. Stable enough. So formic acid. This is more stable. Okay, let us write that stable. Stabilized. So now I can write this is destabilized, this is stabilized, right? Because this is not showing any effect, but here it is showing two effects. In that, R is dominating. If R is dominating, it is more stabilized. Hence, formic acid is stronger acid than benzoic acid. Remember this concept, very, very important concept for your examination point of view. Right, now let us come back and start with the concept 4. Suppose in the exam paper, right, they've given you certain order like this, or they've asked you this particular question. See how to remember this. What is that question? If they ask you why, or in the choice question, if they give you why CF3COOH is 10 raised to the power 5 times stronger than acetic acid. Okay, I'm comparing between these two. Okay, you can directly say, as I said, electron withdrawing group. An electron withdrawing group is there, more number of electron withdrawing groups, more is the acidity. That is what we have learned, right? So now when I have to just speak in terms of pK, CF3COOH has a pK value of 0.2. Right, it will be given in some books. It will be given as 0 also. Like it is not wrong. It is not right. 0.2 is the correct thing. Done. So now very, very less, isn't it? There's so many acids which have negative values also, right? So remember this, because smaller the pKa value, stronger is the acid. Point number 1. Second concept: more of the electron withdrawing group, more is minus I effect, and hence more higher is the acidity. Remember this. So for further information, I'll give you certain data which will be very useful in the exam also. Now let us see this compound. Let me draw one line. Many compounds are there like that, which have if they give you the order which is more greater, which is acidic, you can remember this order. The compound I'm writing pKa value also, right? Suppose if I take HI, the pKa value is minus 10. HBr, pKa value minus 9. HCl, it is minus 7. Sulfuric acid, minus 5. Okay, right, let me turn the page. Again, I am writing, yes, after sulfuric acid, nitric acid, minus 1.3. Right, so now CH3C, okay, double bond O plus and H, right, and NH2. This is 0, 0. Okay, zeta ion, I'll show you why it is this also, right? Next, CH3C triple bond NH. This is minus 10.1. I'll do a question on this, please remember. CH3SH2 plus minus 6.8. Next, CH3CH2, right? I have to take this plus and H and H. Minus 2.4. I'm giving you remember the order, so that's given in the exam. It's easy. CH3SO3H minus 1.2. Okay, there's so many acids like that. You can remember this order, so that's easy for you. If they give you the order of acidity, you can name this. Done. Let us come back and learn concept 5 now. So next concept 5. What am I learning? So in concept 5, suppose I have a compound like this. What is this? Cl2CHCOH. I have one more compound like this, F fluorine CH2COH. Right, now the pKa value for this, if I have to write, is 1.3. Here it is 2.6. Now question is, among these two, right, which is more acidic? Right, suppose there are no pK values are not given, then how will you decide? First important thing you have to remember, 2 chlorine atoms have more electron withdrawing power than single fluorine atom. That is the first concept. So as the same concept I'm again explaining, more of the electron withdrawing group, more is acidity. So the reason is 1. Just see here, double 1.3 and 2.6, which is double. So again, smaller the pKa, stronger is the acid. So what should you write? More number of electron withdrawing group in case 1, hence higher is the acidity. Okay, this is the concept. Now let us write. That means Cl2CHCOH is a stronger acid than FCH2COH. Remember this. Please, they'll give you in the form of questions. Right. Now let us see concept 6. What am I trying to explain in concept 6? In concept 6, yes, right. So if they give you now inorganic acids, they've given you certain inorganic acids like suppose H2S is given, then HCN is given, then carbonic acid is given, inorganic acids are given to you, right? So if they ask you among this, these are all what? These are weak inorganic acids. Weak inorganic acids. Correct? Yes. So what is the order of acidity, they'll ask you, right? So you will you have to remember the order like this. Among this, H2CO3 stronger, H2S stronger than HCN. Remember this. Even when I write the pKa value, carbonic acid pKa value is 6.4, H2S pKa value is 7, HCN pKa value is this. Smaller the pKa, stronger is the acid. So higher is this acidity. Right? So let us see concept 7. I'm going to give you one more concept. So let me write this as concept 7. Now, in concept 7, suppose you have different compounds. Now you have different groups like thiol or alcohol groups like that. Let us see what it is. Now I have compound like CH3, CH2, SH. I have compound like water. I have methanol. Then I have CH3, CH2OH. I need to compare the acidity of this. What should you first find out? Now let me start. For alcohols, if I take the alkyl group, this alkyl group, yes, this is bigger, and pKa value also will be more and more. So according to the acidity order, if I have to see acidity order, first one, yes, thiol. Okay, thiol also is there, thiol group. Yes, so this also and this also, both the things. That means, what should you remember the concept? More number of R groups, then like if the number of R groups are more, like if I have to say more number of R groups here, right? So the pKa value also will be more. pKa value will be more, more and more. Remember this. So as per the acidity between thiol, methanol, water and alcohol, okay, and this one, which is this, I'll write the order, then you will see here. First of all, for thiol, CH3, CH2SH, the pKa value is 10.5. For methanol, okay, the pKa value is 15.5. When I take about water, the pKa value is 15.7. When I take ethanol, CH2COH, bigger alkyl group, isn't it? So it is 16. So what is the order if I label it as A, B, C and D? Right? Now, you need to compare between this group and this group also. Electronegativity. Right. So according to this order, which will be the stronger one? A. Okay, let me write this. A will be a stronger acid. Then B will be a stronger acid than C. Will be a stronger acid than D. Remember this order. Right, now let's come back into concept 8, where I'll be giving you the general order, acidity order for compounds containing the C double bond O, right? Let it be acetic acid, or ketones, or amides, or peracids, like all these ketoesters and all these compounds. Okay, I'll give you the examples also, right? First of all, remember the order. What is the order? First, the higher acidity is the organic acid. Highest acidity. In the exam paper, if they ask you which is more acidic, remember this order and go. It's easy for you, right? After organic acid, it is peracid. After that, it is dialiphatic diketones, greater than beta ketoesters, which is greater than formaldehyde, greater than benzaldehyde, that is PHCHO, greater than acidamides, greater than aliphatic aldehydes. Remember this order and go. It's easy. Not other than formaldehyde. Remember that. Other than HCHO. Right. You can write it in the paper. You'll get that practice. Aliphatic ketones. Then aromatic ketones. Aromatic ketones greater than acid halides. In that acid halides also, fluorine greater than chlorine, greater than bromine, greater than iodine. Right. Now acid anhydride, which is greater than acid anhydrides, which are greater than esters. This is the order. If you remember this order, any sort of example they give you, you can remember this. You can just mark that question. You'll easily get that answer, right? Suppose if I have to write the pKa values for certain compounds, like organic acid, I said, okay, organic acid aliphatic, organic acid, that is aliphatic I'm picking up, that is acetic acid. So this one, acetic acid, CH3, C double bond OH group. See, isn't it? You have the carbonyl group. The pKa value here is 4.8. Right. Suppose if I write aldehyde, CH3, CHO. This is 17. If I have to write a ketone, it is 20. If I have to write CH3 ester, 24.5. If I have to write amide, it is 16. If I have to write a peracid, this is what? Peracid. CH3, CO. Peracid means 2 oxygens, 8.2. If I have to write an ester, okay, not ester, ketones. Then if I have to write formic acid, 3.8. If I have to write beta ketoester, beta ketoester, 10.7. So this is what? Beta ketoester. Right. Suppose further I am writing one more example. This is 8.9. Now I'm writing organic acid aromatic. Organic acid aromatic. C6H5, COH, 4.2. Then benzaldehyde, C6H5CHO, 14.9. So I just gave you for the information. You can note it and remember the exam. Yes. Right, now let us come back and do the concept 9. So in concept 9, what should you remember? Basically, I'm doing questions based on acidity order and basicity order, isn't it? Right. Suppose if you have a question which involves both the hydrocarbons, it is alkanes, alkenes and alkynes, and along with that if you have ammonia and amines, how should you remember the order? So in concept 9, the acidity order would be, remember, acidity order for this when you have hydrocarbons as well as amines. So the order would be, first the strongest one would be, the highest acidity would be in alkynes. remember, which is greater than hydrogen, which is greater than ammonia, which is greater than amine. So other aliphatic amines also, this will be having more acidity, this will be having more acidity than toluenes, right? Then toluene will have more acidity than benzene, right? Benzene will approximately have an acidity which is equal to your alkene. So when I see this is sp2 hybridization, right? This carbon and this carbon, done. So which will have more acidity than this one. These two are again sp2 hybridized, right? Now this will have more acidity than alkenes, right? So suppose if I take an alkene which is sp3 hybridized, so sp2 and this is sp3 hybridized, so this is the order, remember that. So first always remember, only if you have only alkenes, let us do this as concept set 1 and this is set 2. Suppose if you have only hydrocarbons, so among hydrocarbons also you have an order, just see here, it is alkyne which is greater than alkene greater than alkane, remember this. So this will be the least acidic in nature, this will be the maximum acidic in nature. So remember this concept, because in the exam paper if they give you any of these combinations, so the order would be this. Let us come back into concept 10. So in concept 10, what are we going to take now? Right, so in concept 10, remember here like we will take different combinations. Suppose in the first question, suppose if they give you a combination of acids, different sulfuric acid, sulfurous acid, nitrous acid, hypochlorous acid, the oxy acids, right? So I'm going to write in terms of oxy acids, just remember. So in case of inorganic acids, like if I have to generalize, so I'm going to speak acidity for acidity order, should we write acidity order for inorganic acids. So see, let us see the different sets. In the first one, suppose if I have to speak in terms of oxy acids, okay, right? So oxy acids, what will happen? You need to remember one concept, that is the increase in oxidation number of the central atom, right, the acidic nature increases. So first of all, the first important logic you have to remember, increase in oxidation number of central atom, what will increase? Your acidity or acidic nature, acidity increases. What is this? Let me take an example. Suppose if you have H2SO4, one, you have HNO2, you have H2SO3, sulfurous acid, you have HClO4, okay. They're asking you to arrange an increasing order of the acidity. So when it is inorganic acids or when it is oxo acids, go and calculate the oxidation number, very important. When you calculate the oxidation number, let's see here in this particular case, when I calculate 6, 3, okay, this is plus 6, central atom is this, isn't it, central. Now here in this case central atom, right, plus 1 minus 2, 4, okay, then this will become plus 2 nitrogen. Here in this case central atom is sulfur, so when I have to calculate the oxidation number, 6 plus 2, okay, this is plus 4, right. Now hypochlorous acid, when I have to calculate, plus 1, 4, 46, okay, this is plus 7, right, this is central atom. Now higher the oxidation number of the central atom, greater is the acidity, I said. Now among all these central atom, HClO4 is the maximum, so HClO4 is highly acidic in nature with plus 7 oxidation state. Right. The next comes your 6 plus 6, that is sulfuric acid, H2SO4. This is plus 6. Now this will be greater than H2SO3. Here the oxidation number is plus 4. Then last would be the nitrous acid, HNO2. The oxidation number is plus 2. So remember this concept. Higher the oxidation number of the central atom, greater would be its acidity, right? Yes. So let's see one more. So in concept 10, let us go to the next order, the same thing. Now suppose if you have in the like the same thing, like if you speak about the same thing, like hypochlorous acid, in that the higher oxidation state, if I have the central metal atom is the same but it differs. For example, if I have to take HClO4 as one, right, then you have HOCl, then you have HClO3, and you have different oxy acids with the same central metal atom. So HClO3, and you have your combination of HOCl, HClO3 and HClO2, correct? Right. Suppose if you have the same central metal atom as I said. Now everywhere this particular central atom is here. Now here this is the central metal atom. I need to calculate. Let us what shall we write? The oxy acids having same central metal atom. Let us consider chlorine everywhere, right? Same central atom. Okay, so with this concept, let us see if we have same, what is the thing. Now here this is central, here chlorine, here chlorine, here chlorine. If I have to calculate the oxidation state of this is +7 here. We already did. Here in this case it is +1, because I hope you know how to calculate the oxidation state. Now in this case HClO3 it is +5. Now HClO2 it is +3, correct? Now I said higher is the oxidation number, increasing the oxidation number of the central atom, greater would be its acidity. Now start arranging. So once you calculate the oxidation number, the first one, this is maximum, HClO4 +7, it is greater acidity. Next comes here HClO3, which +5, this is of greater acidity. Then HClO2, this is +3. Then this is of greater acidity with HOCl, which is only +1, correct? Right. So this one, this can be written as HClO also, not a problem. Here also it is +1. So this is the order based on the oxidation number. So higher the oxidation number of the central atom, greater would be its acidity. Now let us go to next example. Now when I have to move, suppose in the exam paper they have given you which is of the higher acidity, that is you are moving from left to right in the same period. So remember one more key concept. What is that? Here what is the concept? Higher the oxidation state. Shall I write it here? Okay, higher the oxidation state of central atom, greater acidity would be greater. This is the greater. This is your first concept. I mean the concept, same thing repeated. Now in the next one, what should you say? Remember, when you move from left to right in the periodic table, okay, in a period. So what will happen? Always remember, you already know the atomic numbers, correct? Yes. So if you know, let's give you the atomic numbers, you can let's say. So when I move from left to right in the periodic table, right? So always the first important thing, acidity in a period, acidity increases. So this is one more key point which you should remember, right? So one more key, very important. So in a period, acidity increases. So how should I write the order? Suppose if they give me the certain examples, like example like HClO4, then H2SO4, then H3PO4, then H2SiO4. They have given so many examples in the question paper. So how will I write the order? I said in a period, acidity increases, I said. So when I move from left to right in a period, this what will come first? Okay, it's in the same period, acidity increases, I said, isn't it? Right. Now let us start. First comes this H2SiO4, then less than H3PO4, less than H2SO4, less than HClO4, correct? Yes. So this is the order, right? So remember this order, very important. Higher the oxidation number, more is the acidity. From left to right in the period, acidity increases. So this is least, this is maximum. Atomic number 17, isn't it? Yes. So this is 14, correct? This is 15, this is 16, this is 17 atomic number. So let us write 14, atomic number 15, atomic number 16, atomic number 17. That is from left to right in a period. Done. So now let us come back and do one more concept, one more set of listen here. Now if they're giving you different halogens, now I've come till halogens, I've started explaining till halogens, till 17 I've come, isn't it? Now suppose if they give you a combination of oxy acids with halogens, different halogens, so how are we going to learn in terms of acidity? So we are going to relate electronegativity and acidity. Remember this concept, I'm relating this. How am I relating? Yes, the key word is acidic nature. As the electronegativity increases, acidic nature also increases. Remember this concept. acidic character or acidic nature increases. Remember, I told you already, electron withdrawing group. One more key word which you should remember in your mind. Now, suppose if the electronegativity increases, acidic character also increases, I said. Suppose if I have a different examples given to me like this. Now, HOCl is given. Then HOI is given. Now HOBr is given. Now according to this electronegativity, if I have to see which is more electronegative, first is fluorine, then chlorine, then bromine, then iodine, isn't it? Yes. So fluorine is not given, so higher electronegativity, higher acidity, higher. So HOCl is a maximum. This has more acidic nature than HOBr, which has more this one acidic nature than HO, because based on the electronegativity. Suppose this is the set. Now suppose if they give you one more example like this, HClO4, HI4, HiO4 and then HBrO4, right? Then for this again the same concept, higher the electronegativity, stronger is the acid. So this one is higher acidic. So HClO4 is more acidic than HBrO4, more acidic than HiO4. Remember this. Correct? Yes. Next concept. So suppose if I take one more with this. Now electronegativity concept is over, oxidation state is over, right? So now let us speak in this term. Now if you keep oxidation state same, now oxidation state is same for everything, oxidation state is same. So the condition is oxidation state is same, right? Then how will I decide, ma'am? Condition is that how will you decide the acidic character? So you have to remember, bigger atom containing acid will be less acidic. Okay, I'll tell that also. What is the key concept here? If oxidation state is same, then bigger atom containing acid. I'll give you an example, you will understand. Containing acid. Okay, bigger atom containing acid will be, remember, less acidic in nature. Okay, what am I trying to tell you? That means if I have if I'm taking nitrogen, phosphorus, different combination, different example is given. So what is the concept? Bigger atom containing acid will be less acidic. Suppose if I have an example like this, what is that? If I have HClO4, then if I have HPO3, if I have HBrO4, then I have HNO3. Remember this. Now if I have this concept, now let us see the size. I said bigger atom. Now this is the size, atom which you need to consider, the central atom. Now among all these, which is the smallest atom? Atomic number is 7, right here. So the smallest atom is this. So bigger atom containing acid, bigger atom among these three. So this is the smallest one, right? So the smallest atom will be stronger in acid. That is what is the concept. Let me come back. Bigger atom containing acid will be less acidic indirectly. Smaller atom containing the acid will be more acidic. It's the same thing. Let us write this, both the things. Bigger atom containing acid, less acidic. Smaller atom containing acid is, this is acid containing acid is more acidic. Right, so let us write based on that. HNO3 is more acidic than HPO3 as per size of nitrogen and phosphorus. Then this is more acidic than HClO4, which is more acidic than HBr, because bromine is the largest atom among all this. This is the order. So this is the concept. Remember this. Right. Now let's come back and do the next thing. Next, in the same concept, that is concept 9, let us do one more combination. Suppose in the exam paper, if they give you find the acidity order, acidic higher acidic character given sequence. If you have a combination of such things, how? If you have a combination of water, okay, water. If you have a combination of NH3, right? If you have a combination of CH4, if you have a combination of HF, right? Now see here, what should you do? These are the examples given to you. First, remember, when such things are given, if more electronegative atom is attached with hydrogen, then this will create this electronegative atom will try to drag the electron density. When it tries to drag the electron density, it higher will be the acidity, right? So what is the concept now? What should I remember? More electronegative atom attached. Atom attached to which one is it attached? It is attached to hydrogen. What will be that? Acidity will be greater. Acidity will be greater. So remember this concept. Acidity will be greater when more electronegative atom is attached. Now let us arrange. So you just try to open this one and write. So what? Suppose if among all these, which is more electronegative? HF. So the first would be HF would be greater, right? And after that, next comes after fluorine, oxygen. So write like this, HOH, because electronegative atom you need to show. This will be greater than, I can write this as nitrogen. After fluorine, oxygen, then nitrogen, isn't it? So I can write it as HNH2. Yes, nitrogen, more electronegative. So this will be more greater than CH4, and reckon it as CH3. So now see here, electronegativity, fluorine more electronegative than oxygen. Oxygen is more electronegative than nitrogen. Nitrogen is more electronegative than carbon. Simple, isn't it? So this is your time. So remember this order. One more concept. Now let's see one more concept here. Suppose if the orbital overlap, like if I have to the acidic order, I am going to calculate acidic order of the following. Just let us see. If I am given HCl, if I am given HBr, if I am given HF, if I am given H2TE, if I am given H2SC, if I am given water, if I am given H2S, right? Now if they have given me HBr, okay, HBr is a HCl, right? Okay, HCl also I've written, right? So HI I should write, isn't it? HI. This is given to us. They were asking me to arrange the order, acidic order. So how will I write the acidic order for such things? For such things, the acidic order, you should remember, if the orbital overlapped with 1s orbital. Okay, this is 1s, isn't it? So this orbital is overlapping this one. So if the orbital overlapped with 1s orbital of hydrogen is bigger than the overlapping, then bigger than that, then the overlapping becomes weaker, because this is smaller and this orbital is too high enough. So what will happen when the overlap is bigger? It's easy to release the proton. Easily it can release proton. That means when release of proton is nothing but acidity, right? So based on this overlapping also you'll see. So the next concept is, what do you write? Bigger the overlap, the smaller 1s orbital of hydrogen, 1s of hydrogen, and bigger overlap of halogen. In this case, if I have to take halogen on the next group, whichever group, bigger overlap of the corresponding whichever this an atom is, this overlap of atom bigger, then what will happen? Release of proton. Release of proton is easy. When release of proton is easy, what will happen to the acidity? Acidity also will be maximum. So remember this one more concept. So very, very important concept. So if I have to arrange, so let me take this as one set. So among this, which one will be the higher, this one, the overlap is very high for this, isn't it? Because it is a larger atom. So HI will be more easily releasing the proton, which will be greater than HBr, which will be greater than HCl, which will be greater than HF. If I take this order, right? Oxygen, sulfur, selenium, tellurium, isn't it? The bigger one is this. So H2TE is a bigger one than H2SE, which is bigger than H2S, which is greater than H2O. This is the thing, right? So remember the order. Next concept is this. This is one concept. This is one concept. Smaller 1s orbital hydrogen, larger is the overlap of this atom, particular thing. So it can easily, the bond is weak enough, it can easily release this proton. When it easily releases the proton, acidity will be maximum in this case. So right, so that is the concept. So with all this thing, let me come back to one common order of acidity with everything which I have written till now. So I am writing the acidic nature total, so conclusion of everything which I thought, so you can remember this for the exam. First of all, HClO4 is greater, HI greater than HBr, greater than HCl, it's greater than sulfuric acid, which is greater than H3O plus, which is greater than, I'm combining all the concepts, HNO3 greater than H2 HSO4 minus, which is greater than H3PO4 greater than HF greater than acetic acid greater than carbonic acid greater than H2S greater than H2PO4 minus, which is greater than, okay, greater than, which is approximately equal to NH4 plus. Then comes your phenol, then comes your methanol, then comes your water, then comes your ethanol, then comes your hydrogen, okay, a big list, comes ammonia, then comes CH3NH2, then comes CH4, which is approximately equal to this, right? So this is what, this is your acidity order, right? Yes. Now suppose if I have to write the basic strength of the corresponding bases, like what am I writing now? I am writing the order for, right? So what is this? Basic strength. I'm writing both basic strength of corresponding conjugate base. The same thing, I am writing it with the basic strength of corresponding conjugate base. Right. So first will be the same thing, I am taking the conjugate base of that. HCl4 less than I minus, less than Br minus, HSO4 minus, less than water, which is less than NO3 minus, less than SO4 minus 2, which is less than H2PO4 minus, less than F minus, less than acetate ion, less than HCO3 minus. Then comes for, yeah, which is less than HPO4 minus 2, less than NH2, less than Cn minus. Casino will approximately have this one equal to NH3, less than PHO minus. Okay, a big list. I'm summarizing everything, isn't it? So the list is very big. OH minus, then which is less than C2H4O minus, less than H minus, which is less than NH2, which is less than CH3NH, which is less than CH3, CH2. Okay, this is a list. So in the exam paper, if they give you, you can write both as that. If that is given, that question also you can attempt. In this also, everything is covered in this. Right. Let's come back and see concept 11. So what is this concept and this, what are we going to learn? So if they ask you among benzene, they've given you a question. In that you have a combination of benzene, sulfonic acid and benzoic acid, right? So let's see this. Among benzene, sulfonic acid and benzoic acid, which is more acidic? If they ask you, just see. So if I have to write the pKa value, let me write first pKa value and then explain this. So if I have to take benzene sulfonic acid, C6H5SO3H, this is benzene sulfonic acid. The pKa value for this is 2.55. Suppose if I take benzoic acid, the pKa value for this is 4.2. Okay, now let us start explaining this. Now sulfonic acids are, when I have to say, sulfonic acids are more stronger than benzoic acid, because what is the concept? Smaller the pKa value, stronger is the acid. This is the concept, isn't it? Smaller the pKa value, stronger is the acid is the concept. Yes. Now, so sulfonic acids are stronger than carboxylic acids. Let's show this whole concept in the form of resonating structures. I'll show this. Now, first of all, when I have to take benzene sulfonic acid. Now, I'm taking benzene sulfonic acid. Why is it stronger? I'm just showing it. So, SO3, this one, SO3H. Right. When you dissolve this in water, what will happen? This is going to break cleave this together. Where does this cleave? This is going to exactly cleave here. These two together are going to form or release H3O plus, and this comes out as BH, SO double bond, and O minus. What is this called? This is called benzene sulfonate ion. Correct. Now, benzene sulfonate ion, we very well know it is resonance stabilized. Right? How is this resonance stabilized? Let us write that. So, pH, SO3, the O, oxygen. Okay, this is minus. Sorry. Yes. So, this is going to shift here. Then oxygen, this is going to shift. Then what do you get? You're going to get pH, SO3, O minus, and this becomes double bond because this is shifted here. And this is double bond O. Now further, in the second case, this negative charge drops in down. This comes here. Then what do you get? You're going to get pH, oxygen double bond. This is negative, and this is double bond still there. Right? So there are what? 3 equivalent structures. Just see here. This one, this one, this one. The 3 equivalent structures. Now, all these 3 are, they form a resonance hybrid. How do you write? EH here, sulfur. So, the shift of bond here in this case and here in this case. So, you're going to make one line here and one oxygen and put a dotted line. This dotted line shows it is resonance hybrid. And the third one, then again a dotted line, oxygen. So, this is minus. This is the resonance hybrid of this. Okay. So, benzene sulfonic acid. Now, how many do we have? We have 3 equivalent structures. 3 equivalent structures. 3 equivalent structures for making it resonance stabilized. Right? Now, suppose if I have to take benzoic acid now. Right? I'll take benzoic acid. We will explain why it is less acidic than that. So, in case of benzoic acid, that is C6H5COH. So, I am writing this instead of C6H5 pH. pH C double bond OH, benzoic acid. Now, I am dissolving it in water. So, what will break? Again, it will break here. These two will combine and release H3O plus. Hence, it is an acid. The leftover CH3COO minus. Now, negative charge, how is this dispersed? Let us write the resonating structures. In pH, this one, CO minus. First, this drops in here, this drops in here. This is a resonance stabilized, resonating structures, canonical structures. See, oxygen, because this has shifted here, this becomes oxygen, and this has dropped here, this becomes double. Now, this forms a resonance hybrid. What is that? pH, C. One oxygen. So, this is minus. This is a resonance hybrid. How many equivalent structures we have? We have 2 equivalent structures, 2 equivalent resonating structures, 2 equivalent resonating structures. Now, simple, isn't it? Now, what can you conclude? More stability of the corresponding conjugate base of strong benzoic acid is stronger than benzoic acid, isn't it? That is what is important thing. The stability of the corresponding conjugate base of benzene sulfonic acid is stronger than benzoic acid. Right. And next important thing, why is benzoic acid more stronger? Because it has 3 highly electronegative oxygen atoms in benzene. And the release of H plus easily it can release, isn't it? So what factors? It is 3 benzene sulfonic acid. First concept is it has 3 oxygen atoms which are highly electronegative. So 3H. So because of the electronegative nature, it drags the electron density and it easily donates H plus. That is the first concept in benzene sulfonic acid to be acidic. The second concept is 3 equivalent resonating structures are there. Correct. So it can easily release that H plus. Next important concept, the corresponding conjugate base of benzene sulfonic acid is stronger than benzoic acid. That is one, or that is also the main reason for benzene sulfonic acid to be a stronger acid than benzoic acid. So C6H5. So let us conclude what is, according to the acidity, C6H5 SO3H is a stronger acid than C6H5 COH. Right, now let us come back and do the last concept based on acidity. What is this? So suppose if they give you in the paper certain examples, like what are the examples? Examples are CH3 taken thrice, COH. One example. Let us name this as A. There's one more, CH3, CH2, CH2, CH2OH. Let us name this as B option. There's one more thing like CH3OH. Let us name this as C option. One more example, CH3, CH2OH. D. This is the example. Now they ask you to arrange in the increasing order of the acidity. First, what is the concept you should remember? All are alkyl chains here. So branching, more branched. So what is the concept? Branching leads to decrease in acidity. Okay, what is the concept now you should remember? Higher the branching, lower is the acidity. Remember this concept, higher is the branching, lower is the acidity. Right, so what is this one? So if I have to write on this basis, we'll write the reason also. Let us write the order. What is the first thing? What is the higher this one branching? So tertiary, that is least. So which will be, this will have least acidity, which will be minimum. CH3OH will be greater. Then comes CH3, CH2OH. Then comes CH3, CH2, CH2OH. Then so remember this, higher the branching, lesser will be the acidity. What is the reason for this? If I have to write, reason is, if the conjugate base is if I have to speak in terms of conjugate base of this, the conjugate base will be highly hindered. In means the particular thing will be the effect of that will be hindered, and it cannot be solvated, right, easily. So the solvation energy will be very, very less, and it will also, when the solvation energy is very less, it will also have the corresponding conjugate base also is destabilized, hence it is lower acidity of that. So what did I say just now? What is the reason for this branching case? You have to write is, if the conjugate base is highly, like in this particular case, let us write conjugate base will be hindered, highly hindered, rather hindered, and it cannot be well solvated. When it cannot be well solvated, so solvation energy will be less. When the solvation energy less, what will happen? It will destabilize the corresponding, it will destabilize corresponding base. When it destabilizes the corresponding base, what will happen? Yes, acidity is lowered. Acidity is lowered of which one? Of the corresponding acid. Corresponding acid. This is the concept. Right, so this is how is a concept. Fine, hope it is all clear for you all. So let me come back and do important concepts in general organic chemistry. Let me meet you all in the next video. Right, now let's come back and solve or learn the important concepts of GOC. That is the first important thing, that is inductive effect. So here I'll be giving you different examples, how to do the increasing order, decreasing order of acidic strength, basic strength, and everything based on the inductive effect, based on the carbocation, everything I'll be doing it. Observe the video carefully. Right, so whenever inductive effect, whenever I have to study inductive effect, what is the first important thing you have to remember? It is a permanent effect, right? So remember this concept. What is this? It is a permanent effect. Where, when does this occur? Where does this occur? This is going to operate, or this inductive effect operates only in polar covalent bond, right? Observed in polar covalent bonds, right? So now whenever how is this happening? There's an development of partial positive charge and partial negative charge, because there is a drift of shared pair of electrons towards, because you have one element. I'll give you certain examples. The more electronegative element towards a more electronegative element, there's a drift or shift of electrons. When the shift of electrons towards a more electronegative element, what will happen? There's a formation of certain fractional charges or formation of charges, both the partial positive charge and negative charge, because the difference in electronegativity will be there, isn't it? The electronegative atom tries to drag the electron density, so that will get the partial positive negative charge, and the one which has lost the electrons will get partial positive charge, right? Fine. Now suppose when a carbon atom is bonded to hydrogen and there is another carbon atom bonded to another carbon atom, right, by a covalent bond, such as alkanes. Now how will that be then? How will you speak in terms of there is no electronegativity because both are same, isn't it? It's carbon and carbon. How will you speak? So that, let me start now. Fine. So hope you understood. Difference in electronegativity creates the charges. This charges may be partial, that will be a partial positive and negative charge, and sometimes small fractional charges also can exist. Suppose if I have a condition like this, let me take an example. Suppose if I have carbon hydrogen in this case, or if I have, or the same thing if I write like this with pair of electron. Now what will happen here? What type of sharing you will have? It is symmetrical sharing of electron pair. Symmetrical, because there's no difference in electronegativity. Symmetrical sharing of electron pair. This will happen. Right. Now suppose if I have carbon like this, or the same thing I can write it as carbon bond carbon. Now what will happen here also? Here also symmetrical sharing of electron pair. Symmetrical sharing of electron pair, because there is no difference in electronegativity. But now in this case, suppose if you have an electronegative atom present. Now, or if I have to write like this, it is X, okay, dot 2 electrons. Now this is electronegative, this will drag the electron density towards itself, right? So what will happen? This will get partial positive charge, this will get partial negative charge. Now because of this, origin of fractional charges due to greater electronegativity of the halogen will happen. Now that's why they get this. Here equal sharing, here also equal sharing, but here it is unequal sharing. Correct? Yes. So what should you remember? Now the direction of displacement, if you have to show, like how is it shown from when it is shifting? You have electronegative atom. How is this shown? The direction of displacement of charges. Direction of displacement is shown in this way. Of displacement is shown by an arrowhead. Right? What am I trying to explain? Suppose if you have one like this, one carbon, one more carbon, one more carbon, one more chlorine here, electronegative atom. So let me name this as C1, name this as C2, because we'll start from the functional group C2, C3, and this is C4. You're going to show it by an arrowhead in this way. Arrowhead, we call it as arrowhead. Electronegativity is dragged. So this is going to drag the electron density, negative charge. This will get one positive charge. This will be getting, then this will attain, and this, and further. So the electron density is dragged towards this, right? So this is the direction of displacement. Correct? Now the inductive effect of an atom or a group of atoms, right, it decreases with distance. The first important point you have to remember, inductive effect decreases with distance. As the distance increases, means farther and farther, the inductive effect decreases. Right? In fact, if I have to speak, it is almost negligible beyond 2 second, beyond third. From here only the inductive effect starts decreasing. So inductive effect decreases with distance. So remember this keyword, right? If they give you in this, right? So basically inductive effect, it does not involve actual transfer of electrons, right, from one atom to another, but it is only displacing them permanently. It will displace them permanently, not actual transfer, but displacing them permanently. Permanent effect, I said. Now suppose again in this, inductive effect is of two types, minus I effect and plus I effect. Right. So groups with minus I effect, now what are they? Let us see the examples. NO2 is greater than Cn greater than COH. These are all electron withdrawing groups. These are all electron releasing groups. Remember this. So electron releasing groups, electron withdrawing groups. Right, in that order I am writing. Greater than CO, then fluorine, greater than chlorine, greater than bromine, greater than iodine, greater than OCH3, greater than C6H5. Right, so this is the decreasing order. So this is the maximum, this is minimum. Now plus I effect, electron releasing groups like, now tertiary will be more alkyl groups, greater CH3 greater than C2H5 greater than CH3 greater than H. So this is the decreasing order of plus I effect. This is the decreasing order. This is maximum, this is decreasing order of this. Right. So the phenomena of inductive effect is like, I can use this concept to explain different examples. Let me come back and explain you. Now this is the basic concept of inductive effect. Now with this I'll try to explain different concepts. Right, now based on the inductive effect, right, that concept of inductive effect, and now I'm going to show you how to apply that inductive effect in different examples. Now let us speak the relative reactivity of alkyl halides. I'm using the inductive effect only in all these concepts. I'll be explaining many different examples on this. Now what is it? Based inductive effect means difference in electronegativity, correct? Yes. So now based, if you have an halogen atom, alkyl halides halogen atom, if I have two examples like this, now CH3Cl, right? So now how should I write? Now this particular thing has an electronegative atom, so how can I write this? I can write this as CH3, the electron density shifts, isn't it? That means the arrowhead like this, in this way, CH3 Cl, this way, isn't it? So what will happen? It will get a partial positive charge and this will get a partial negative charge, isn't it? Yes. So what is that? The site for that, now which is this one? This is deficient. Now this is the site for the attack of electron rich reagent. Electron rich reagent will attack this because this is already deficient, and further reaction happens. Now what will happen? The presence of halogen atom in the molecule, yes, of alkyl halide, it creates a center for low density which is readily attacked by negatively charged reagents, because this tries to pull the electrons. It will create low it will create the deficiency here. So what is this site? This is the site for attack of electron rich reagent. This is the concept. Now this is for reactivity of alkyl halides. Now when I speak in terms of dipole moment, now what is important? As the inductive effect increases, dipole moment also increases. This is the important concept which you should remember. What did I say just now? As inductive effect increases, dipole moment value also increases. Remember this concept. Yes. So based on that, if I have to take CH3I, CH3Br, CH3Cl, right? Again this is electronegative, it drags the electron density. This is also electronegative, this drags the electron density. This is electronegative, this drags the electron density. So among all these, which is highly electronegative? The fluorine, chlorine. So higher the electronegativity, more is the drag. When more is the drag, the dipole moment also will be maximum. So this is 1.83, okay, dpi. This is 1.79 dpi. This is 1.64 dpi. Right. So what is this? The electronegativity value. This is, okay, if I have to say less, then this is less. So the same concept, higher the electronegativity or more is the electronegative atom, higher is the inductive effect. Higher is the inductive effect, more is the dipole moment. So now next concept, among this, if I have to compare the acidic strength of this one, what is this? Formic acid and acetic acid, right? So now what will I speak? Methyl group in this both the case. This is methyl group, this is electron releasing group. Methyl group is an electron releasing group means which effect? Plus I effect. When it has plus I effect, therefore acetic acid is weaker than formic acid, means it keeps on donating. See, when you have this certain pull in the this one only, the concept of inductive effect starts. When you have plus I effect, all the electron will be releasing continuously. That means the inductive effect decreases. So among these two, what is this? CH3 COH double bond O. The second one HC double bond O OH. Correct. So now what will happen? This will donate the electrons, arrowhead. From here this is donated to this, correct? So from here this is again donated to hydrogen. It's meaningless, isn't it? Right? In this case then you don't have any donating group. So what is the concept here? Plus psi effect or electron releasing groups, if they are present, what will happen to the acidity? Acidity decreases. Okay, this is the concept, remember, right? What is this here? In this case it is pKa value is 4.76, here the pKa value is 3.77. remember this. So what is the concept here? More of the alkyl groups, higher more of the alkyl group, the acidity will be lesser. Here there are no alkyl groups, so the acidity will be more. That's why see here pKa is less. Smaller the pKa, more is acidity. So let us come back and see. Plus psi effect, when is it shown? That means when you have electron releasing groups. When you have electron releasing groups like methyl groups, alkyl groups, then automatically the acidity decreases. You can see this from the pKa value. Again I am telling, lower the pKa value, stronger is the acid. This is the concept, isn't it? Yes. Now let us see one more. I am applying the same concept with one more. What is that? Relative acidic strength of chloroacetic acid and acetic acid, right? So what is this concept, right? So chloroacetic acid and acetic acid, that's it. First important thing, suppose if I have to take like chloroacetic acid and acetic acid, that's it. Let me write that thing. What is chloroacetic acid? It is chlorine, CH2, COH and double bond. This is chloroacetic acid. Now where will the electron cloud where will that start? This is from here, because this is more electronegative, it will drag the electrons from here. Again this will drag the electron, again it will drag the electron density from here. So this is chloroacetic acid, done. So acetic acid, now CH3, C double bond OH. Among these two, right, this is electronegative in nature, so automatically this will be more acidic in nature, chloroacetic acid. So this is greater acidic than acetic acid, because this is electron releasing, correct? Electron releasing, this is electron withdrawing, correct? So when it is electron withdrawing group, what effect is observed? Minus I effect is observed. Here what will happen? Plus psi effect is observed in electron releasing group. That is why this is more acidic. So pKa value for this is 2.86. Now for this acetic acid is pKa is 4.76. Smaller the pKa value, stronger is the acid. Hope you have understood this. So this is the concept. Please register this. Minus I effect, electron withdrawing group, acidity will be more. Acidity will be greater. Plus psi effect, electron releasing group, acidity will be less. Simple as that. Now let's see. Relative acidic strength of fluoro, chloro, bromo and iodoacetic acids. Right. If this is the concept, if you have this concept, what should you remember? So important thing is again the same thing. Like electronegativity, that concept, isn't it? Right, based on electronegativity, first would be fluoroacetic acid would be stronger acid, then chloroacetic acid, then comes your bromoacetic acid, then comes your iodoacetic acid. This is the concept, isn't it? Right. So since the inductive effect decreases with like if I have to speak in terms of distance, that also we will do. So remember, based on the electronegativity or electron withdrawing group, this is the order. Now let us come back and apply the inductive effect with some more examples. Now here, how will I apply inductive effect when when acidic strength has to be decided based on the distance? That means, what am I trying to speak? Suppose if I have alpha chlorobutyric acid, beta chlorobutyric acid, gamma chlorobutyric acid, N butyric acid. These are the examples. What did I say? I said alpha, beta, gamma and N butyric acids. I am taking like butane, or I've picked up 4 carbon chain. Right. So first let us see. So first important thing you have to remember, inductive effect decreases with increase in distance of halogen atom. Then what am I again saying? What am I writing? Inductive effect, okay, i.e. decreases with increase in distance of halogen atom. Increase in distance of halogen atom. Okay, distance of x. From where? From carboxylic acid, from COH group. That means if the halogen atom is adjacent to the carboxylic group, it is strongly acidic, is highly acidic in nature. If it is a bit farther away, it is weak. That means the carboxylic acid as well as the halogen should be very close. When it is closer, then automatically the particular compound is highly acidic in nature, right? If it is very far away, it is less acidic in nature. So I'll write the example. I'm taking these examples. So alpha chloro or alpha halobutyric acid or alpha chlorobutyric acid. What is that? CH3, CH2, CHCl, COH. Now this is alpha chloro because immediately after that, adjacent to that, this I said it is very close by to the carboxylic acid, hence it is stronger acid. Now let us come back. CH3, CHCl, CH2, COH. This is earlier it was alpha, adjacent to this. Now this has become beta chlorobutyric acid. Now this is the strongest acid. Then this will be greater than this. This is a bit lesser because beta is distance started increasing, isn't it? I said as the distance increases, inductive effect decreases, right? So inductive effect decreases with distance. So this is a bit lesser. When the again next comes gamma, CH2, Cl, CH2, COH. It's greater. And CH3, CH2, COH. This is N-butyric acid. Alpha chlorobutyric acid, beta chlorobutyric acid, gamma chlorobutyric acid, and N-butyric acid. Once again, come back. More is the distance from the carboxylic acid, lesser would be the acidity. Once again, closer is the electronegative atom to the carboxylic acid, higher would be its acidity. In other terms, inductive effect decreases as the distance from the carboxylic acid decreases. That means indirectly acidity also decreases. So let me write this. Inductive effect decreases with increase in distance of the halogen atom from the carboxylic acid, hence acidity also decreases. Right. So I am using the same inductive effect concept in this. Relative reactivity of toluene and benzene aromatic substitution reactions. Right. So as soon as this thing is given, write the structure. Toluene, CH3. This is your benzene. Now if I have to see the acidity of this. Now what type of group is this? This group is electron releasing group. This CH3 is which group? ERG. That means which effect does it show? It will show plus I effect. ERG will show plus I effect. Right. So when this keeps on donating electron density towards it. So now what will happen? Aromatic substitution reactions are generally electrophilic reactions. And electrochromatic substitution reactions are basically electrophilic substitution reactions, ESR. So methyl group, what does it do? It keeps on donating electrons. Now what will happen? Toluene with higher electron density is more reactive than benzene. Correct? Because a lot of electrons are there. This here, everywhere electrons are there because methyl group is donated. So when a lot of electrons are there, electrophile means deficient. That electrophile will easily come and attack this. So what am I trying to say? Electron releasing groups or plus I effect groups, what will happen? They prefer electrophilic substitution reactions more. Right? Electrophile which is electron deficient. So this would be greater. So toluene is more effective towards ESR than benzene because of the presence of plus I effect groups. Right. Now let's apply inductive effect to this concept. So we will learn relative reactivity of nitrobenzene and benzene. So based on the same inductive effect concept. Right. So when I have to speak about nitrobenzene and benzene, again let us write the structure. This is nitrobenzene towards which one? Electrophilic aromatic substitution reactions. So this is your nitrobenzene. Now second one is benzene. Now let us speak in terms of this. What is the nature of nitrobenzene or nitro group? Nitro group is electron withdrawing group. Correct? This is electron withdrawing group. So in the early case, what did we write? When I have written electron releasing group means plus I effect. Electron withdrawing group means minus I effect. Correct? So, right. So now when this is electron withdrawing group and minus I effect, now what will happen? This nitro group keeps on dragging the electron density towards itself. Correct? When it tries to drag the electron density, it will lower the electron density as all these sites, ortho, para and ortho. So when it lowers the electron density, when an electrophile comes and tries to attack here, will it allow? Because there is no electron density existing here. So what will happen? Nitrobenzene shows less preference towards electrophilic substitution reactions. Hope you have done electrophilic aromatic substitution reactions. Once again, this is electron withdrawing. No electron density is available here. When no electron density is available here, the concept of electrophile coming and attacking also not possible. Hence, it is less reacted towards electrophilic aromatic substitution reactions. Let's come back and see this. Relative acid strength of water, phenol and methanol. Now, as compared to water, phenol is more acidic. Why am I trying to tell this? Let us write the structure. This is phenol. Then this is water. This is methanol. Okay, right. First I'll put the reason, which is this is more acidic than water. Let us write the reason. Why is phenol more acidic? Because it has this is here. It is showing minus I effect. This ring, electron withdrawing effect, EWG group. In this case, what happened? It shows plus I effect, electron releasing group, right? So this is maximum, this is minimum. Water is in between them. Right, so welcome back students. We've already started with the concept of inductive effect. I've taught you what is inductive effect. I've also taught you how to apply or what sort of questions you'll be getting for using inductive effect for different acids, like to find the acidity between acidic strength between water, phenol, methyl alcohol, to find the acidic strength of benzene and toluene, like that. So now let us see how can I apply inductive effect to find strength of the base. That's right. So let us see. So first of all, whenever you're given a base, what is the first important thing which has to come to your mind? What actually is a base? Base is something which accepts proton, right? This accepts proton. Correct. This is the first important thing. Next, what is the next important thing you have to remember? If you're not speaking in terms of proton, you can also write it as electron pair donor. Base is an electron pair donor. Okay, right, remember this concept. Fine. So after this, based on this concept, let us do certain examples which will be given in the exam. Suppose if they ask you to arrange the following of certain examples based on their basicity, how should you do? Suppose if I take an example like this, they've given me C6H5NH2, okay, and they've given me C6H5 taken twice. Now I've taken this hydrogen replaced by NH. Okay. Then I have picked up ammonia. They've given me ammonia and they have given me CH3NH2. Now I'm supposed to arrange these according to the increasing order or decreasing order of the basicity. Let us write decreasing order of the basicity. So now when they give this order, the first important thing, I need to remember this concept. What is the concept? Base is something which accepts proton or donates electrons, electron pair. Correct. Now I have to apply the inductive effect to this, isn't it? Right. What do we have? We have two types of effects. One is plus I effect and minus I effect, isn't it? So what is plus I effect? Plus I effect are electron releasing groups and minus I effect are electron withdrawing group. That is what we have studied. Yes. So when I have to speak about amines, here aniline, this is aniline, this is also almost aniline, this is methylamine. So when I have to speak in terms of aniline, methylamine or all the ammonia group, the first important thing, methylamine is this particular thing. Methylamine is electron, if I have to speak in terms of plus I effect, electron releasing group, isn't it? So let us write this is electron releasing group. Or what type of effect does it show? It's going to show us plus I effect. Correct, releasing group. Now when it comes to this one, aniline or diphenylamine, when I have to say this one, this is electron withdrawing group, EWG group. That means which effect is this? Minus I effect. This also is the same, electron withdrawing group or minus I effect. Correct? Yes. Right. Now you can easily write. Now what did I say? When it is electron releasing, that means electron pair donor. When it is electron pair donor, isn't it strong? Isn't it high? It has higher basicity compared to this. So this is your concept now. So electron releasing group plus I effect, that means electron pair donor, that means it is highly basic. Now let us arrange the order. Now let us name this as A, B, C and D. So the highest basicity would be D, would be greater. Correct? Yes. Then when I have to take further, now after D, what is the next important thing which comes? Ammonia. C would be greater than. Next would be one aromatic ring A, which is greater than B. B would be least basic because it is withdrawing group. It goes on, withdraws the electrons. It will not allow to release. If it is not releasing, it is not a base. So this is the order. So remember, once again, higher the electron releasing groups present, more is the basicity. Let us write that also. Higher electron releasing groups are present. Higher the electron releasing group, more is the basicity. That's it. You need to remember this concept. When you remember this concept, it is easy for you to answer the ordering of that. Right. Now let us learn one more concept. Fine. So now after this concept, let us see same thing I'm applying for relative stability of carbocations. Now here in this case, when I have to speak the relative stability of carbocations, remember, yes, we have what type of carbocations we have? We have basically tertiary carbocation, secondary carbocation, primary carbocation, as well as methyl. Now I have to relate the inductive effect to this. So once again come back. So inductive effect, again I said electron releasing group. Yes, so remember, electron releasing groups are present means what type of effect is it showing? Electron releasing group means plus I effect. Correct. So when plus I effect is more, what will happen? The basicity also increases. Okay, I'm applying the same concept here. The basic strength also increases. I'm applying the same concept to this. So in the carbocation, what do we have? We have tertiary carbocation, secondary carbocation, primary carbocation and methyl carbocation. All these cations we have. Now as I said, let us write this. Tertiary carbocation. Now I said tertiary, how do you write? CH3 taken thrice C plus. This is tertiary carbocation. What is secondary carbocation? CH3 taken twice CH and plus. What is primary carbocation? It is CH3 CH2 plus. Now methyl cation is CH3 plus. Correct? Yes. Now see, all are electron releasing groups. Same concept. All will show plus I effect. Yes. All will show plus I effect means everything, all are base. They have basic strength. Now which will show maximum? Let us name this as A, name this as B, let us name this as C, let us name this as D. Now when I have to take A, there are 3 alkyl groups, means there are lot of electron releasing groups. 3 electron releasing groups means the plus I effect will be more. When electron pair donor, base is nothing but electron pair donor. So there are 3 groups which are donating. Hence this is the highly basic carbocation. A. Next comes B. Next comes C. Next comes D. This is your option. So I am again saying more of the electron releasing groups, more is the basicity. Remember that. Yes. So let us come back and do one more concept. Now how am I applying or how am I seeing this concept for inductive effect and state of hybridization? How will I apply this concept of inductive effect to the state of hybridization also? You should remember. So let us do that also. So I'll be doing different concepts. Let us see. So I'm applying inductive effect to state of hybridization this way. Just see. So inductive effect, basically how many types we have? sp hybridization, sp2 and sp3. You have further sp3 d2, d2 sp3, like that. You have different combinations, but now I'm going to speak in terms of sp hybridization, sp2 and sp3. Remember? Yes. Now first important thing, I am going to write for basicity and acidity also, stating this. So this is the order for acidity. This is the order for basicity. Yes. So now When I have to write the order of acidity, relative acidity of hydrocarbons, I'm picking up, first comes sp hybridization. This is more acidic. Then comes sp2 hybridization, which is seen in alkenes. Then comes sp hybridization, which is seen in sp3 hybridization, which is seen in alkenes. Alkynes with sp hybridization are more acidic than alkenes with sp2 hybridization, which are more acidic than alkanes with sp3 hybridization. Right? Fine. So, when I have to speak in terms of the basis of the corresponding carbon ions. So, I am talking in terms of basicity with the corresponding carbon ions. I am going to pick up carbon ions of the respective ones. Now, it is a reverse order, isn't it, for basicity, the reverse order. So, if I have to write this, basicity order CH3, now I am writing the carbon ion of this. This is the carbon ion for alkane, which will be greater than, now I have to write the carbon ion for alkene, that is, now I have to write the carbon ion for alkanes. Right. So, what is this hybridization? This is again the same thing, like we have picked up the carbon ion. So, this is the order. So, remember that. So, whenever they ask you for the acidity, the basicity order based on the hybridization, this is the concept which you should remember. Right. So, now next, the same concept. If I have to basicity of corresponding carbon ions also, okay, I did the same thing. So one more concept which they am going to ask you. Suppose the same thing I am just writing. If they ask you among acrylic acid and your propionic acid, okay, let us write. I am comparing the same thing. These two are topics of the same. Now if they ask you among acrylic acid, okay, what is acrylic acid? We will see acrylic acid and propionic acid. Propionic acid, right? They'll ask you which is more acidic, or which will be more highly acidic in nature based on the hybridization. First you will know, right? I am going to compare with this. What is acrylic acid? Acrylic acid is CH2 double bond CH-COH. This is acrylic acid. Propionic acid is CH3 CH2COH. This is your propionic acid. Correct. Now I need to explain in terms of hybridization. Now when I have to speak about this in acrylic acid, what do you have? First of all, let us compare. Here you have electron releasing group. Correct? Yes. Here also you have electron releasing group. But how will you decide? First of all, when I have to speak about the acidic strength of acrylic acid, it is higher than that of propionic acid. What is the difference? Because of electron withdrawing inductive effect of, this is sp2 hybridization, isn't it? This is where is sp2, alkene means sp2. So what should you remember? Here you have electron withdrawing nature of the inductive effect of the electron withdrawing nature, and this also has sp2 hybridization. Right. So sp2 hybridized carbon atom. Because of this alpha and beta, this is alpha and the beta bond. Though their resonance effect, the alpha beta unsaturated system will decrease the strength. Correct? Yes. So once again, this particular thing as sp2 hybridization, we very well know, compared to sp3, this is sp2. Because of this, acrylic acid is a stronger acid than propionic acid. Though it is stabilized, yes, though it shows resonance effect, but due to resonance effect tends to decrease acidic strength. That is one more concept. But here, if I come back to the hybridization, I'll clearly say that this is more acidic. Acrylic acid is more acidic than propionic acid, right? So that is the concept, right? So now let us come back and see one more topic, electromeric effect. Right. Now we are going to start after inductive effect. We are going to start with one more concept called electromeric effect. Now what actually is inductive effect? It is a permanent effect which we have told. Now when it comes to electromeric effect is a temporary effect. Temporary effect. So this is the first thing which you should remember. So first of all, when does this operate? So temporary electromagnetic effect operates only in unsaturated compounds, just like your alkynes and alkenes rather. So first important, and this is going to work on, or it depends on the demand of the reagent. In the presence of the reagent only this concept will work. Okay, what am I trying to explain? I'll tell you. First of all, whenever somebody asks me to explain what is electromagnetic effect, you have to say it is a complete transfer of pi electrons, right? Transfer of pi electrons, first point, and that too in the presence on the demand of the reagent. Now, as soon as the reagent is removed, the original compound is restored. That's why we said temporary effect. Let us write what we said. It is, what do you define electromagnetic effect? It involves complete transfer of pi electrons of multiple bond, right, at the demand of a nearby reagent. Now, and as soon as this attacking reagent is removed, what will happen to the effect? The original compound is lost, means the effect is lost and the original compound is restored. Okay, this is what is the thing. That's why we call it as temporary effect. Now, let me take a carbonyl compound in this way. Right. So 1, 2, 3, 4, 5, 6, 7, 8. First, there is a shift of pi electron as we have written. Right. Okay. First of all, these two will be in resonance, plus, and this is minus. Now count 1, 2, 3, 4, 5, 6, 7, 8, and this is shifted, and this gets minus. When this gets minus, this also gets plus. Now this is a complete transfer of shared pair of electrons of the multiple bond. How is this transferred? The shared pair of the electron is shared towards a more electronegative atom. Remember that. So again, this is more electronegative atom. Based on this more electronegative atom also, we have one more condition in that, types of electromagnetic effect. Right? Let us come back and see the types of electromagnetic effect. So now I said this transfer of electrons. So we have two types of electromagnetic effect. One is plus C effect and one is minus C effect. What is plus C effect? How to remember? Suppose if I have an unsaturated compound like this, an alkene, right? Now I have an attacking reagent. I said this will work only in the presence of a reagent. First, this shifts, right? Now, in the shift of electrons, now this hydrogen goes and attacks this carbon. What do you get? You're going to get one as plus and you're going to get one more as H. Let us take one more example. Propene, CH3, CH double bond CH2. Again you have an attacking reagent here. This is electron releasing group, the electrons will transfer. Now again there is a shift. So this hydrogen goes and comes and attacks here. It becomes CH3, CH single bond, CH3, because this hydrogen is added here, and this becomes plus now. Now what are you observing? Here you are observing, right, the transfer of pi electron takes place towards the attacking reagent. It is going towards the attacking reagent in this direction, towards. So then it is called plus C effect. So what are we going to write for plus C effect? Remember, transfer of pi electrons towards reagent. That is plus C effect. The same thing if I have to take minus C effect. Let us take, now I am taking this and Cn minus. Now attacking reagent. Right? So now what will happen? First of all, there is shift of electron. When this is shift of electron, how does this look? This looks like C oxygen minus. When this is minus, this has become plus, isn't it? Then this Cn goes and attacks this carbon. So what do I get? I get Cn here. This is minus. So now what is happening here? Here the transfer of electron is happening or takes place away from the attacking reagent. Here it is towards the attacking reagent. Here it is going beyond this. So it is away. So this minus E effect is nothing but transfer of pi electrons away from reagent. Remember this, transfer of pi electrons away from the reagent. This is what is happening. So that is minus E effect, plus E effect, and this is minus E effect. Yes. Suppose if I have to write the mechanism of this. So simple, isn't it? C double bond O, oxygen. 1, okay, let us write this 1, 2, 3, 4. This will shift here. Then what do you get? And you have a reagent also attacking minus. This step 1, this is step 1. This is a very slow step. Let me make a line. Very slow step. Then what will happen? This cyano is going to attack. Then the second step would be attack of H plus ion, because HCN will be there, right? We have done this in aldehydes, cyanohydrins, OH. This is the fast step. This is the slow step, and this is the fast step. This is how you are going to learn. This is your plus E effect, and this is minus E effect. Right, now let's come back and see the applications of electromagnetic effect. Now we have studied it is a temporary effect, and we also said this transfer of pi electrons from where? From an unsaturated compound. Now this is again minus E effect and plus E effect, which I have told you. Now let's see how can I apply electromagnetic effect. Now basically electromagnetic effect is applied in 3 things. What are they? Let me write. The first thing, let me divide the page into 1, 2 and 3. I can apply electromagnetic effect in electrophilic addition reactions. I can apply electromagnetic effect in nucleophilic addition reactions. And I can also apply electromagnetic effect in electrophilic substitution reactions. Now what will happen in electrophilic addition reactions of an unsaturated compound? Basically it will involve polarization of carbon-carbon double bond. That is what we have seen, isn't it? It involves polarization of carbon-carbon double bond. Right? What will, in which one? In the presence of electrophiles like H plus. It is also used, or I can also apply in nucleophilic addition reactions. What will happen here? This is electrophilic addition reactions of which one? Of unsaturated compounds. Let me write that. Unsaturated compounds. But when I take nucleophilic addition reactions, I can use this in which one? Carbonyl compounds. Right. So what will happen here? It will involve the polarization through electromagnetic effect of carbon-oxygen double bond. Correct? So it involves polarization. Just now I showed you polarization, isn't it? Polarization of carbon-oxygen double bond. Correct? In the presence of nucleophile. Right, here in the presence of H plus, here in the presence of nucleophile, which I showed you in the earlier video. When I have to speak the electrophilic substitution reactions, this will show in it, or it will involve benzenoids. I'll show you what are they. Here the polarization effect is shown. The polarization will happen through here due to carbon-carbon double bond, C double bond C. Here to C double bond O. Here it's going to show electromagnetic effect through when an electrophile approaches the benzene ring, it starts showing electromagnetic effect. I'll show you what it is. Suppose if I take benzene, here an electrophile approaches benzene, which you have studied in, isn't it? So what will happen here? This will shift in this direction. Then you get This becomes plus. Okay, if I have to draw the bonds like this, let me draw the bonds in this way. It's not confusing, I'm sorry. The one bond is here, one bond is here. Now further, when the electrophile attacks this, what do you get? You get this way, plus is here, and the electrophile and hydrogen is here. Suppose if I take a compound like anisole, what is anisole? This is anisole, OCH3. One bond is here, I'm drawing aromatization. One bond is here, one bond is here. So 1, 2, 3, 4. This will shift in this direction. These electrons will shift to this. Now in the presence of an electrophile, what will happen? You are going to get, just see, so double bond arises, OCH3. This becomes, because it has lost electron, this will become plus, right? Fine. So bond shifts in this direction, yes, okay. And then this is hydrogen, and further when an electrophile attacks this, what do you get? We're going to get this double bond, OCH3 is here, this plus is here, and you have 2, and electrophile goes and attacks this side. You get H and E. Correct? Yes. So like that, like everywhere you can show it here, here attacking in this direction, you can show it here. So this electromagnetic effect can be shown in both 3 electrophilic addition reactions, nucleophilic addition reactions. These 2 examples I've shown in the earlier video also, or this one, and electrophilic substitution reactions. Let's come back and learn after inductive effect, electromagnetic effect and its applications. We'll learn a topic called hyperconjugation, very important topic in general organic chemistry. So whenever I have to speak about hyperconjugation, first of all you have to remember what actually, or the definition of hyperconjugation. What is this and why does this happen? So basically hyperconjugation is a stabilizing interaction, right? It is only to stabilize the compound. So because of the stabilizing interaction, what will happen, right? There is transfer. To stabilize this, there is transfer. So first of all, let me draw a diagram and then show you. First of all, what did we say? It is a stabilizing interaction. Which will it interact here? Interaction. Which will interact? It is the interaction of electrons in the sigma bond. As well as that sigma bond can be C carbon hydrogen or carbon carbon, and with an adjacent empty or partially filled pi orbital. Okay, let me draw what I'm trying, right? I said it is an interaction with the interaction of electrons. Okay, let us write that. It is an interaction of electrons in a sigma bond. This is the first keyword which you should remember. Sigma bond can be between carbon hydrogen, or it can be between carbon and carbon. So which is this interacting with? It is interacting with adjacent empty or partially filled non-bonding pi orbital. Okay, so many things I have written, I will explain this now. Orbital, or you can also write it as anti-bonding p orbital. Anti-bonding p orbital. Okay, that means suppose if I have to take, now let's see. Now I have carbon atom, right? Now this is CH3, this is CH3. Now I am talking about a bond between carbon and carbon. This carbon again has one hydrogen here, and one hydrogen here, and there's one more hydrogen here. Right, now this also has, now what did I say? These are empty orbital. Correct, this is empty orbital. Now I said there is interaction of electrons in a sigma bond. Okay, sigma bond with adjacent empty orbital in a sigma bond. Now what is this? This is carbon hydrogen sigma bond. orbital, carbon hydrogen sigma bond. So there is an interaction between the carbon hydrogen sigma bond with an adjacent p orbital or pi orbital, which is anti-bonding pi orbital or partially filled non-bonding orbital. Remember this, yes, right. So this interaction, so what will happen, this will interact like this. Because of this is what, okay, what are these orbitals? These are p orbitals. So interaction between the sigma bond of this and the p orbitals, which are empty, is this. Because of this, what will happen, it is, what will this overlap result to? It will result to stabilizing overlap. This will try to overlap and stabilize it. Correct. Now we have taken this is butyl, isn't it? Butane 1 2 3 4. Fine. So this is what is your hyperconjugation. Now when I have to speak about this hyperconjugation, let me add some more points. Let me take one more page. Right. So because of this hyperconjugation, this concept, what actually is an important, propene, for example, right, as is found to be more stable than ethene by how much? Almost 11 kilojoules per mole because of this hyperconjugation. Because besides this, you know, even alkyl groups undergo alkyl group also undergo conjugation. Fine. So now first important advantages, as I said, one example which I said, propene is more stable than ethene because of this hyperconjugation by how much? By about 11 kilojoules per mole. Right. Let us see one more important thing. So the concept of hyperconjugation was based on the discovery of, they are relating the hyperconjugation with plus I inductive effect also. Right. And now I'll relate to. What am I relating? I am relating the concept of hyperconjugation and plus I effect, that is electron releasing groups. In the exam they will ask you this. Suppose if you have a combination of primary, secondary, tertiary like that, arrange according to that. So the plus I effect of alkyl group is normally of the order like this one, isn't it? CH3 donating. This is less than CH3, which is again like this is donating, which is less than further less than CH3. I am speaking in terms of hyperconjugation as well as inductive effect. Less than right? Yes. So remember this. Suppose further if I have to write for this one, propyl, ethyl, like that also, you can remember this order. The alkyl group also I am writing methyl greater than ethyl greater than isopropyl greater than tertiary butyl. This is also one more order you can remember. Yes, fine. So this effect is known as there's also something called Baker-Nathan effect, right? So that is a permanent effect, and in fact hyperconjugation is extension of resonance also, you can write that. So resonance is basically what? It is delocalization of pi electrons, isn't it? So hyperconjugation can also be described as double bond, no bond resonance. Let me write that. Hyperconjugation, how can I name this? I can name this as, if they ask you in the option, ABCD is given to you, it is also known as, it's an extension of resonance first thing. It is also described as double bond, no bond resonance. No bond resonance, remember this. Double bond, no bond resonance, this is one keyword which you should remember, right? So this is the thing. So let's come back and see the types of hyperconjugation. Now we are done with this. Now we'll see types of hyperconjugation. Right. Conjugation. Now, basically hyperconjugation, if I have to speak, there are three types: sacrificial hyperconjugation, isovalent hyperconjugation. Like the most important among the three, I'll explain those. Among three, I'll try to explain two for you all. So, what is the first one? The first one is called sacrificial hyperconjugation. Let us write what it is. Sacrificial hyperconjugation. Okay. Now, in sacrificial hyperconjugation, what will happen? We'll see. Now, the essential condition is that the attachment of alkyl groups to double bond or triple bond. That is the most important condition, right? So now, when I have to take an example, let me take an example. CH, right? Or you also have, now what did I say? It is the attachment of the alkyl group, correct, to the double bond, or attachment of the alkyl group CH3 to the triple bond. Now, carbon atom of this alkyl group is attached to the double bond, but one more condition is it must at least contain one hydrogen atom in hyperconjugation. Right? So, right, once again, it should be, alkyl group should be attached to the double bond, or alkyl group should be attached to the triple bond. That is the first thing. Second condition, that carbon or that carbon of the alkyl group which is getting attached should have an hydrogen. Remember that. Then we can start. First of all, hydrogen. Right. First thing, the shift and right. Now what's going to happen? I'm just showing hyperconjugation concept here. Because this is shifted, this is shifted, it's got some minus. Now further, this will, now this thing, H plus, carbon, hydrogen, double bond, okay, here. Further, now this hydrogen turn now, or this is over, isn't it? This side is also, now this hydrogen turn, right? H plus, this carbon is here, double bond, C, carbon, okay, one more single bond. So this involves a sort of sacrifice of the bond, isn't it? Every time there's sort of sacrifice of the bond, here this is sacrificing, this is sacrificing, this is sacrificing. So that's why it is called sacrificial hyperconjugation, right? So let us see the next one. What is that? The next type of hyperconjugation is isovalent hyperconjugation. Isovalent hyperconjugation. Isovalent hyperconjugation. So right. So in isovalent hyperconjugation, it involves no sacrifice of bonds. Remember that. And let me take an example. So if I have to take an ethyl radical, correct? Right, let me take an ethyl radical. There is no sacrifice here. Hydrogen. I am taking an ethyl radical now. Plus. Now we will draw the resonating structures for this. Right? H plus for this, double bond, hydrogen, hydrogen, hydrogen. Again, H plus to this hydrogen, double bond, hydrogen, hydrogen. This is again H, carbon, hydrogen. This is H plus, double bond, H and H. This is isovalent hyperconjugation. Fine. So now ethyl radicals have the same number of real bonds at the classical structure. Remember that. So that is why it is called isovalent. Same number of structures. That is classical structures, the original one. That's why it is called isovalent. Iso means same. After hyperconjugation concept, let us see the significance of hyperconjugation. So I'll be speaking the significance, I'll be relating the concept of hyperconjugation to different concepts. Let's see. So hyperconjugation I can use or speak like in terms of heats of hydration or heats of hydrogenation. So I'm applying the hyperconjugation thing in heat of hydrogenation. Heat of hydrogenation. Right. Now what is this? What is hydrogenation? Addition of hydrogen, right? So if I take an example, C double bond C, I'm going to add hydrogen. When I'm adding hydrogen, this is H here, right? Single bond, carbon, hydrogen. Hydrogen got added to around the double bond. Now what will happen? E kilocalories. So what is the thing now? Lesser the heat of hydration, lesser is the internal energy. When the internal energy is less, stability of the system will be more. So what does hyperconjugation do? It decreases the heat of hydrogenation. Remember that. So what did I tell just now? Let us write that. First concept is lesser the heat of hydrogenation. This heat, lesser the heat of hydrogenation. What will happen? Lesser is the internal energy. Lesser is the internal energy. When internal energy is less, what will happen? Stability will be more. So stability will be more for the system. So what does this do? Hyperconjugation will, it decreases heat of hydration. That's why this system will become stable. It decreases heat of hydrogenation. So hence that is the first application, and because of this the system will become stable. Suppose if I take certain examples, I'll show you what it is. Suppose if I have to take this example, CH3, C, double bond C, H and CH3. What is this? This is trans-2-butene. Now I'm writing cis now. Cis means on the same side. CH3 here, CH3 here, hydrogen here, hydrogen. Trans-2-butene opposite side, cis-2-butene on the same side. Here the delta H value is delta heat of hydration is 27.6 kilocalories per mole. For the cis, the delta H value is 28.6 kilocalorie per mole. Right? So which is more stable now? Whichever energy is this one less, right? So cis-2-butene is less stable now because the energy for this is less, 27.6. Here the energy is more, 28.6. So according to this, what is the thing when just write cis-2-butene, this one, cis-2-butene is less stable than trans-2-butene, isn't it? That is what is the concept, isn't it? Right? So that is how we are going to write in terms of heat of hydration. So that is what heat, that hyperconjugation can be related to heat of hydration in this way, right? So this is the first application. Fine. Now let me take one more example. I'm going to apply the concept of hyperconjugation to one more, or apply this to which one am I applying? I'm applying it to stability of, second application, stability of carbonium ions. I'm applying this concept to this. Right. So what is this? Greater the number of hydrogen atoms present on carbon atom, like alpha atoms, like alpha carbon, that is immediately after unsaturation. More is the number of resonating structures possible, due to which hyperconjugation, due to resonating structures due to hyperconjugation, and hence greater is the stability. Let me write whatever I said. First of all, greater the number of hydrogen atoms, okay, where present on the carbon atom, that is alpha carbon atom, alpha to unsaturation. Right, hydrogen atom present on, means adjacent to that, present on the carbon atom. Which carbon atom? It should be adjacent to alpha carbon atom. That atoms alpha to unsaturation. Immediately after unsaturation, that carbon atom. More hydrogens are present. Then if more hydrogens are present, what will happen? Number of resonating structures. Why are these occurring? Due to hyperconjugation. Due to hyperconjugation will increase. Because of number of resonating structures, stability of carbonium ion also increases. This is how you are going to relate. The third application of hyperconjugation which I am going to speak is in terms of bond length. Right? Fine. So hyperconjugation, like conjugation resonance, also affects bond length. How is it? Suppose if I take an example, I am taking hydrogen here, this hydrogen CH double bond CH2. The bond length between this carbon and carbon is 1.46 angstroms. Here the bond length of this is 1.353 angstroms. Shows hyperconjugation, then this becomes CH hydrogen double bond, because this is going to shift in this direction, minus, and this becomes H plus. Right? Fine. So here the bond length, what is this? If I have to say, okay, the bond length is 1.46, we said. Okay, fine. Normally if I have to speak about this, is 4.6, isn't it? Normally if I have to speak in terms of propane is 1.54 angstroms. Why? Here propene has a partial double bond character and acquired, and hence it is little shorter, isn't it? Now because of this hyperconjugation also I am relating once again. Propene has 1.46 compared to propane alkene because of the partial double bond character. Correct? Right. So I can also relate or apply your give this application of hyperconjugation. Let me take a paper to the next concept, that is dipole moment. Let us see the fourth application. I am going to relate or apply this concept to dipole moment. Let us write the heading, dipole moment. Right. How? Hyperconjugation causes the development of charges. Yes. So because of this, it affects the dipole moment of the molecule. How? Right. Suppose this is C double bond. The dipole moment of this is 2.27 D. Now this shows hyperconjugation. See, if I take same aldehyde. Okay, one more example. Extension of this. I am taking one more which shows, because I need adjacent alpha hydrogen, isn't it? Yes, double bond. Now taken. This is alpha hydrogen compared adjacent to the alkyl. Now this here it's going to show hyperconjugation. Then the shifts. This becomes H plus. This is H double bond O minus. The mu value for this is 2.72 D by Hubble. Now what is happening here? See the mu value, this whole thing, CHO. How much is this? This is 2.27. Now because of hyperconjugation, the mu value has become 2.72. So hyperconjugation also affects dipole moment. Significance, that is important thing. Now suppose if I take the next application. I am applying hyperconjugation to ortho-para-directing properties of methyl group in toluene. Right. So OP directing group in toluene is basically due to Prussy effect and partially due to hyperconjugation also. What am I writing? Right. Ortho-para directing property of methyl group is due to methyl group in what? In toluene. In toluene is due to two things. One is plus I effect as well as hyperconjugation. Let's see this. Let us take toluene now. Toluene is CH3, right? So if I have to write toluene, same thing like this only, same thing I am writing. Let me write in terms bonds C, hydrogen, hydrogen and H3. Now, in the first case, now I said hyperconjugation, isn't it? So first, this is going to shift here. When this shifts here, how does this look? This becomes double bond first, carbon. This becomes H plus. This is hydrogen. This is hydrogen. Right? This bond is here. Now, because both double and double can't be here, isn't it? This will shift in this direction. Double bond C, hydrogen, hydrogen, H plus. Correct? So this bond will shift here. This bond will shift here. This becomes minus. Now this is going to shift in this direction. This hydrogen, this is H plus. This becomes minus. Right? So this particular thing of methyl group, like in toluene, orthopara directing group, both you can explain due to inductive effect as well as hyperconjugation, both. Inductive effect also, hyperconjugation also. Plus I effect as well as hyperconjugation. So these are the significance of hyperconjugation. Now let me come back and meet you with the next topic, that is the resonance effect.